Okay, so it's a really great pleasure to be able to introduce Vanessa. We have, it turns out, in Southampton, a number of philosophers of science, and one that Sammy and I have been involved in talking, Will McNeil. We've had very interesting discussions, although our attempts to organise a philosophy and chemistry symposium hasn't managed to go very far. And we've been thinking about this for a number of years, and then suddenly I discovered that whilst, you know, physics and philosophy, there are even courses and everything like philosophy and chemistry is remarkably barren as far as actually people being there. And then suddenly, up in chemistry world pops Vanessa, giving some very articles about what is a chemical bond and various things like that. And that got me thinking. And I used to say one of the things that distinguishes chemists from physicists is that physicists insist everything adds up. Chemists know that things are a bit variable, so creative accounting was undoubtedly all those chemists who went into accounting. You know, it sort of adds up. We can change a little bit here, change a little bit there, invent a new possibility here. But I've come to the conclusion it's even worse than that. You know, the famous quote that all models are wrong, but some are useful, attributed to Box. Well, certainly, fine. But chemists, we have mutually contradictory models. Take how I draw a benzene ring with a circle in it, and my organic colleagues insist on drawing one Kerkulé structure for very good reasons, because we use them differently. But what's unique, I think, with chemists is that we manage to use mutually incompatible models at the same time to solve the same problem. This is, of course, a disaster when it comes to the semantic webs and things like that, where there's supposed to be an answer to something. And mutually contradictory models don't quite fit in here. So the idea of actually thinking about what do chemists really understand by things, that's why I thought it'd be really good to get Vanessa to come and talk about that. Now, I don't always sleep so well, so I'm sometimes listening to the BBC World Service, and they have a very interesting program called Crowd Science. And I'm suddenly listening to this at 2 o'clock in the morning, and they're discussing why is water wet. And suddenly, Vanessa comes on there. So here we have somebody who has actually made it onto the BBC, onto the World Service, to discuss how, well, along the lines of how much water do you actually need to have there for water to be wet. So I thought, well, this is a really great introduction. So Vanessa, it's great to welcome you to come and talk on prediction, explanation, and chemical progress in the age of AI.
Well, thank you, Jeremy, so much for inviting me. It's not the first time I've given a talk to a chemistry audience, broadly speaking, but this one tops the list, definitely. I'm so excited, and I'm a bit nervous, to be honest. So hopefully you will find at least some of the stuff I'm going to touch upon interesting. Maybe I should give some background. So I've studied chemical engineering for 5 years at the University of Athens. And then I did my PhD in philosophy of chemistry at Bristol, where I studied chemistry's relation with quantum physics. And IUPAC's Gold Book has been so useful to me. You have no idea how grateful I am. And I suppose I should say it here, because I've been using the Gold Book throughout my academic research, both with respect to chemistry's relation to quantum physics, but also a lot with respect to the chemical bond that I've investigated. So I'm very excited. Currently, I should say, I'm working on a slightly different project in Athens, funded by the European Union, that has to do with chemical reactions. But I'm starting to switch, or at least I'm trying to broaden a little bit my philosophical investigations, and I'm starting to look a little bit into AI and how AI impacts chemistry and our idea of chemistry. So this is going to be also a sort of first pitch of the ideas that I have in mind and that I would like to investigate, hopefully in the near future. So I'm looking forward to comments and suggestions, or even if you have any ideas for future collaborations, it would be wonderful. Okay, so progress in science is a topic in philosophy of science that is very much talked about, and there is a huge literature about it. And this is because progress can mean many different things. So it can mean predicting new things that no one expected, like predicting the existence of new planets in the galaxy, or of elements, discovering things, again, discovering a planet, explaining or understanding phenomena that we didn't have a very good understanding before. Here, notice I'm separating explanation from understanding because one doesn't always imply the other, right? Or there are other things that we kind of regard as being a sign of progress, like achieving greater numerical accuracy in our experimental, in our observations, getting better measurements, or even, more heuristic things like, having technological innovations or applying what we've learned through science to things that have societal impact. Another very important aspect of progress is reaching truth. So science, for example, we say progresses because we've discovered something that is true about the world. And this is one of the most highly regarded features of scientific progress, but it is also one that is the hardest to attain, especially nowadays. So what is the traditional idea of progress? This is George Sarton. I don't know if you know him. He's a chemist. He was a chemist, rather, in the United States, and he's regarded the father of the history of science. So he defined progress. Well, he says progress has no definite and unquestionable meaning in other fields than the field of science. But what he says, and this kind of tracks down the traditional idea of progress. Progress has to do with, getting an accumulation of truth and being progressive. So he says the acquisition and systematization of positive knowledge are the only human activities which are truly cumulative and progressive, right? So this is the traditional cumulative view of scientific progress. So we have science which grows by doing errors, right? We get stuff wrong when we're practicing science, but the more we go on in time and discover things, the more our knowledge about the world grows. So here you see there is a sort of a continuity in the way that knowledge is grown, and there is an accumulation of truths. Now, unfortunately here, and what is very important to this cumulative idea of scientific progress is that the proper methods of inquiry, it is the methods that we use, is that they are what guarantee progress in science, right? The fact that we're using methods that are reliable is what gets us towards the truth and its accumulation. Now, this has started to be regarded as very problematic, especially since, the second half of the 20th century, where especially philosophers and historians of science noticed, well, that progress doesn't really go that way. There is not such a straightforward continuity in the way scientists accumulate knowledge. So there's no accumulation. Science is not always or completely a rational enterprise. There are certain epistemic values that figure in how we make certain scientific decisions. Also, observation and theory are not completely distinct from each other. It's not like we make an experiment, we make a specific measurement which directly confirms or disconfirms a theory. And so what we arrive at, I cannot go back, well, is towards new ideas of progress that try to accommodate these kind of discontinuities that are apparent in the history of science. So here, a very famous philosopher that usually is one of the favorites when I talk to scientists, that's the person they reference, Sir Karl Popper, philosopher of science who worked at the LSE. So he says, on the one hand, progress indeed has to do with truth, but it has to do with a progress towards truth, right? So what we are doing is we approximate. Science is trying to continuously reach or approximate truth. And how does it do that? Well, by producing new predictions. For him, a novel predictive power was a very important aspect and sign of scientific progress. So the fact that a new theory would not only accommodate previously known fact, but will also make risky predictions and bring unexpected empirical results was a sign of progress. Then, I don't know if you might know him, Thomas Kuhn, another very influential figure. His book is the most sold out book in the history and philosophy of science, The Structure of Scientific Revolutions. So he had a much more radical idea of what progress means. He said that actually progress is not so much occupied with getting towards truth or accumulating knowledge claims, but rather it has to do with problem solving. And this is because each scientific period works under a specific paradigm. That's how he called it. And so we cannot really compare different periods in which a different paradigm was at work. So rather within each framework, what scientists do and the way that they progress is essentially by solving problems. So here we have a very explicit detachment of the idea of progress from the idea of reaching truth. Now, a more recent philosopher of science, Alexander Bird, who's a professor at the University of Cambridge, kind of tries to bring us back to the traditional notion of scientific progress, where he says, well, it has to do with the accumulation of truth again, but it has to be justified, that truth. It's not enough to have, a set of true beliefs about the world. We have to have good justifications about them. Now, why am I mentioning all this? Well, I'll tell you later why I'm mentioning this. A classic example, an exemplar of progress in science, is a periodic table. So Dmitry Mendeleev, when he introduced, or rather when he proposed his own classification, I don't know if you know the history behind this, he wasn't the only one who had proposed the classification of chemical elements. There were at least two other proposals by Myers and Newlands. And there was, for a time, there was a debate about which classification should be adopted by the chemical community. And here we see this was an interesting instance of how values figured in the debate about which classification should be chosen, because Mendeleev said, my classification is good because it's more complete. It includes more of the known elements that we've discovered so far. And Newlands and Myers said that, my classification is good because it's based on a simple numerical relation regarding the atomic weights of elements, whereas Newlands said that simplicity, that mine included only elements for which we have very accurate observations of the atomic weights, measurements of the atomic weights, right? So here we had a debate about which value we should adhere to. And what won at the end was neither of these three considerations. It was the fact that Mendeleev's table predicted with very good accuracy which elements we should discover, right? So it was the predictive power of Mendeleev's periodic table that that won over the rest of the tables. And this is what philosophers often invoke in order to show that predictive power is one of the strongest signs of scientific progress. So here I have a quote by a philosopher, Peter Lipton, who says, when Mendeleev produced a theory of the periodic table that accounted for all 60 known elements, the scientific community was only mildly impressed. When he went on to use his theory to predict the existence of two unknown elements that were then independently detected, the Royal Society awarded him its Davy Medal. 60 accommodations of chemical elements paled next to two predictions. So predictive power has been very important. So this is a little bit of a short, very, very short story of how scientific progress has been construed so far and how it also has been construed with respect to chemistry. What about AI? There are, especially in popular science articles, there are like exclamations that AI is going to revolutionize science. It's going to revolutionize chemistry. We're not going to recognize how chemical practice is going to, be done in a few years because of AI. So do we have good grounds to believe that? Indeed, it seems that it contributes to certain things that, as I said before, are signs of progress. So some of the achievements of AI, we can discover new chemical elements. We predict chemical and physical properties of matter. We optimize reaction conditions, predict novel reaction pathways, or we realize complex quantum calculations for chemical purposes. So these are some of the achievements of AI, which on the face of them seem to match with our traditional notions of progress. But is this truly progress? Well, there are certain special problems with AI that seem to, if not undermine this, make it a little bit harder to argue for this. So first we have the problem of opacity. The problem of opacity is the following. So I'm going to read out the quote because it's going to explain it much more eloquently than I would. So Facchini and Termine say that that an AI system is opaque means that it is difficult for users to know how it works, as well as to interpret its decisions at various levels and evaluate its behavior against scientific and ethical norms. Now, in philosophy of science, there is philosophers are starting to think about AI, and there is some growing literature about this. In this particular paper, what they're trying to do is also distinguish between different senses of opacity. So they distinguish between so-called access opacity that has to do, with the opacity of the learning sample, the sample that we use in order for the AI algorithm to learn how to make predictions of the training engine and of the learned model. But also we have link opacity, which occurs when a system that is used to model a given target phenomenon conveys inadequate information about the elements that are relevant for explaining, predicting, and controlling such a target phenomenon. So we have different levels of opacity. And this problem does seem to undermine at least some ideas we have about scientific and chemical progress. So take, for example, Alexander Bird's idea of progress that I mentioned before. So he said that for progress to occur, it's not just that we need to grow the set of true beliefs that we have. We need these beliefs to be backed up by sufficient and good justifications. This doesn't really seem to be the case here, because we don't know how the AI algorithms have produced the predictions that they have. We know empirically after testing them that, some of these predictions do work out, but we don't know how this has been achieved, right? So this is one way in which at least one idea of progress has been undermined. Another idea of progress, which I believe has also been undermined, and which is an important one, is Popper's idea of progress. Because here, and this, I suppose I need to bring a little bit more context. So for Popper, it's very important for science that it is falsifiable, right? So what he said is that science is distinguished by pseudoscience by the fact that if I bring some empirical data that seem to undermine a scientific hypothesis, that then I have to reject the scientific hypothesis. But how can you do that in the case of AI, when AI might predict things, or we know does also predict things that are physically impossible? So strictly speaking, AI models sometimes falsify the underlying beliefs that we use in order to develop those models. So how do we kind of, how can we accommodate these two facts about scientific practice is not very clear. Now, another problem, and here I'm going to go a little bit to what Jeremy also mentioned about models. AI and the AI algorithms are forms of scientific models that we currently use. Very, very smart models and very complex ones, but models nevertheless. And there are two problems with models. The one is that, strictly speaking, we know that they are false, right? So we make approximations and idealization and assumptions that we know are not true when we develop specific models. The second problem is that, models are often inconsistent with each other. And this is a problem because, first of all, we don't know how to accommodate this fact with the idea that progress is associated with the accumulation of truth. So how do we reach truth through things and models that are strictly speaking false? Doesn't really matter. This is a little bit of a contradiction in some sense. Or to put it the way I've written it here, if models also are mutually inconsistent, but also false, then they cannot be all approximately true, nor can they all be explanatory the same way. One of them has to be wrong about something, right? So there are different options here that have been proposed in philosophy. I'm presenting three of them. The first one is the idea of perspectival realism. So the idea that, each model gives you an incomplete image of the world through a different window. That's usually the metaphor that philosophers use. So each model is a window towards the world, a different one, a different perspective towards it. So it highlights some aspects that are true of the world, but not all of them. And this kind of resolves the apparent inconsistency between the models because each one highlights a different aspect of reality, right? A different aspect, but overall each window is an incomplete image of the world. The second option is to say, well, we cannot have expectations as far as a truth is concerned when we are working with models, because we know that by definition, models are false. So we shouldn't even be raising that question or have such sort of, expectations by models. The third option is that, models are helpful because even though they are strictly speaking false, they can help us detect causal patterns, that exist with respect to certain phenomena. But again, here, what is interesting is that all the work in detecting those patterns and seeing how they connect to the truth has to be done by the scientists. So the model has certain epistemic limitations. And this is nicely also put by Gross, who says that machine learning can be tightly integrated with other more traditional research methods, and in a clear sense can contribute to insight into the causal processes underlying phenomena of interest. So this is the third idea that is now starting to being developed with respect to machine learning models. They have the ability to help us detect certain patterns about the world, but they cannot do that work by themselves. It is the scientist who has to take over with more traditional research methods in order to uncover it. Now, apart from truth, there are also other virtues that are very important in scientific practice. Here we have prediction, explanation, and understanding. How does AI fare with respect to these virtues? Well, there are at least two options here. We can be instrumentalists about AI and say that, AI models, each one serves different values differently, and that is okay. The second one, and this has mostly to do with resolving the problem of opacity, now scientists are trying to develop what they call explainable AI. So models that will untackle or resolve the opacity that exists behind, the way that AI models work. But certain philosophers of science have been a little bit skeptical about this, because even if so-called explainable AI were to resolve the problem of opacity, it would only give us an explanation of how the machine, to put it crudely, works. It wouldn't really give us an explanation of how the world works according to the machine, right? So even that is not entirely clear that it will resolve all the problems that we have with the problem of opacity. So as Bogue also says in a recent paper, we may arrive at a result where AI allows many discoveries, but scientists will have a hard time understanding those discoveries, right? Which is, I think, fascinating. So concluding remarks, do I have time? Am I okay? Good. So going back to the idea of AI, especially in popular culture and in the representation of AI through pictures, you see sometimes it's represented as a person, the AI models. There is this underlying idea that AI is a new form of rational agent. A thinking being, intelligent being that can do the same stuff that we can do as scientists. And I think this is misplaced, or at least it is too soon to have such an understanding of AI models. So here I think it's important to distinguish between two perceptions of AI, either as an instrument or an agent. And there is literature in the philosophy of science that views models, and therefore also perhaps AI models, as merely instruments. So, for example, philosopher Margaret Morrison argues that certain computer simulations could be construed as just experimental measurements. So the computer functions, she says, as the apparatus, and the act of running the simulation is regarded as a numerical experiment that just produces certain kind of data. So models should be seen as measuring instruments in the same way that instruments in the laboratory are viewed like that. And maybe this is also the same with AI models, right? So here, if you think about it, we have a controlled environment where we set and vary initial conditions or values of parameters for the algorithm to work. The computer and the program stands as the apparatus, and the simulation model is the target that is under investigation, which in turn we take to represent, at least with some respects, to a physical system that exists out there in the world. So maybe this is a much less problematic way of viewing, AI and AI models. I'm not going to, it's too long. And I think also, and this idea has been has been expressed before, not with respect to AI, but with respect to how science works and uses its observations. So a famous philosopher, American Charles Peirce, said a long time ago, like 50, 60 years ago, that science advances in leaps. The impulse for each leap is either some new observational resource or some novel way of reasoning about the observations. Such novel way of reasoning might perhaps be considered as a new observational means, since it draws attention to relations between facts which would previously have been passed by unperceived. And I think that's the right way of thinking about AI models as well. It's just a new, but it is a new observational means which helps us detect patterns which cognitively we were unable to detect by ourselves before, right? Now, this is a much better way, in my opinion, to think of AI models and simulations, because if we think of them as an instrument, then the problems associated with it, especially with respect to chemical progress, the problem of opacity, how we know with respect to truth, then they're not particularly surprising. There are problems we have faced and philosophers have tried to untangle with respect to models for a very long time now, right? And also, the second thing is, now, the contribution of AI to progress, however we construe progress, is much more modest as well. It is not particularly revolutionary how AI contributes to progress. It contributes the same way that other very important and revolutionary instruments and measurements have done so in the past as well. And an example, the Hasok-Jang, for example, explained how the thermometer contributed to chemical progress a few centuries ago. So the same way we can construe AI models as well. Of course, this is not the traditional way of viewing AI models because they are viewed as rational agents, or at least in the popular culture they are. And this is a problem because if we view them as a rational agent, then they have to be held under much higher standards, specifically the same standards that scientists are adhere to and are held to. And I'll give you an example. Scientists, one of the things that they have to achieve in order to say that, they have produced meaningful work is understanding of the phenomena that they are working on. So should we expect AI models to achieve understanding as well? But apart from understanding in these kind of epistemic capacities as well, we also need to assign ethical considerations and obligations to these agents, as much as the same way as we have ethical obligations towards the science that we are doing. But indeed, if we view AI as a rational agent, then it is true that the progress, that its contribution to progress would be immense. Now, some thoughts on progress, and this is where I'm going to conclude. I think it's very important in this discussion, both with respect to models in general, but also with respect to AI, to do a detailed conceptual analysis of what we mean by progress in science, because different goals come into modeling and simulations, and different goals also, they cannot always be met in a uniform way. So the sort of progress that we achieve every time by using a certain model is a different kind of progress. So it's important to distinguish between the different aims scientists have, because this can help us dissolve the apparent inconsistencies we view in scientific practice, especially with respect to inconsistent models, but also can help scientists specify what we are doing, what they are doing, and what they should do with the tools they use. And here, one last idea of progress by Otto Neurath, one of the logical positivists of the 20th century. So he says rather that, we cannot really give extra scientific standards of what it means to achieve scientific progress. Scientific progress and its standards for it are a result of the choices scientists make within a specific framework. And that's how he also gives the famous example of the ship. He says scientists are like sailors who have to rebuild their ship on the open sea without ever being able to dismantle it in dry dock and reconstruct it from the best components. So it is as we go and through the process of developing science that scientists themselves have the responsibility, but also the power to identify and determine how they achieve progress. And last one, I promise, that's how I finish. Bertrand Russell talks about progress in science. This is, I think, a very nice quote that pins down how important it is to have this discussion and this integration between science and philosophy. So he says, if therefore a scientific civilization is to be a good civilization, it is necessary that increase in knowledge should be accompanied by increase in wisdom. I mean by wisdom a right conception of the ends of life. This is something which science itself does not provide. Increase of science by itself, therefore, is not enough to guarantee any genuine progress, though it provides one of the ingredients which progress requires. So science is essential to identifying and achieving progress, but we also need to have the discussion of what we mean by progress and how we choose to achieve it in each particular context. Thank you very much.
Thank you very much, Vanessa. I think that's just a wonderful introduction to the ideas. You know, we're all currently, when we sell our grants, we say, we, in particular our context, data to feed into AI. Yes. What for and why? And what is the progress? And what are we doing here? And I mean, I like it, you talk to people, when people started complaining about these large language models hallucinating, I thought, so what's the difference between the discussion I have in the tea room with my colleagues? Former colleague Martin Fleischmann, you might know, have had some interesting ideas, but if you could tell the difference between the really brilliant ones and the ones that might be hallucinating, you would have got several Nobel Prizes. This is what we do, right? This is the exciting part, but you've really wonderfully set the context here for what we're trying to do. We have some time before in the probe for some questions, but obviously questions will come later. Anybody, some immediate questions?
Thank you very much, Vanessa. You started with the word truth.
Yes.
Now I would like to ask a philosopher, what is truth?
Yes. Okay. So there are different notions of truth. The traditional one is correspondence to reality, right? So we assume that there is a world that exists independently of us, and it exists also independently of how we perceive it. So our propositions are true in the sense that what it says corresponds to facts about the world. That's a traditional view of truth. Then we have other views that have mostly to do with systems of true propositions. So some philosophers believe that, you know, we don't have enough evidence that there is a world outside of us for which our propositions correspond to, but rather we build systems of knowledge, and what makes them true is that they cohere with each other. Different. It's a huge topic, what truth means. But these, in a nutshell, are the two views. It's the traditional one. Yes, I'm what they call a scientific realist. So I believe that there is a world outside of us that would exist even if we weren't here, and that, you know, we are trying to capture with the way we describe it.
That's really interesting to raise that, and in the context very specific, some things we've discussed, truth and trust, trustworthiness comes together and is really, really important. Tammy.
Thanks for a really interesting talk. So as our use of AI, LLMs, machine learning continues to exponentially increase, what are your biggest ethical concerns about this? As you mentioned, the ethical side of things.
Could you? I missed half of the question. So the ethical concerns with respect.
Yeah, the ethical concerns about our sort of increasing use of AI, LLMs, machine learning.
So I mostly put this because I read recently an article about an AI model that was used where the people who had developed it were invited to a conference, and just as a game, they changed a couple of parameters. So they changed the toxicity parameter, I think, that was assumed in an AI algorithm, and it produced substances that could have been used for chemical weapons that they hadn't known before. And they never published the results of that. I think they just, I don't know even if they went, but they never published the results of that. And so this is an ethical concern. How you handle information, because AI produces such a large amount of information, and you don't have control of how this information could be used, of its capacity, right? It just spits out stuff. And so you have a larger ethical consideration here on how you're going to handle those results. And I think it's also very important here that these are stuff that are not so much developed in the public sphere by public universities. It's private companies now that are doing all this work. And I don't know sort of constraints or rules have to be imposed in order to control the results of AI models. So these are some issues.
Hi, thanks very much for a really interesting talk. I'm thinking about definition of progress that you gave around problem solving, rather than the others. And the thing that AI seems to do really quite well is problem solving.
Yeah.
And I'm not thinking of large language models. I'm thinking about data interpretation, things like that. But another thing you said was we have to kind of live with contradictions that different models give you different. We're used to that, and that's really good. I think if we look at the machine learning and the AI as giving a probabilistic answer, it's probably right, but very often right. But we think of it in the context that sometimes it'll be wrong, and we do some probability theory on that. I think it takes away a lot of the worries.
It does.
So I think we have to, like we do in lots of other things, we apply probability theory to the results and just accept that sometimes they'll be wrong. If we have the AI driving a car and it sometimes has a crash, well, humans sometimes crash too. If it can crash less than humans, then I'm fine with it.
Yeah, no, I absolutely agree with you. I should have written it down in one of the slides. So the Kuhnian idea of progress as problem solving fares just fine with AI. And if you take into account, as you rightly say, that this probabilistic reading of the results, then you don't even have inconsistencies because the probability dissipates the inconsistencies. But the problem is that then you have a little bit of you lose this this higher expectation or higher value you used to assign to scientific practice, that it's not just useful, it also does something more noble. It reaches, uncovers truths about the world. If you want that, then this is a problem.
I think.
Yes.
I think, Juan, you're being an engineer here, scientist. You see that. But any other questions? Eva.
Thank you. What a fantastic description of the evolution of thought, innovation, progress. I was wondering, throughout your readings, is also an evolution on risk taking?
I'm sorry?
Risk.
Risk.
How bold ideas are.
How bold are these? I know, I haven't thought about this. Risk taking in scientific practice or in scientific theorizing?
Ideas.
In ideas.
Give you a little context.
Yes. So, okay. That's interesting. Usually, so at least according to Kuhn, risk-taking usually happens when there's a lot of trouble in science. So during periods where there were large problems with the theories that were accepted. So, for example, with the Ptolemaic system of astronomy, right? It was so problematic to try and uncover how the planets are positioned based on the Ptolemaic system, that it raised a lot of disputes, and this also generated a lot of different ideas, which we would regard as risky. But during what Kuhn calls the normal science, when we don't have particular controversies, then risk-taking is not so common. So it depends which period you are, but also which discipline. Right, so some fields of science are more problematic nowadays than others.
I think that's really interesting because when I would talk about this, sometimes you take a risk in publishing your work because it's not accepted by the community, and sometimes there are very good reasons why it's not accepted, but quite frequently it's not, and it's just state opinions and people don't like it if you question them. But that isn't what scientists by the general public are perceived as, perceived to have been more open. And actually, we're all still just normal people, and we don't like it if somebody tells us we're wrong. But we have to get more into the attitude that airline pilots are supposed to have of, the near misses should be reported, and it's important to report it, and it's not held against you.
Yeah.
It's held a positive thing that you're questioning something. Nonetheless, that is still difficult. I think that's a very interesting area to bring up.
So I think if you want to read more about this, Thomas Kuhn's book captures perfectly how this happens. He actually says that during normal science period, it's very hard to publish stuff that are controversial because everyone expects that you only solve, problems, quantitative problems and nothing else. So yeah, I recommend us both for this.
Yeah, I love the question. I'm also thinking of funders. So funders have a huge role in either encouraging risk-taking or innovation, we can use different terms, or discouraging it quite strongly.
Yeah. No, and this is a problem not only for scientific fundings, for philosophical ones as well. The things that I've said I'm going to change in philosophy in order to get funding, that we're going to revolutionize somehow the world through philosophy, it's ridiculous. But that's the things that are expected by funding bodies for some reason.
Some of us push within the strategic advisory teams that this is an area. And actually, the UKRI, I think it's at that level, has a meta-science program coming in now, which has not been widely publicized. I mean, it's all there, but somehow we didn't notice it. And there's been quite a lot of opportunities in this. And I think it is trying to address why we do certain things. I think that's, I don't care if you know more about this program, but it is a UKRI program, moderately well funded with some fellowships. It's, I think, given this room, maybe the ideal people to be applying this. One last quick question.
I just want to come back to the hallucinations, because there's obviously differences in hallucinations and different kinds of AI models. So large language models, hallucinations, we don't really know where they're coming from. But I think a lot of machine learning AI applications these days, we do know what we put into them. So in theory, at least, we can then go back and develop higher level understanding. And so I think there are probably distinctions between AI models. And I think a lot of the models are useful because they make predictions that we can then test against reality, whether it's an instrument or an agent. And sometimes that's the only thing we care about. But then obviously the higher level understanding, wisdom comes from understanding what the physical constraints are in the model that we don't immediately see.
Yes, no, I agree. And I think that the better the AI models are going to become, the more difficult it's going to argue that they are just because their capacities are going to be. Yeah, but there's a lot of work to be done. This is a very niche topic for very few papers that are being. It's only now starting to grow, and you know, it takes some time for us to get our heads around all these advances and how they take place. So yeah.
Time factor, isn't it?
Yes, you need to give us some time.
Well, I think also that we need to engage these things as practitioners, and we need to understand that it's useful for us to. The example you gave of the chemical weapons, it's Sean Elkins. The community does feel that he rather over-egged it, because to give you an example, if you have unfortunate enough to have a chest operation, be treated with a derivative that comes from curare, what the South American indigenous population used to paralyze their prey, because you can't be breathing, moving if someone operates on you. They paralyze those muscles and you're. Well, there is a classic example of the drug versus weapon. This is a problem that chemistry. The difference is that bad actors may have more access to the AI tools, but they still have to make the chemistry. I think the synthetic biologists have far more to worry about than we do in chemistry. Not that we should ignore it, but unfortunately, the insurers of our university start asking the questions about how much dual use we've got. The dual use problem is one comes up here, and the answer strictly to what we were sent is all of chemistry is dual use. I think all of science is dual. So these are really important problems to address, because when it comes to the insurance company, the economists are in play here. This is very serious, and we need answers to this. But I hope this has really been wonderful at setting the scene for the environment in which we are doing all this data, all these standards. Thank you again for a really wonderful talk.
Thank you so much. It was such a
A while ago, actually about a year or so ago, I was at the International Data Week in Salzburg. We had a session that the Drum group had put together, and we had a colleague, Wright, talk to us about some new inventions in metrology. I think most scientists consider new inventions for metrology come from making better measurements, but actually it's better understanding of measurements is important, and better conveying of those measurements. And I heard about this M layer, and I thought, oh, this sounds really interesting. So when coming to this meeting, I discovered that the person behind it all is Blair Hall, who's going to be talking next. And I really have to thank Blair, because being willing to come from New Zealand, was already in Europe, and I said, well, would you mind coming to the meeting? He said, it's a lot to go back and forward again. So we were even luckier that Blair agreed to come and stay with us in Southampton. And I can tell you, he's convinced all of the colleagues in PSDI that he's talked to that this is going to be a really important thing to discover and use. And I think this really follows on brilliantly from Vanessa's talk about the stuff that we don't know we know, and stuff we know we don't know, and so on. And I think this is really at the heart of the provenance and issues and conveying that and conveying data information. I'll let Blair introduce himself. Thank you very much for coming all the way today.
You make it? Yeah. Thanks. That's my controller. Thank you, Jeremy. Thank you for inviting me, but more so, thank you for all the heavy lifting involved in allowing me to be here. And it's been a pleasure for me to be with your colleagues in Southampton for the past couple of weeks, and a couple of them are here today. So it's all been great. So thank you very much. And I'm really thrilled to be here. When I got Jeremy's invitation to begin with, I thought, oh, if only I could go. And he made it happen. So fantastic. So I'm going to, the topic that I need to talk to you about today, it's not complicated, it's simple. So if I don't succeed in explaining it to you, it's probably my fault as a poor pedagogue. But there is, I will perhaps have an excuse because of tacit assumptions that you may well have. And so that's really where the, yes. So I like to refer to Donald Rumsfeld's famous quote there about things we know that we know, things that we know that we don't know, things we don't know that we don't know. That always amused me. And those are the three things that if you're a metrologist, I'm afraid there aren't many of us here, but if you're a metrologist, we really worry about those things, particularly the known unknowns. But it occurred to me that for the talk today, we have the other combination. We have the unknown knowns, the things that we know so instinctively that they just pop out and we don't really think that we know them. So we interpret symbols. Tacit knowledge allows us to interpret symbols without a second thought. And units are a bit like that. Scientists learn about their units very, very early on. I suppose I've known about units for 50 odd years. And you build up your own personalized working understanding of units. So once again, can anybody read ASCII? Those are ASCII codes. I mean, some of you are data scientists, you might. 20 is just a space, so you can see it's going to be indented to the left. Those are what the characters correspond to, so that's the presentation of the ASCII code. But do you understand what that's for? Well, if you see this, then I think you do. I think then the context of that information is clear to you. It's a milestone, it's on the side of the road, it's in front somewhere, there are cyclists who are powering up and down the hills, and this is information that they can use to navigate. And so the context is important, and the context sets in place the sort of thought process that we're going to use to analyze the symbols. We respond to symbols in a particular way. They trigger our thoughts, and the meaning that we take from them is based on some sort of shared experience. And that, of course, is, I think, the triangle on the right must be familiar to many of you. Published in a book on semantics from the early 20th century. And on the bottom left, we have the symbol. On the bottom right, you have the thing you want to refer to, but you can't go straight from one to the other. You've got to go through the summit of the triangle, some sort of thought, in order to understand what you're referring to. Now I've got one more photo to show you. I think it's a doozy, but it may fall flat on this audience. It's best suited to a metrology audience. I was visiting NPL a few weeks ago. Of course, as Richard has explained, NPL is the United Kingdom's metrology, National Metrology Institute. They are the source of time, for example, in the United Kingdom. So I'm walking along the road a few hundred meters from NPL. I'm thinking metrology. I'm looking forward to the discussions that I'm going to have. And I look up and I see this sign. It's just a couple of hundred meters from the entrance to NPL. I'm completely bamboozled. Does anybody just understand what this means? Hospital, yeah. So because I'm thinking metrology and because UTC is the acronym for Universal Coordinated Time that the metrologists look after, and not 24 hours, I'm thinking, huh? And the H, it just didn't really, it's big, but I just thought, oh, they use H for something, perhaps it's ours. I didn't understand it. Okay, so when you travel, you're confronted more often by these situations where your tacit knowledge doesn't quite fit. It's quite an interesting experience. Okay, now on to SI units. So, and this may be alarming, please don't get alarmed, don't get angry with me, just try and soak it up. Units are redundant if we know what the scale that we're working with. It struck me years ago when there were people renovating my house that they didn't need units. They would just, the workmen of different trades would just share information as pure numbers because they knew exactly the context. I couldn't figure out what they were talking about, but they knew what they were doing. Calculating is the same. When you do a calculation, the units are gone. You're using numbers in the actual calculation. But units help us when we want to share data with other people, especially if we think they may be using different scales. Units are needed to convert data between scales of measurement. So what do they provide? Well, the format we use is a number and a unit symbol. So please, unit symbol is just IN for the moment. It's just some text. It indicates the size of scale divisions that we're dealing with. Doesn't indicate the kind of quantity, not necessarily a length. Doesn't relate to metrological traceability, which is probably not a concern for you people. It facilitates the conversion by identifying a physical reference with the same scaling behavior as the quantity that's being expressed. So whatever it is that's being expressed, I don't know, but I know that it's going to behave as inches do if I want to change the units. So how does that work? Well, to convert to a different scale, we take IN as a numeric variable and we replace it with the numerical measure in the required scale, and then we calculate the product. So the measure of 1 inch in centimeters is 2.54. So to convert 1.23 inches, I would multiply by 2.54. Straightforward. So the system that we have is a system of producers and consumers of data. The producer reports a symbol that refers to the scaling behavior of the thing that they were using when they generated the data. The consumer may need to work in a different scale, and the obligation is on them to transform the data. This is repetitive work and subject to error. And everybody is writing unit conversion software. So this is the way it works. This is what we got from the 19th century. Fourier and then Maxwell introduced these ideas, which are now firmly embedded in our SI units. So it's also an idea that popped into my head in Southampton. It's curious, isn't it, that such important works as Fourier and Maxwell's books at the time worried about unit conversion. Would similarly important works now be burdened with that? I don't think so. So at the time, it was important to make sure that calculation was done by hand. It was important to make sure that it could be done effectively, efficiently, without too much error. So there's this notation to express a quantity in abstract terms. We have the value, the curly brackets Q, and we have the dimension, square brackets Q. When we express something concretely, we replace the curly bracket with the number and the square bracket with the unit symbol. So the conversion factor that we looked at before, inches to centimeters, is the ratio of the initial unit, which is part of the information that we're given, to the desired unit. Before we know the initial unit, we're dealing with a dimension. So that represents just an unspecified conversion factor, a numeric variable. Once assigned, it becomes a unit. It's a form of metadata. So Maxwell gave us an early example of metadata. So when we come to a product, for example, Q equals R times S, we can expand that in terms of their notation, but we can manipulate those terms as we would ordinary numeric variables. Arithmetic applies to them. They're all just numbers. And so you can obtain the dimension of the product as the product of the dimensions of the factors. So Maxwell's system suggested that with a judicious choice of base units, we could efficiently obtain conversion factors for all the different quantities that would be needed. So the Maxwellian system is a very pragmatic, efficient way of dealing with computations. The choice of dimensions is really an arbitrary thing. So it's a judicious choice, but there are alternatives. And so we really have what I would prefer to say system dimensions, the choice that has been made. And when you've done that, so mass, length, time, and so on, different quantities may end up with the same dimensional expression. And so we now understand what that means. It just means they have the same conversion factors. So what can we do with unit systems? Concrete quantity can be expressed in one unit and later converted to another. And we can do this without loss of information that may be depicted in the data, right? Because the data is somehow representing something, empirical observations, what we want to study. Knowledge about the kind of quantity is not contained in the statement. System dimensions describe the scaling behavior. And that's why dimensionless quantities, of which there are so many, is not a quantity kind in itself. It's just telling you these quantities are invariant under changes of units. We end up with situations where alternative scales belonging to a particular, so the alternative scales that we may have in a system will all have the same zero, and this sort of defines them as a group. The inclusion of degrees Celsius is the odd one out, and this is what Richard's predecessor was a bit mad about. So systematic units and units with special names. There's always going to be a name, compound name for an SI unit that can be expressed as a product of powers of the base units. And that seems to be such an important thing, I'd like to give it a name. It's just me, but I like to call them systematic. And so these systematic unit names correspond, they're mnemonics for the dimensional expression that quantity has. But the SI also defines 22 special unit symbols, special units. Each is associated with a particular quantity kind. So these have been introduced to try and patch up the SI's inability to identify quantity kinds. And so you can use Hertz to refer to a frequency. You can use Becquerel to refer to an activity, but you can't mix them up. So you can't take data in becquerel and express it in hertz. That's supposed to disambiguate a few things. But the trouble is they can also be used in compound units, and then you get back to the ambiguity problem. So each of these special units has a systematic equivalent. So Gray and Seifert, both meters squared per second squared, hertz and becquerel per second, joules and Newton meters, kilogram meters squared per second squared. So what can't we do with unit systems? Why do we need to do a bit better? Well, one of the assumptions, if we leave aside degrees Celsius, is that conversion between one unit and another is just a multiplication. And that's a restrictive assumption. And that's, so you will have more to say about that soon. And the other problem is there's no reliable mechanism to identify the kind of quantity if you're just given the unit name or symbol. And so that's what we've got with SI units. That's what Maxwell gave us. And I'm not sure that he really intended anything else. So now the M layer. The idea is that we can do a little bit more for the consumer. So remember, producer generates some information and they would like to present it in a way that the consumer can use in any of the formats that they, they desire. So if we introduce an intermediary here, which we're calling the M layer, if the producer can identify the form of expression that they're using clearly with respect to this M layer, then the consumer who may wish to use different formats can ask the M layer, is this a legitimate alternative format for this data? And if it is, the M layer will oblige and help with that transformation. So why? Why do we think this is important? We think we need to unambiguously identify the scale on which data is expressed. And this is a bit of a generalization of units. And we need to enable transformations into other valid forms of expression without distorting or losing information that's depicted in the data. So what will the M layer do? It associates pairs of identifiers with data. These will allow data to be transformed into other legitimate forms of expression. It will distinguish between legitimate transforms that won't distort the data and those that might, necessarily will, but might. So some of the ideas. So now we've got these two identifiers, scale, something that I'm going to call aspect. But thinking about scales to begin with, there was a huge debate in the 20th century about whether physical scientists had a monopoly on measurement. So it was a very strong lobby from the physicists. And Stanley Stevens contributed to that by showing that there are in fact categories of scales in which you can express data and represent on those scales what it is that the qualities of the data, which may not be as of high quality as a physicist would use, nevertheless have some properties that correspond to empirical relations. So quantities, especially quantities in physics, are the sort of elite group. It's an abstract idea. We can create physical models of systems. We can do quantity calculus with them. And so a lot of the literature on quantities and units is making this assumption that we use physics quantities. But a lot of engineering data doesn't qualify. Material properties are often measured in a way that's very, very standardized in order to control aspects of the measurement so that data can be compared. So if you use a standardized method, you can compare data, but you can report viscosity in SI units, but if you've used a different method, they're not comparable. Similarly, method-defined measurements, and I think chemistry might be full of this, moisture content of soil, octane rating, but also the temperature scale, which is very commonly used at the moment, and measurement measured properties in the social sciences. So all of these things, we want to try and accommodate them somehow. So the M layer, what does it look like? Well, it's instead of a doublet, number in a unit, it's a triplet. So we have, in order to express 70 as the mass in kilograms on a ratio scale, we're going to have something that identifies mass and identifies our scale with the unit kilogram and this thing ratio scale. So there are really three things here now. Our schema. And if you imagine what this would look like in XML, it's just going to be a couple of extra tags associated with the data. It's really just a simple markup. Now, if you have data which has been labeled with the M layer, and you want to know if you can express it in a different form, you simply query the M layer saying, I have temperature data in Fahrenheit on an interval scale. I'd like it in temperature Kelvin on a ratio scale. Is this possible? If it is, the M layer will give you an expression that you can use to evaluate that, and you can make the conversion. So, understanding more about scales. Now, I have the greatest respect for Antonio Guterres, and it's not fair for me to nitpick about his use of units. The rhetorical effect of this is far outweighs the, but anyway, he was wrong, right? So billions of people are facing an extreme heat epidemic, wilting under increasingly deadly heat waves, with temperatures topping 50 degrees Celsius, halfway to boiling. You can't say that. It's halfway from freezing to boiling, and that would have been okay. I forgive him. So in quantity calculus, so going back to this physicist elite view of the world, sum of difference of is only allowed between quantities of the same kind, and then the result is of the same kind. But when transforming expressions of temperature, we need to know whether we're dealing with an absolute temperature or a temperature difference. There are different formulae involved. So this is why Richard's predecessor got mad with me. Pointed that out. So there are these different types of scale. So measurement typically assigns numbers to certain aspects of objects or events, and there's a scale type associated with a group of transformations that you could apply to the numbers on the scale that would leave the empirical information there intact. So the scale form is said to be invariant if empirical information is preserved. There's a supposed isomorphism between numbers and actual things that are going on. So the M layer is identifying different formal scale structures and also the legitimate transformations. Now, there's been quite a lot of angst about Stevens' scales in the literature. The M layer is not trying to be prescriptive or proscriptive. We're not trying to tell anyone what they can do. It's just descriptive. We're saying this is what was given to us. This is what makes sense to do with it. So there was a hierarchy of 4 scales in Stevens' original idea: a nominal scale, which is a measurement which simply assigns to categories; ordinal scale, where you can actually order the property in terms of increasing or decreasing. So, for example, gold is better than silver. Interval, where the equality of intervals or differences is meaningful, but not ratios. So this is where temperature in degrees C comes in. And the transformations that preserve the properties of those scales are linear transformations. And then ratio scales, where you really can talk about halfway to boiling. Those are the sorts of scales that most of the SI is made up of, and we just we can transform those by multiplying by a constant. So here are the invariance transforms: the ratio, interval. Bounded interval is what you get with angles when you say we can only go between minus 180 degrees and 180, something like that. So circularly wraps onto itself. So Stevens didn't have that one, but we think it's important. Ordinal and nominal. Those are the scales. The aspect. The aspect is generalizing this idea of quantity kind. Sometimes quantity kind is fine. What we're looking for is the most general aspect, measurable property of what we're looking at that would be needed to uniquely identify the expression format in combination with the scale. Our objective here is to disambiguate the different formats of data. So, for example, you don't know, if you're dealing with seconds to the -1, whether you've got an activity or a frequency, unless that comes in somewhere. So the aspect of frequency or activity would accompany seconds to the -1 on a ratio scale. The problems with degrees Celsius can be handled. Angle, a dimensionless quantity. We can identify that we're dealing with angle, and therefore we can say you can navigate amongst the alternatives for it. Now I mentioned earlier that most of our thermometers are calibrated to a scale called ITS 90. I'm not sure how many of you would know that. It's not temperature. So it's a very good approximation to temperature. It's a practical scale. It's defined by a number of physical fixed points and interpolations between them. And so our ability to measure thermodynamic temperature, the physical quantity, is getting much better. And so these two ways of calibrating instruments to measure temperature are going to encounter each other. And so we think that it's useful to have a way in which you can disambiguate the different situations. So here's a list of possibilities. We have temperature and temperature difference up here, delta T, but we would have temperature on ITS 90 and temperature difference. And there's another scale in 2000 at very low temperatures. So we would have all of these possibilities. And of course, in terms of Kelvin, you can have the other possibilities. So you can really identify your data much more finely. Dimensionless quantities. The SI recommends that if you have a ratio of two quantities of the same kind, that your notation reflect that. But so the M layer would probably define, or does define, ratios of that sort. So we would not say, oh, this is a dimensionless quantity. We'd say this is a length ratio, this is a voltage ratio, so on. So in this sense, the aspect is more specific than the physicist's idea of kind of quantity. But the nonlinear functions, for example, the logarithm of a ratio quantity, we go the other way. So there's an ISO standard called 80,000 in which many quantities are defined, and it says that quantities defined in different bases, logarithmic quantities in different bases, are proportional to each other but have different values and are considered different quantities. Well, the aspect for all of those logarithmic ratios with different bases, we would say is the same. There would be one aspect there, because the conversion is just exactly the same form as a ratio scale conversion. I don't know why they decided to do that. The zero remains the same. It's just a conversion factor. So our aspects here are more general than the conventional sense of quantity. So just to remind you again, we can define things, temperature difference on a ratio scale. We would need we would refer to the degrees Celsius as the unit. Angle, we can say this data is a bounded interval angle, and we can give the limits of the bound. Frequency, we can disambiguate between frequency and activity. And here, I left this one in because I want to retract this in front of this audience. this table came from an earlier publication before I really knew that the chemists had INSHI and things like that. So I was thinking, what can the M layer do? And I was saying, well, amount of substance is really parametrics. It's amount of substance of some elementary entity. And so I thought, well, maybe we could do that, but you've done it. So we're taking that off the menu. So the M layer, what the M layer does, it kind of creates relationships between these pairs of aspect and scale. So you get these graphs, relationships that show you that you can go from one to another. And you can do that without loss of information. Or you can do that if you really want to, but you may incur some potential risk. So that's the M layer very simply. It's just these two things, these two identifiers. We will have more information in the M layer. We will capture the structure of the formal unit systems like the SI. And this is what a UML diagram of that looks like. And this will enable us to do things to support people who want to do things like unit arithmetic, unit calculations, things like that, which are a bit fraught because of the interpretations that are put on. And of course, we distinguish between those scales on which that's legitimate to do unit arithmetic and those that it's not. So our interval scales, you will not be able to do legitimate transformations like that. So to sum it up, unit systems are best used by skilled people with their tacit knowledge. They're not really going to be easy to develop digital models for. And I think there are some existing ones out there, and I suspect that you agree with me that it's not working terribly well. The M layer is intended to generalize this idea of a Maxwellian unit system as I presented it to you, as something that's there to facilitate conversions by supporting this wider variety. So it's extending it on the basis of good metrology, good scientific ideas, the classifications of scales and things like that. It's extending the 19th century idea, but with the same broad purpose in mind. And the interesting thing that has, to me, which has come out of this, is that there are structures captured by this database that now refer to more fundamental notions that are often confused with the SI. So I made a point of saying system dimensions, because there is a notion of dimension, and that's a broader notion than the system, the SI idea. So you can have a dimension of angle, and you could say, well, what are all the ratio scales available to me for angle? But the SI won't give you that. So is an M layer available? Sort of. The M layer was an idea that I had with another person, Mark Custer, who chairs this Measurement Information Infrastructure Technical Committee within the National Conference of Standards Laboratories. It's a strange name because the I means international, but it starts with nationals. It evolved. Membership of the NCSLI is open to all, and we have developed a prototype which is already up there. It's far from perfect. We're trying to put in place a structure that will allow the M layer to grow, a governance structure, and a way in which people contribute, and a way in which it can be sustained going forward. Because obviously I've got quite a few white hairs. It needs to be more durable than my career. So that's where we are with that, and I'm looking forward to seeing what you think of these ideas.
Thank you very much indeed for explaining very coherently what are the issues and what we're trying to address. So open up to some questions. We have 5 minutes or so for questions. And the only one that I'm going to ban for the moment is any discussion of amount of substance in the mole, because that will take a lot more time to discuss.
Yeah, thanks. Really interesting ideas. And I think the underlying problem we're trying to solve is how to translate information from the left side of the equation, where we have the quantity symbol, and to which we often add labels and indices, which are then not transferred to the right side of the equation, where we have the numerical value and the unit. And I guess some of that is addressed by the special SI units that you mentioned, like Seifert or Gray or Hertz or so, which translates some of that meta information. Other people, including environmental sciences I work with, include chemical symbols on the right side of the unit, so they have like tons of carbon. And I guess the meta layer does another thing. So there's various ways of solving the problem of lack of meta information that we don't include on the unit side of the equation, but we do have on the quantity side. I'm just not sure whether the M layer will ever be sufficient, because there will always be people who want to have more meta information, whether it's what height the wind speed is measured at, or like I said, what chemical we're interested in. So I think it's another approach of solving this, but I'm not sure whether we efficient.
Yeah, so the M layer is not trying to solve all your problems. One of the challenges when you're when you're working with it, you're trying to decide whether something is an aspect or not, is whether it satisfies this requirement. Is it as general as possible in order to disambiguate the different forms of expression that it's going to have to serve? And so what tends to happen in your mind is that you go down a rabbit hole, which is more and more specific to the things that would have been on the right-hand side of your equation. So you start to think, oh, I need an aspect which, well, to give you an example that troubled me for a while, a ratio of lengths, we would say, yes, we want to know that we have a ratio of lengths. That could be a scale factor, but it could be an aspect ratio, in which the lengths are perpendicular to each other. Do I need to have an aspect for aspect ratio and for scale factor? And in that case, it goes on and on and on. So we're trying not to get trapped by that. The Maxwellian idea was to show how give enough information that the data could be expressed in different ways, but knowing what the data represented was never part of the deal. It's on the, as you said correctly, it's on the right-hand side of the equation. And this is the advice in the SI, is always, if you need to annotate, you put it on the symbols on the right-hand side. You define in the context of your scientific article what it is, this symbol that you're going to put on the right-hand side of your equation, exactly what it is. In the context of what we're doing in metrology now, and this relates also to the CNCSLI group, we have another project. So in metrology, there are all these services. You can build sort of a taxonomy of the sorts of, or a list of the sorts of measurements that people might want to have done by calibration laboratories. It's quite a long list. And so we want to have ways of identifying that unambiguously. And this is getting into the right-hand side problem. It's specifying far more closely what a certain measurement is going to be, what the service provided is going to be, what the measurand is. But the values, the magnitude of what we've measured, is a much more general thing. So the M layer will interact with this, they call it a taxonomy. And so we will know that the certain quantity has been measured, that aspect and scale will be there, and then people can then express that in other legitimate ways through using the M layer. Okay?
The beauty of the Westphalian system is that it's sort of a minimalist system, and especially if you just restrict yourself to the systematic units, by expanding it to some of the other information that you're including on the other side, on the left-hand side of the equation, it sort of makes it. I mean, you're saying you're developing some restrictions, some ways of avoiding going down the rabbit hole, and I'm just afraid that we might not have a limit, or I mean, there might be desires for people who are not limiting too much further.
Thank you, Blair. That was a fantastic talk, and it's really interesting problem you've identified. That, of course, were we to start constructing the SI today, we probably made different choices. So the SI is very much a result of historical, societal, cultural compromises, and in some way, what we're trying to do digitally is starting from scratch. And it's a bit of a question about, can we start from scratch, or do we have to match what is written down in documents like the SI brochure? And you made me check in the SI brochure what we'd written about Celsius, because I was a bit worried about that. And it says that unit degree Celsius is only coherent when expressing temperature differences. So that works, I think.
Yes, that would be a ratio scale. But there is a so-called quantity equation in the SI brochure, which I would say is not a quantity equation. It's actually wrong.
We'll have to talk about that later. So my specific question was, on one of your slides, you mentioned ITS 90, which is a way of realizing the definition of the Kelvin. You mentioned it both as a ratio quantity and an ordinal quantity. So you had a slide that I think had both. So under what conditions are you considering it a ordinal quantity?
So this is, it doesn't matter whether it's ITS 90 or thermodynamic temperature, it's the same applies. If you're going to use an interval scale to express it, so these are the scales where there's an arbitrary point is chosen. So you need two standards to define an interval scale. You need to define some arbitrary reference point and then some other arbitrary point, which will then determine the size of the divisions and give you a 0 or whatever. So in Kelvin, we have no problem, right? It's all ratio scales. But in degrees Celsius, whether it's thermodynamic temperature or ITS 90 temperature, we have an ambiguous situation. If I have 12 degrees Celsius, I don't know how many Kelvin it is until I have that extra information. So we have to be able to say we've got temperature difference, interval scale degrees Celsius, or temperature difference. Temperature difference, ratio scale degrees Celsius, temperature absolute, interval scale degrees Celsius. We have to be able to do that. Otherwise, we end up in a cul-de-sac at some point.
I wanted to just comment or relate to your slide on dimensionless ratios. We work in a data warehousing context, and we compute plenty of dimensionless ratios. And our data warehouse hates the fact that cannot attribute a unit of measure for those scenarios. And we found that there is an equivalent representation in many cases, which is alternative representation for dimensionless ratios, is to think of it as a change of unit of measure, introducing new units of measures, practically quantity captured by the denominator. Give you an example in the physical world, that would be the equivalent how physicists or astrologers when measuring the solar system, they do astronomical replacement. So if you divide everything with certain context with the same specific quantity, measured quantity, then you can then consider that quantity as a new unit of measure in unit of measure system. And within that scope, that's a totally valid measure. It doesn't lead to this void that data warehouse, but in general, people want to have a grasp of the quantity that number next to it represents.
Which would be a mistake.
Sorry? But in a way, I mean, what I saw in the M layer, this attempt to maintain some or reference to the original type or divided by meter per meter, in that attempt, not the association.
Yes, but I wouldn't say that. As I said, for example, with the inches, 1.23 inches, it could be a rainfall. The rainfall's not a length. So the appearance of the unit, and you know that it's a unit of length, I'm not disputing that, doesn't tell you what the expressed quantity is necessarily. It will often, but it can't be relied upon. And so I'm not sure, I mean, maybe we have to talk offline. I'm not quite sure that I understood the point you were making. You were saying dimensionless quantities, but then if you chose one of those quantities as a new unit, then somehow you didn't have dimensionless quantities. But dimensionless quantities are, of course, a ratio of two things. And a length, you could say, is choosing a length reference and dividing an unknown length by that. So it's not a ratio. It's not then a dimensionless quantity.
Thank you, Jeremy. Thank you very much, Blair. Of course, the Maxwell's unit system that you mentioned, we call it quantity calculus in the Green Book, and there is a chapter on this entirely dedicated to it. Now, what I feel the biggest problem in approaching this topic to the outside world, not to specialists, so to students, for instance, is to teach them that you can divide by unit, as you just mentioned. And so we actually, when we use a quantity, a physical quantity or a chemical quantity in a computer, take the quantity and divide it by the appropriate unit. This is what we feed the computer, right? We feed an axis of a graph or an entry in the table. This is the quantity divided by the unit. And this form of expressing the quantity is not so widely spread. And I have a hard time in teaching it to students that you can, of course, divide by unit. We are used to take it as a multiplication factor, as you showed. But we can also, and you said, we can manipulate it, we can do algebra with that, we can divide it on both sides of the equation, and then we get a plain numerical value. I think our efforts should go in the direction that we can make these understandable to a wider public, that we can divide by units. So complete no offense in the ratio type scale that we mentioned.
So the presentation of SI units that I gave you today it's something that I mean, for a long time I was thinking about units as somehow individual quantities and manipulation of them, and that always led me to sort of philosophical issues from time to time. Suddenly I realized, and this came from both reading Maxwell's, the first few pages of Maxwell's book, and also looking at some of the ways that dimensional analysis was taught. So some teachers of dimensional analysis, which was back in the 20th century, it's dropped off the curriculum now, they explained that these terms are really just numeric variables. And because of that, you don't need to understand what it means to divide a length by a time. What does that mean? You just have a speed. It's telling you how to manipulate data that represents that. And so if you were a tutor of dimensional analysis, you might find it very beneficial to introduce to your students this view of quantity calculus and dimensional analysis, because it makes sense mathematically and you understand immediately what those rules are that can apply to it. And I don't know what a meter divided by a second is, honestly. I'm still struggling with that.
I think there are a few things that we need to pick up there, particularly the disagreement between Europe and America about how you label graphs on axes on graphs. But in time for thank you very much indeed for really.
Okay, so some of what Blair talked about would be relevant here. We'll go a little bit more deeply into that. slightly to explain the pictures on the screen. By the end of this, you'll understand why the different terms have different meanings and why they mean different things in different contexts and based on what we know. Right, okay. So as Sammy said, so I work at the University of Southampton, Senior Research Fellow. There are particular problems that I'm interested in solving and hoping that PSDI can come and help us along with that. So I have lots of different hats, but one of the sort of areas is, trying to make technology easier for people to use and make it more useful. So on the one hand, I'm interested in how people record their experiments. So how they use their notebooks, what they record, but also how moving to digital can help facilitate that process, how it might be more effective, but also what the consequences of those things might be. And the other side is trying to encourage researchers to share their data, and particularly about how they might describe their data so that other people can understand it. So data is completely useless if there's no context behind it. It's a bunch of numbers, doesn't have anybody. You need to understand what it is for, how it was acquired, all of those are different aspects. So that's what I'm interested in doing. So a bit about the technology, a bit about people. Okay, so I'm going to talk a lot about the brain, behavior, psychology. So I'm not an expert in these things, but I do have quite a bit of knowledge about these things. So in part, so when I was at IBM, I was looking at usability, how to make software easier, particularly IBM software is very complicated. Developers don't necessarily care it's difficult. They like people to know how hard it was to make. So I was there to try and make things a bit easier. With Southampton, my research has been looking a bit into psychology, so things like memory, expertise and knowledge. And I've also had a personal insight into the fascinating things that your brain stops doing when you hit the ground at 20 miles an hour and land on your head. So yeah, talk about some of these things I know a bit about it, but I'm not an expert. Okay, so thinking about this talk, thinking, I'm not sure I know a lot about units and symbols, but actually, probably I do know a little bit about it. So symbolic thinking is the idea that we can take symbols and give arbitrary symbols, but we can give them conventionalized, contextualized meanings. This is something that is quite unique to humans. So although animals like apes, dogs, even birds and dolphins can learn to understand our symbols, so they can learn some of our words, the meaning, and some of our gestures, so you can teach apes sign language. None of them actually kind of really use symbols in their own environments in themselves. Bees also can do maths. They can learn human symbols and they can learn those symbols to go and do some maths. They're also kind of fascinating. They also know what the concept of zero is. So yeah, there's things that we can do, but you'd be quite surprised by what other species can do too. So we have a long history of using symbols to mean things. So there's some research that suggests that when we moved to Europe 45,000 years ago during the Ice Age, that actually we probably brought with us 26 different symbols that are quite consistently used across the whole of Europe. So some of these symbols go in and out of fashion over time. So there's maybe more of them at some points than others, but that there are these different symbols that are being used. So we think about cave dwellers, Paleolithic people, and we think about the pretty pictures of animals that they made, but also these symbols were being used, and the use of these symbols was like 2 to 1. Twice as many of these things were being used as the paintings, the animal paintings. So you might think, wow, they're just sort of abstract things. Archaeology is all about ritual. It's some kind of, God worship thing. But actually, there's some evidence that these symbols have meaning. They weren't just geometric doodling. So, for example, where we have these cave paintings of animals, quite often they're associated with particular marks, particular symbols, such as dots, lines, and kind of Y shapes. And some research suggests that these are not just doodles. They're actually data. They have meaning. So the marks are made specifically in conjunction with animals. And when it's looked into, they appear to represent calendar, so that they start in spring, and the dot or the line represents a lunar month. And then the Y symbols when animals are giving birth. So it looks as though this is Paleolithic people actually capturing data, information, knowledge, external memory, so that this information is there. And we know that they, in their pictures, they also represent different seasons. Now, for groups of people that are nomadic, they wander around, they follow the animals, they need to understand when's a good time to hunt, what's happening, what animals are available, then that's useful information. There's also some more sort of evidence of this a bit later, where there's symbols used in complex ways. So this potentially could represent, you know, sort of early stages of writing and language. And there's also evidence from that you get the same signs used in different places in jewelry. They could represent tribe names, individual names, or some other kind of meaning. But there's definitely us and creating meaning out of symbols, and then leading on to writing. Terminology is a long history of doing that. So how is all this knowledge stored in our minds? So going into a bit more detail about the complexity of memory. So this is an area that has lots of its own terminology. There's lots of disputes and disagreements about how it all works. But basically we have two kinds of sort of major memory. So there's the implicit procedural memory, which is the skills that we learn that we forget about, and the processing that happens in the brain. So how you recognize words, how you recognize faces, the processing the sound, and also the skills that you learn. So like writing that you don't think about when you're doing it, or riding a bicycle, learning piano. The other side is our explicit declarative memory. So this is where the memory for things that we know lives. This is the facts that we know. These are the events that we've experienced. And this is our autobiographical memory. So knowledge is thought to live largely in the explicit side, so that we can get at it. If we want to know the answer to something, we can go find that information. So the way that we develop this knowledge is through the development of concepts. So picture of the owl on there, you know this is an owl, you know it's a bird, but from that, your knowledge in your brain links to things you know about birds. So you know that they fly, you know they have feathers, they lay eggs, they have beaks, all of those kinds of things. And that helps us to develop concepts of things. So we have the concept of an identity for something and the properties that it has. So we know that birds are a kind of animal, and because they're an animal, they're living, they're breathing, they're moving around. And we can see that that's very much how we kind of represent information in ontologies. And there's reasons why the way that we structure the way we think about things is the way that our brain is kind of working. So the idea with knowledge in the mind is there's a process called spreading activation, so that when you information comes in, you perceive the colour red, it makes you think of things. So if you talk about red, if you think about strawberry, it triggers other things in your mind. So you might think about other red fruits like apples or berries. If you have the concept of red and you have the concept of vehicle go in as input into your head, then you start to think about other vehicles that are red. So you might think about a double-decker bus or a fire engine. So the idea is that priming, so you have a cue, something, a keyword, something that tells you, gives you an idea, it sparks new ideas, and neurons go firing off and we get more information. So the knowledge in our minds and expertise depends on our experiences. So you saw a picture of an owl. So this is a photograph I took of an owl. I know that this owl is called Shanti. He lives in Norfolk. He's a Bengal eagle owl. And I also can remember who I took a picture with, how I met Shanti, where that was, when that was, all of those things. That's my experience, my knowledge. We have different knowledge depending on what we do. So our life paths, our decisions, our experiences. So in this example, there's brain scans of mathematicians and then professors in other disciplines, experts, and the way that the brain lights up, the way your neurons fire, how big regions of your brain are dependent on that. So for mathematicians, when they see numbers and they see formulas, their part of their brain lights up. It's twice as big as everybody else's who doesn't know these things, but apparently they're very poor at faces. On the other hand, people who are expert in different disciplines, different parts light up and they do things. So knowledge for similar things is stored in similar places, but how it links to everything else, how big it is, how good you are at processing that, depends on what you've seen before. So for some of you in the room, this is lighting up bits of your brain. For me, it lights up the bit that says run away screaming. Okay, so why do I care about this? When we want to get people to write down, such as their experiments and what they did accurately, and if we want them to describe their data, then what we need to do is to get that knowledge out of their brains, because they are the experts. They are the ones who are best equipped to describe these things in the most useful and appropriate way. And it's not just about the description of the data, it's also about how that metadata about data is going to be used. So it's not just a description, it can be used for kind of organizing the information, it can be used as search terms for discovering it, and so forth. So before I go back to how the brain stuff helps, talk a little bit about what I know about how scientists, chemists in particular, but not exclusively, also some physicists, how they are using metadata in the real world. So going back in time, some of you may have seen this before, I did a survey of over 100 electronic lab notebooks to see how people were using metadata. And the notebooks allows users to define their own metadata, and in some quite complex ways. So for each post that they put, each experiment or each section of an experiment, they could create one particular user-defined metadata term, but they could also create key value pairs. So you think the single term enables you to organize your data in a meaningful way, but the key value pairs could be really useful in kind of giving you information about the conditions of the experiment, what materials you were using. And this metadata that users would add would also help to organise the navigation on the interface on the right-hand side there, but also how you might go about searching for the information. That metadata was reused there, and it was also how to organise it in other ways. So it's really quite sort of powerful. And what you would hope, having developed these things, is that the users of the notebook would be getting lots of value out of doing this. They'd be adding lots of metadata, and it'd be brilliant. However, the experiences are not quite like that, and the sort of overall major finding was the researchers were not using the data the metadata particularly effectively. So there are a number of different kind of problems. So the metadata they were choosing to use was typically very high level and not specific. So it's very general sorts of things like procedures, experiments, meetings, that kind of thing. I was not particularly, so it's helpful in terms for them maybe to organise the work, but it wasn't very helpful to actually help people to find things. And this was true of both the individual sections and these key value pairs. So the specific things that were useful were only used a very small amount of the time. So only 30% of the individual terms, and then 20%, even less, where you'd expect it to be more in the keys. So there was also a problem of a minimum metadata use. So the system required only that you enter one section, and you didn't require keys at all. But what we found is that people were sort of bypassing this by using a catch-all. So a section called MISC. So everything would be filed as MISC, or they wouldn't even go to that extent. They'd use a space or a dash or something like that. Anything to satisfy the system, anything not to actually think about it and put something useful in there. An interesting thing that we also did find is that when people were using metadata, it described things. So chemistry is very much about running experiments, procedures, all of those things, and it was all about the things rather than actually activities. There was a lot of zombie nouns, so where things like purification rather than purifying, or filtration rather than filter, that sort of thing. So this was very interesting. And talking directly to users of the system, all of these different groups, there were a number of sort of issues that came out. So partly it was notebook is empty. There's no schema or anything in there. There's not a drop down to select a particular value. Once you've entered them, they appear there. But to begin with, there is nothing. So didn't really understand what metadata was, didn't really understand what they should put in there. Some of them kind of understood it and wanted to use it more effectively, but they were scared, because if they put in something, they were then committed to it. If they wanted to go back and change it, it would be a lot of work. So there was a lot of sort of fear, anxiety about it. There's also sort of not really understanding what the metadata could do for them, how to use it, and the effort involved in creation. There was also, even where groups were, so there's one group in particular that had a leader that actually gave examples, or like a sort of semi-schema for them to use, but even there we had things like things were misspelled in different ways or used in different ways, so we lost all the consistency. So went to have a look, see, so is this just a problem for our particular ELN? Is it the way we structure the metadata? Is it being done somewhere else more effectively? So went to look out, where else can we find places where users are defining their own metadata to describe their work? So we looked at these various platforms. So LabTrove's blog-based. So we looked at some blogs that were about chemistry, looked for things that were labelled as chemistry and experiment. We looked at 500 photos and Flickr that were labelled as chemistry experiment. We also looked at NASA because they, although it's not chemistry, it's astronomy, it's doing very similar things in a kind of similar system. And then my experiments, the workflows, so more the computational side, and tags is a big thing in there. So what we did see was some patterns, but they were very similar patterns to what we'd seen before. So my experiment's really effective at getting people to add metadata, because there's a warning on the page that says you don't have any metadata, we don't have any tags, please add some tags. But in WordPress and Blogger and in the NASA blogs, where there was a catch-all category available, so WordPress is uncategorized. On NASA, there's a category general. People were not selecting something, not adding something relevant. They were still doing that, let it go into the thing minimum effort. 80% in the case of NASA. What was interesting about Flickr is, so it was still really about things. There were adjectives, but it didn't increase the number of things about activities. I'm slightly interested with the sort of like generative image making, and I think that these images that get generated by AI are very focused on things. They're very good if you could give them a thing, but if you try to get them a thing doing something, the pictures are absolutely terrible. And I wonder whether the sort of the way we annotate with things rather than activities actually is influencing that. So the other thing that we learned about looking at the metadata on these different platforms is that the metadata is very community specific. So with the chemistry things, it's very materials dominated, all about the chemicals that people are using. With NASA, it's very much about equipment, so less about stars and astronomy than you might imagine. It's a lot about their instruments and their craft. And my experiment, computation stuff, it's very computer science dominant, the kind of metadata that's being used. So what do we do to help people get better metadata out, more metadata? So one of the first things is trying to explain better to metadata what it is and how to use it and why it's a good thing to use. But there are various techniques that we can do by looking at the psychology. So how the information is in our head, how can we help people to get it back out again? There's interesting things with memory research. So our memory is not as static as we think it is. What goes in does change. It's influenced by things outside. And one of the primary areas that deals with this kind of research is eyewitness testimony, because it's found that when policemen were questioning witnesses, they were interjecting some of their own thoughts about it. And that was actually changing people's memory. If they say, oh, did this man do blah, then it's automatically inserting it was a man that did this thing, and it's changing people's memory. If they're talking about a car crash and they use the word smash, then people's memory of how significant that car crash is changed. They think it was a worse crash than it really was, that kind of thing. So the process was developed called the cognitive interview that actually looks at different strategies for getting information out without corrupting the memory as it comes out, without rewriting the memory for you. So there are a number of various techniques which I might come back to if anyone wants to, or talk about it after, because I'll probably run out of time. But using some of these techniques, not all of them, then looked at how we can extract more information from researchers. So particular ones that we're dealing with are free recall, cues, and changing perspectives. So I'll talk about each one. So free recall is what you do when somebody says, tell me what you're thinking. What you have, if you have a blank piece of paper, what you write down is it's thoughts coming out of your head, knowledge, memories coming out of your head exactly as they went in there. And that's what we do in our paper notebooks. And it's what we do when we enter our metadata without any kind of extra context in it. It's the things we think of, first 10 things you think of come out. Cues is where we use this priming that I talked about. So we use some kind of words, terms to promote people to answer a particular question, to give us information about a particular subject. Changing perspectives is where we actually get people to think about somebody else's viewpoint. How might we describe something to somebody in a particular context, or what are they thinking about? So an example of this is if you're thinking about a house. If you're thinking about buying a house, then the chances are you're thinking about how many bathrooms has it got, how many bedrooms, how nice is the kitchen, has it got a garden, those kinds of things. If you change your perspective to think about it from the point of view of a burglar, the things you're thinking about are very different. You're thinking about what kind of windows has it got? Is there a back door? What's the lights look like? Is there a camera? Is there a burglar alarm? So it creates an opportunity to get at different knowledge because you're priming those circuits in a different way. Okay, so we had a look at how we get information out using these different techniques using electronic lab notebooks. So if we give somebody a blank piece of paper to record their experiment, what do they capture? If we give them a template in the form of very high level headings, you know, the background, reaction scheme, results, as simple as that, what does that do? And then if we change it so that we're giving questions, so we're asking them, record this as if you were helping somebody else to repeat this experiment, because one of the things that's quite difficult to do is to repeat other people's work because some of the information is missing. So I'm not going to go into vast detail about the results, but it did have a significant effect on what people were recording. It changed it significantly, sometimes for the better, sometimes for the worse. But we wanted to try it for metadata and see whether it could help. So we looked at in a number of different studies, including 117 chemistry undergraduates doing chemistry experiments. What happens if we try these different techniques to get metadata terms to describe experiments out of people? So firstly, the free recall, what are you thinking? What's the terms that you'd use to describe this? And then cued perspective. So all of those questions, what materials did you use? What instruments and equipment did you use? Where did you do the experiment? Who did it? What materials? What else? And then the changing perspective, thinking about search terms in particular. So keywords are sort of shortcut in people's brains, I think, for search terms too, but also explicitly, what search terms would you have to help somebody else to find your experiment description? And what we found was very interesting. So we did get different kinds of terms being used to describe things. And interestingly, free recall was kind of the most problematical one. So we got terms, but we also got a lot of low consistency. So people would use different terms to each other, so suggesting that they were describing the same thing in different ways. There was also quite a lot of irrelevant things that came up, so they just weren't sort of particularly appropriate to what we were asking. And there was also kind of guessing an opinion. So it wasn't actually that helpful a way to get content out of people. Q recall was very useful, very interesting. So by far and away generated the most amount of terms, as you might expect, because we were asking lots of different questions, so we got more. And there was also a good diversity of terms. So there were lots of different things that described the information in different ways, which is quite useful. The terms were also really very relevant, and they were also specific. So that was something we don't see in the free recall. It's those really specific things that are really very helpful. Occasionally adjectives sneak in and they weren't particularly relevant, useful. So it wasn't perfect, but it was pretty good. A huge problem with the cued recall, if you don't ask the question people will not give you the information. This is something that's been seen in other contexts as well. So, for example, in digital medical systems, when people move from paper to digital, there were boxes to fill in. And if the patient was giving the doctor or the nurse information and there was no box to put that information in, it did not get put down. It just ceased to exist. So there are problems with making sure that you have all of the right questions, and also, is there anything else you'd like to tell us? So, changing perspectives. So this is about search engine key terms. There was very high consistency, surprisingly high consistency. So across like that group of 117, there'd be 5 or 6 terms that everybody used. And these were very, very relevant, very consistent. There was no personal kind of perspectives on it. And taking these experiments, getting a information specialist to create terms, they were very consistent also with what the information specialists would do. The problem with that is that they were not very specific. You could kind of get the same information out of the title of the experiment. So useful, but not a lot of extra added information. So why am I telling you all this? So there are different approaches that you can take to get knowledge, terms, metadata out of people, but we need to make sure that we're asking the right questions. So how can technology help? I think we spend a lot of time, particularly at the moment with AI, thinking about what we can do for the computer, how can we make it better for the computer, but actually the computer can make it better for us too. There are ways we can use technology to help get knowledge out of people's brains. So one of the first ones is using these cues, using invitations and prompts to get information out of people. So the social media companies are very effective about this because they are built on the metadata that you give them. The information you give them is how they structure things, how they help other people to find them, and how they get to learn about us. So example of an effective cue, invitation is at the top left there. That's so this is a Facebook post, creating a Facebook post. It's inviting us to do some free recall, but it's also inviting us to add other bits of metadata. So location, who we're with, how are we feeling, what are we doing, all of those things. LinkedIn is particularly effective actually at extracting this kind of information out of people. So there's lots of different prompts. It's recommending things. It's like, you don't have to give us everything now. It gives a bit of this, an extra bit of that. And if you do that, then you're going to be in the top 5% of people's profiles. But it's also being smart. It's using the technology. So it's looking at related terms, related job key skills, for example. And so it's suggesting things. So it can make it easy for you by suggesting things and clicking. So also, so I'm a big fan of wizards. It seems like the world has gone into form-based. So everybody's got to fill in a huge long form for everything, which is just awful and terrible. And so wizards are not a thing you particularly see on the web, but on desktop software, they're really quite helpful because they break it down and they can lead you and they can change what path they take. So you can tell it things and then it can make decisions about what's the most relevant thing to ask you rather than give you everything. So it reduces the cognitive load, makes it seem like it's not quite so painful. Okay, so being smart. Clippies for anyone that came to my webinar last week where I had a big rant. But the idea that, you know, we can do better. There are things, if we're uploading some data, we should be able to give the user some more information to be able to prompt them and give them things and to be able to take some of that metadata that already exists. We can validate it with the user and say, you know, it looks like you use these materials. Are they right? Are they correct? So there's more we can do through kind of automation. So, for example, standards is really important here. CIF has metadata about the equipment and instruments and parameters and things inside the file. It's like the user shouldn't need to present that. That should be captured by the instrument and it should be sucked into the system. And then that's there. So it's also important to make sure that the metadata is useful so that people understand why they should bother adding it in the first place, but also so they can maybe change their perspective and understand how somebody else might go about using it. So a really good example for this is Flickr. where, so you have photographs, you can tag your photographs, but it also provides you with a lot of really useful other metadata. So whether you're looking at your own things or you're looking at other people's, you get really useful things. So for example, the EXIF metadata, so this is the metadata that's provided by the camera, and it tells you about the kind of camera it was, but also all those settings that were there. And if you're doing particular types of photography, so for example, light painting photography, that can be really useful to actually look at things and go, oh, what were the settings to do that? How do I get that same effect? But it's also got metadata about, you know, who's looked at it, who's liked it, what are the comments, what groups is it in, what galleries is it in. So you can click on things and you could get more information. It's much more useful. Something I'm slightly sad about is Flickr used to have automatically generated tags. So it could do image recognition, it could identify what was in the photograph, and it would show those. And that was really helpful. It was really interesting to see what the computer could do and what it couldn't do well. So I have lots of photographs of ski jumpers, which Flickr decided were bees or insects, which is, you know, quite logical. They were flying and they were like that. So yeah, perfectly reasonable. But this is a, you know, a good use of metadata. This is helpful. So there's opportunities to get metadata to collect terms, descriptions from people all the way through the data life cycle. So from the data management plans that we fill in, there's lots of metadata. Our data files, there's lots of metadata. And at the end, what we want is that metadata because it's useful when we want to archive it or to publish it, share it, help people to find it. So we should be doing more. We should be supporting the researchers to give us their specialist knowledge. They are the experts. We want to extract that in a nice user-friendly way. So, for example, I would quite like to build something like this that takes all of those different things, encourages researchers to give us that information, and then at the end they can press a button and it creates a nice package they can upload in a really nice way. So it's challenging, particularly terminology is challenging. So for PSDI, we're using metadata. It's become very central to what we're doing and how we're going to expose that to the people that are going to come and use our service. But it took us months to get to the consensus that what we were providing were resources and that we had resource types of data sources, tools and services. And because there's a lot of to and fro, we're coming from different knowledge backgrounds, we have different terminology, understanding of what they mean, and you know, there's a bit of a fight to get to something everybody can agree on. And part of this is because what we learn is what comes up in our brain first. So there's evidence from MRI scanning and neurology that the things that we learn first, we have to actively the brain has to inhibit before we can sort of then go on to the, oh yeah, this is what it really means, what I learned later on. So it is difficult. So another example of that is in caving science. So there's lots of different disciplines that do research in caves, and they all have different terminology. They use different terminology to describe the same things. They use the same terminology to describe different things, and they have a lot of linguistic arguments. But what they found is that having, as well as those kinds of issues, we also tend to go in science into acronyms and jargon and very specialist terms that mean it's much more difficult to communicate with each other. And if you put those specialist terms into your title of your paper and your abstract of your paper, you will get less citations, because people are either looking at it and not understanding it, or because when they're trying to find things, they're not finding your work. So you need to keep it simple, make it easier for people to understand, and particularly think about how do we communicate with the public, who are after all paying for a lot of what we do. Back to the picture at the very beginning, the idea that meaning comes from what we've learned in our life experiences. So some of you, if you went to my webinar, would have seen this before. So save icon, everyone knows what the save icon is, but what we actually understand it differs. So if you're more technical, from an older generation, you know that's a floppy disk and you know what you do with your floppy disks. If you're a younger person, you've no idea what that is. And apparently they tend to think about it, it's a garage. It's a place where you put your stuff. It's where all the junk goes. And the same thing with padlock. When you're doing your internet shopping, you know, you need to see a padlock. For those of us that are more technical, we know if that's a padlock, it means it's secure. For shoppers, it's a fancy handbag. So you can also have symbols that have shared meaning, even though actually our understanding of it is completely different. Thank you very much for listening.
Thank you very much, and perfectly on time. So, do we have any questions from parents? We do have 10 minutes in the schedule. I'll be used to the question.
Everybody's dumbstruck.
Thank you. You talked about how queues were really important. I wondered how you were, well, I guess the question is to what extent are you able to use ontologies and related things as part of ways to develop queues and to direct the responses, control the responses, so then we're useful at those?
Yeah, I think so. I think the so providing a terminology actually makes it easier for people because it is giving them the starting point, and also they can understand that there are correct terms rather than whatever the sort of vague. Because I mean, so chemistry, naming of chemicals is extremely complicated, and there are many different ways of doing it, and how you know that you can draw a chemical and all of those things. I think giving ontologies is really helpful. I think the area where we need to be careful is that that we have the same understanding of those things. But I guess the ontology helps because it gives the extra context to the terms. So yeah, I think it's important. Getting consensus on developing them is a whole other issue.
Speaking on that, there are quite a lot of ontologies that obviously cover the same things or have overlapping with them. So how do you decide which ones?
Well, I think that's a question for the individual researcher to a large extent. I mean, so there isn't a simple answer. If it was a simple answer, we wouldn't have hundreds of different terminologies. So I think it depends on who you're working with. So I think it's, you know, if you're working in a lab on your own, you can use any term you want effectively, so long as you understand it, but it means nobody else is going to understand what you do. If you are collaborating with other people or you're collaborating with other disciplines, and I do think there's a negotiation, let's select which ontology, which taxonomy is appropriate for what we do. And it has to be a negotiation that at least you can agree. And then if you can tell other people what you've done, at least they then have the context to go look that up and understand it, and, you know, understand the reasons why you've chosen.
I'm not sure, but I mentioned I'm so science. It's actually most what I do is doing it, but a lot of what you're describing there, essentially, is very, I mean, the experience of missing metadata, missing, you know, trivial responses, essentially are things very similar to what you would see in social sciences, down to the point of having qualitative interviewing before we test for, before we run surveys and so on. And I wonder a little bit, so what we do know is, often is having control vocabularies, ontologies, we get what we need for those. So having a sort of, partly the question might be having sort of design goals. What is it, let's say, the set of terminology, if not exchanging it, also very early, also just say, it doesn't matter if you want to be more specific there. But so is there intent there for what, if it's missing metadata, so what? I mean, it's an argument, so I'm very concerned about that from the church's point of view. If they're not sharing it with others, then it's not really an issue that's there. So is there a set of sort of design goals that you see progress there? Set and following on from that, it might, let's say, a lot of the sort of cognitive psychology talk about and it's thinking fast and slow, that, you know, kind of feed into this might be sort of a basis for kind of making decisions there to sort of essentially to your experience.
Yes.
Same thing as well. That you draw upon you and kind of fill in the gaps as well, which is say, is it good enough to stand by, you know, or sharing terms, is that enough? What do you think?
I think it also is a battle that we have to convince people that they should share their data, and that somebody, you know, they don't even think, well, why would anyone want my data? So there's a communication and an education effort to sort of communicate why that is important, and that it's not necessarily so it's good for you too, because you keep your data nice and safe. You've described it, so you know in 2 years' time you can come back and understand it. But also, yeah, that changing the perspective to think about, so how might somebody use this? How might they go about finding it? Can I write a description that describes this in a nice, you know, actually understandable for somebody that doesn't know my very narrow specialism? It's a lot to do.
I think there's one person that has probably filled in a blank space in one of these metadata forms. I can very much synthesize. But then I'm also on the other side where I'm trying to use data and then the person who produced them and didn't put the metadata in there that it needs to use it. So is there a solution where we're getting the people together, both the generators and the users of the data, to make sure that everybody's satisfied? I mean, you said these queues would be one way of automating queues. Is that what we should be doing?
Yeah, I mean, I think maybe. So I think that AI is going to kind of drive a lot of that in the, you know, actually what do we need to do to make our data ready for machine learning? And so that the sort of that the producer of the machine learning as being the sort of ingester of the data, and therefore they can kind of say what their requirements are. I think in an individual level, it's quite hard. So one of the things I've noticed, particularly talking to data students, is there's a desire to get rid of data, which is what I also see with software, that people create a thing and they've done it, and you know now they've checked the box, it's uploaded, it's somewhere, it's not mine anymore, I don't care about it, I don't want the responsibility and the effort involved in worrying about it. And I think that's kind of a shame. I think that we should be proud of our data, and that we should want people to use it. We should want to, you know, engage with that. Oh, you really want to use my data? Great, terrific. What can I do to help? But yeah, nobody's got the time, I suppose.
Any final question? I have time for one more. Okay, thank you very much.
Thank you.
Promptly, so we are now going to have the much awaited talk earlier from, I'm going to get it wrong, Gyorgy, and then we will continue. Then after this talk, we will then get back on the regular schedule.
Thank you for the introduction, and thank you for giving me the opportunity to give this talk. It's the first time that I take these ideas beyond my small team at the OECD. So I made the title a bit risk averse now that I read it. Probably the way I will be pitching it, it's going to be a bit more risk taking, but hopefully I will not stir too much controversy with the ideas presented here. So about the OECD and my team, the OECD stands for the Organization for Economic Cooperation and Development. It's an international organization with almost 40 member countries, headquartered in Paris, with the motto of building better policies for better lives. It's a primarily policy-oriented organization, but as part of its mission, it collects, integrates data, and disseminates the integrated data on various aspects of the economies and societies that are members and are partners to the OECD. And so you can see here on the slide a couple of topics that are covered. It's even longer than that, but I couldn't scroll the whole image to take the snapshot. So we deal from agriculture to health, public governance, society, and general economics data sets. And so this work is done in more than 100 small data producing units in a fairly decentralized way. My team, which is called Smart Data Practices, is doing a little bit of coordination, best practice work with the data producing teams. And so in the last 2-3 years, we have revamped our data warehouse. This is the front page of the Explorer or data warehouse. And as part of that work, we revised in the range of 1,000 data sets. We looked at metadata and we looked specifically into how units of measures are described and defined. And it was one of the most challenging parts of harmonizing and coordinating and improving the quality of the data as a whole in the data warehouse. And so some of the ideas that I will bring here come this experience that we worked on, and we kind of distilled as initially internal guidelines for working with units measures. And so, I mean, briefly, what do we like in units of measures, and why did we insist with many of our data producers to do a more rigorous work than they did before, and to review their practices? The first thing that we appreciate in units of measures is that in a data warehousing context, it gives a very immediate grasp to the user of the data of what kind of quantity is being measured, even without reading what was the measurement description, what was the measured quantity description. We have an idea of what it is and how big it is, and so that's the immediacy. If we didn't do this rigorously, of course, that information is still somewhere in our metadata or associated methodological documentation that is published, but it's much less useful for user of data. So, and then the second point that we like about it is that it sets the scope of comparability of the data. And this is related to the previous point, but what we like to see is what in our data warehouse can be compared with each other. What is commensurable, what we can add up, what we can subtract to make meaningful derived quantities. And more in general, it's activating dimensional analysis on a large part of the data which has units of measures. And where I'm talking about units of measures that are not the non-units of measures or the kind of dimensional quantity associated units of measures of just one. So we try to avoid maybe too hard to have quantities, measured quantities in our data warehouse that are represented as dimensionless quantity. Kind of storing all the information about the quantity on the left-hand side, so in the descriptor of the unit of measure or in the various dimensions that make up the key of the data or the description of measured quantity. And then ultimately, and it's based on the first three properties, is that since we are in a data warehousing context, we can use the units of measures to filter out all the commensurable data and give slices of data to our users that are immediately comparable, can be put on a table, can be put on a graph, and of course not everything that shares the same unit of measure is immediately a good candidate to be put on a graph or a table, but at least it's it's a good first kind of slicing and filtering on data warehouse. And similarly, it allows pivoting. If we have the same quantities measured in many different ways, our users often like to see the different measurements next to each other. Sometimes one way of measuring gives more insights to the data, and some other units of measures or other representations of the same data give more intuition to data. Skip this. So while working with the data, we have noticed a large chunk of our data assets being characterized by counting quantities or counting style units of measures, and we had long debates in the organization whether these are just dimensionless counts where there is nothing to be shared in the unit of measure, and then everything goes in the description of the statistical measurement. But in the end, we kind of tilted, and we have taken a deliberate approach to represent all these counting quantities with a specific unit of measure. And I will describe the process, how we try to still stay kind of with a limited scope of counting units of measures and have some rigor in the application of this counting type units of measures. But just to give you an illustration of what you can come across as these types of units of measures. So we have plenty of measurements in our data warehouse that are just counting sets of persons. So you can think of a population of a country, or people in the labor force, persons who cross borders, and so on. And so these are the measured sets that all have their ideal or typical element, a person. Not as simple as that, but I mean, just for the sake of introducing some of the most typical cases that we dealt with, poly persons is the best example. In our case, we didn't come across too many electrons or electron-related measurements in our economics and society-related data working with electrons, but I have put here nonetheless because in our development of our internal guidelines, we try to stick as much to the international system, and we try to stick as much to the spirit of the international system. And so we have seen that many of our problems are not covered or not fully covered, but we always hope that we can work on analogies and then bring those analogies to our problems and extrapolate. And so here, for example, we have seen that in a way, the international system struggles with the same problem, and it's a little bit schizophrenic, maybe too much of a statement, but just to illustrate what I mean here is that unfortunately I didn't put it on the slides, but in the second paragraph of the SI definition for the mole, we have something that says that it's elementary entities, Avogadro number of elementary entities, and then in a parenthesis, maybe an atom, a molecule, an ion, an electron, or any other particle, or a specified group of particles. And the dimension that it relates to is the amount of substance. And so, yeah, our initial thinking was, can we think of persons as measured in, I don't know, nanomoles or even smaller number of moles? And theoretically we could, because you could say that the person is just a certain specified group of elementary particles. And then we fit within the definition. But of course, for us, the Avogadro number as well, it's a very impractical kind of unit multiplier for the. And having looked at kind of more science examples, also we have seen that still there is an ambiguity whether we should say mole of entities, elementary entities, or moles of electrons, or just mole, because the mole already contains all that, and then there is something left to the context to determine about. And so, yes, the third example is just a couple of other related containers, which are somewhere in between our kind of pure counting quantities or itemizables and between something that has a strongly correlated physical unit like volume, or in most cases volume, but it could be mass as well, a mixture of volume and mass combined that could kind of substitute for the containers. Okay, sorry. And so, yeah, here in my talk today, I would like to challenge two, I call them entrenched positions. Probably they are not entrenched because I have seen kind of mixed usages and mixed recommendations on these topics. But one of the idea where we kind of took an opposing view in our data warehouse practices and in the guidelines that then followed from that is to in working with these counting type quantities, we don't look at them as dimensionless, even though we don't necessarily identify and associate a clear-cut dimension with the measurements being done. But we definitely don't take the approach of assigning the one or the unit or the broadest unit, maybe entities to it, but going in a more specific direction of kind of capturing better the ideal element being measured for a certain set of elements. And then there is a second idea. I'm not sure I will have time or whether it will fit perfectly with the talk today, is to challenge also the idea of measured quantities being very different or fundamentally different from units of measure. I think this is, again, not an entrenched position, but especially in forum discussions in the QUDT ontology group, there are kind of efforts to delineate between the units of measures and between other quantities measured with those units of measures as being so different that the quantities shouldn't be considered as units of measures. And here's, of course, I mean, I see the rationale of these two positions. They kind of protect the system from blowing up. So if we throw away this kind of axioms or positions in a unit of measure system, then there is a massive scope creep. With the counting quantities, you can imagine a large number of different sets. Members are counted, and all sorts of ideal elements for those sets then considered units of measure. And in the second case, we have all sorts of measured quantities that people just out of fun will try to push into standard ontologies like the QUDT to say, I don't know, the distance I cycled yesterday afternoon is a valid number. It's not necessarily the best unit of measure, but it could be as good a unit of measure as the meter if everyone adopted it and that was an observable, very well-known distance. So those are the two things I try to kind of go against. Not because I want to blow up the system, but because I think that by having these two positions, my data warehouse would have very few nicely written units of measures and would have very few of the the things that I presented as things that we like about units of measures available to them. For me, or for us, the goal was to have dimensional analysis work for us in as many measured quantities as possible. And so one of the way I try to go about this is to present to you how much measurement, at least in kind of an archaic intuitive way, and counting are very close to each other. And so when I talk about counting and counted quantities, I usually imagine that we have a set of items, and the set is described by in some form, but in most of the time by an ideal member of the set or an ideal element of the set. And so when we do the counting, we define this ideal element. So in the case of population of a Borga, we would pick a person as the ideal element set of persons, and then we will kind of identify this ideal and finally count the number of times we identify this ideal in our population without overlaps. And so this is very analogous on how we do measurement, for example, for distances. We take a standard which is recognizable and well identifiable, and then we line up this standard or align this standard to something that we want to measure, and we just count the multiples. These two things align. We make an effort not to make overlap in the count. And yeah, this is probably a very kind of impractical way of doing the measurement, but I would bet that in most of our heads there is something like this when we think of a measurement process, and in that sense, counting the elements of a set is very typical, similar to measuring something like a distance or a length. And yeah, so those are the similarities, and that's what drives us to say that when we associate this sets a unit of measure in counting process, we take the ideal element, or we try to identify the ideal element. But then we see that usually when we think of the traditional SI or SI compatible units, we have this idea that they are continuous, although not always. And I mean, with recent physics, we observe that most of the SI units could be replaced with some sort of Planck unit that corresponds to that dimension, which is the smallest indivisible unit that we could associate with that dimension. And so in that respect, it works if we were to say measure distances in Planck distances or Planck lengths, and we were to measure time in Planck times or mass accordingly, we would be very much in the situation of counting. We would have a smallest indivisible element that we just count when we count pies or kind of extensions along that dimension. So the other difference, and I think this is one of the crucial and real differences between counting units of measure and the classical units of measure, which have a well-identified associated dimension to them, is that most of the time you have an obvious choice, but there is a little bit of ambiguity on which unit of measure to pick, of a whole set of trees of candidate units of measures or candidate ideal elements for the measurement. And already the mole definition illustrates that we have on one hand or one side the entity, which is probably the broadest unit of measure that we can think of for measuring discrete sets. And then in this case, I was just drawing some immediate candidates around the person. We could think of a legal entity, which could be either a person or an enterprise, so entity that can get into legal contracts. And then a person could be an inhabitant or a visitor in Seborga, the self-claimed principality that I mentioned before. Depending on the context, sometimes person is the good choice, but sometimes if the definition requires, maybe inhabitant or visitor would be a more accurate choice for the unit of measure. But then if there is this ambiguity, how can we work with that, or at least what kind of soft guidance can we give to our data producers to pick the right unit of measure that fits their context? Here our guidance was, at least internally, to pick the most generic possible unit of measure that the users would still find useful in their working and would generate useful subsets of data where the dimensional analysis will still work. Persons with persons can be added up and compared, but avoid as much as possible scenarios where there could be a double counting. So let's take the example of inhabitants versus, sorry, not inhabitants versus visitors, but teachers, students versus persons. So in some education data sets, we ended up having units of measure which distinguish between teachers and students. And there the deliberate choice was made, on one hand, to be able to have teacher-student ratios of various kinds, but on the other hand also because some of these categories, or being in these categories, were often overlapping. And so just allowing addition, or kind of giving the hint that addition is allowed of such quantities would mislead the users. So choosing a more specific kind of counting unit of measure highlights that maybe there is something that makes these things not additive or not immediately comparable. So it's kind of the task of the user of the data to check carefully whether in their context or the specific measured quantities they can upgrade teachers and students to persons and then make the operations of the rules of dimensional analysis. And so there is another kind of criticism that comes with that people who try to propose these counting quantities, for example, to the QUDT editors, is that these quantities are often labeled as contextual or more contextual than others. And it's true, as this category 3 presents it can be very context dependent. But having said that, even classical units have a certain element of context in that. And mole is a glaring case, but if we set aside mole, I mean, even let's say with the meter, if we were to really precisely use meter, we should always give more context and maybe subscript the meter to the inertial reference frame in which the meter applies. Because if you take two inertial reference frames, the meter measured in one is not the meter measured in the other, and so they are not additive or not immediately comparable. And I mean, it's probably a little bit nitpicky, but if we were to factor in also that the definition of meter changed several times in the last couple of centuries, then ideally, if we were to make it properly context-less and precise, then we would have to add qualifiers for the vintage of the dish. Okay. So these are just to illustrate how, I mean, there are differences indeed in the counting units of measures, but they are not so clear cut as we would think at first sight, and these differences are kind of more on the spectrum than very large cleavages. And so with the proposition of letting these second-class citizen counting units into upgrade them to a resident status or give them citizenship in the units of measure world, there are a couple of problems that could be solved. So in the case of mole, we could have a much more clear-cut recommendation to indeed use electrons, atoms, and molecules next to the Avogadro number, and kind of, or use mole just to represent the Avogadro number and say moles of electrons, molecules. It would kind of fix the problem that was mentioned already with the M-layer presentation by you, Blair, with Hertz and Becquerel, because you could call them periodic event per second and action per second, because there, this kind of non-unit in the numerator is really that hidden, non-spoken, tacit understanding that there is a counting unit. We count in one case periodic event, and in the other case we count actions, and those are probably in a kind of tree, maybe not on the same branch, and then they would be nicely and easily distinguished. Although it would lead to a very interesting dilemma if we consider the category tree of event, wave, and second. We think of the second definition as just a very special wave, that of the cesium emitting a certain energy transition. It would be kind of a real headache to then understand how the periodic event and versus a second works, and whether that's, let's not go into that, given the only 1 minute left from my presentation. But of course, it would also save lots of headaches for us statisticians, because we could kind of use or kind of validate our current practices of using these counting units as proper units of measures, and to take away some of the ridicule that some of our colleagues face, or giggling that comes up when, for example, the suppository is often mentioned as a very strange unit of measure, which is in active use since a couple of decades in the codes of units of measure for international trade. And so, sorry? Suppositories, the things that go up as medicine, it's kind of a packaging unit in trade of medicines. They have boxes and I don't know, tablets, suppositories, and they are counted. And yeah, and dosages depend on that. Have suppository per day, measures like that, derived units of measures like that. So just very briefly, in the proposed way forward, I think of two directions that we could consider. One of them is to, because these new units cause trouble. I see that, and they stretch probably too fast and too far the SI system or any system that is kind of an extended version of that. And so one nice thing would be to follow up on recent work that has been done to build kind of algebraic representations of the current units of measure systems, to include some of the features that may come from an extension like this, which focuses on the discrete of units of measures rather than the continuous representation of units of measures, and works out the algebra for that and limitations and probably nice properties that come with that. And also the fact that there is this category of possible ideals that would need to be kind of handled in a certain way. And then the other line of work would be connecting to software and ontology developers, for which I think the drum group is the perfect starting point to reach out from and test the waters, whether there is appetite for early implementers, experimentations on how exactly this could work. That I close my presentation. Thank you.
A comment perhaps rather than a question. I think you were referring to the quantity amount of substance and not to its unit, the mole. But in your case, I would think it is perfectly okay to say that ship has 1 micromole of grains loaded.
Yeah.
Because if you just count it, I'm about that number. And of course, the mole or unit mole played a role just to make this link between the microscope and microscope. It was very long, very difficult to assess this now. First, actually, correctly given by a theoretician by Max Planck, 1900 paper, right? Gave the first value of the Avogadro. It not change it, so I would not agree with. You have to specify the amount of substance that has to be.
Thank you. Just a comment. I think it's very clear in the SI that the amount of substance in the mole is designed to recognize elementary entities and distinguish them from other entities. So the definition very clearly says elementary entities of a system, and that's designed to be of a system whereby a thermodynamic system where things can react together. So it is not designed to be for non-elementary entities, and that's because we give it an independent dimension. So there is no such thing as a mole of eggs or a mole of planets. It's only designed for elementary entities.
Jeremy invited me to come along and give a talk about well, isotopes and the work of the Commission, and specifically mention at some point uncertainty in relation to atomic weights, I'm presuming, right? Not just uncertainty in general. But I'm going to talk a little bit about IUPAC projects on terminology for isotopic analyses. It really nicely has, all the other talks today have got things that are relevant to what I'm going to talk about. It's just really nice. So, option that I can go. There we go. Yes, so I'll talk a little bit on why isotopes are important, where standard atomic weights comes in. I'll talk about some of the issues that have arisen with terminology and nomenclature within isotopic analyses in the time since the 1940s. These kind of analyses were first performed, and then how IUPAC projects have been drafted, attempted to address these problems and the successes, partial or otherwise, that they have had. I'll start with the first one. Isotopes are important in terms of chemistry. They affect the standard atomic weights of elements. So if we think about the periodic table, we know there are some elements that are monoisotopic. There's one stable isotope that contributes to the atomic weight. And that's why we know for elements like fluorine, the standard atomic weight at the bottom there, got a really small uncertainty. It's in the 9th decimal place. That's because all the fluorine atoms are the same. Other elements, like strontium, they've got more than one stable contributes to the standard atomic weight. And there's two factors now that contribute to that uncertainty. The first one is how well can we measure the mass of any one of those isotopes, just like it is with fluorine. The other one is that pie chart varies a little bit depending where your strontium comes from, because physical processes, biological processes discriminate sometimes against heavier isotopes or otherwise lead to slight changes in the relative distributions of those isotopes. As a result, we end up with an uncertainty that is very much larger. That's because it's a contribution of both things. And then for some elements, like oxygen, the uncertainty through this natural variation in the shape of that pie chart is by far and away the dominant source of uncertainty. It's the measurement precision of measuring those isotopes themselves is a really minor kind. And at some point before I joined the IUPAC Commission on Isotopic Abundances and Atomic Weights, they decided that actually for education purposes, it's useful to express that slightly differently and express it as a range. So what that means is the atomic weight of oxygen and the atomic weight of oxygen is a range. So for any specific sample of oxygen that we meet in our labs as chemists, could be a reagent, could be a sample, lies somewhere between those two numbers with great certitude, I believe is the phrase. But it tells us nothing about the likelihood of any particular point in the midpoint of that interval is not the most likely standard or atomic weight of any particular sample of oxygen. So actually using this in calculations is difficult, and that's why the Commission also provide a single number, an abridged atomic weight for use in a more straightforward way than people who don't know how to use. I can't do interval math. So we have monoisotopic elements where the uncertainty is dominated by measurements, and interval atomic where the uncertainty in that standard atomic weight is dominated by variance in the abundances of the isotopes across different sources of that element. And the key thing here is that standard atomic weight applies to all normal materials, normal in inverted commas. There's a specific definition of what normal means, but basically it covers, as I said, everything that we could come into our laboratories. And as an upshot of this is that atomic weights are not constant. As an isotope ratio chemist, metrologist, I see plots like this, often called isotopic landscapes or isoscapes for short, and they often have delta values, I'll come on to those later, expressing variation in isotopic composition of elements, sort of geographical. But you could also just label it with atomic weight of oxygen, rather than saying it's the ratio of oxygen 18 to oxygen 16 that's varying. It's also the atomic weight of oxygen that's varying in river water across the US. That's true globally as well. So this idea that atomic weights are constant just isn't the case. The atomic weight of oxygen depends on where you're getting your oxygen. Why these things are important, I will touch on. There's all sorts of applications. I will concentrate on one of them, food authenticity, and it kind of gives a quick introduction to how we might express isotopic composition. So the plot there has got two axes. The one at the top is amount fraction of carbon-13 expressed as a percentage. So it's about 1%, and there's a bit of variation across. And the bottom one is what we call an isotope delta value, and that's a relative difference in carbon isotope ratio, so carbon-13 to carbon-12 ratio between a sample and a reference. Complicated, but it's a delta expressed in per mil, so we end up with numbers that the human brain can comprehend easily because they're in the sort of tens and hundreds. The key thing here is that if we look at different sources of carbon have different carbon isotopic composition. We have different amount fractions of carbon-13, different delta values. Two different photosynthetic mechanisms of plants dominate across the world. 95% of all species, that's critical here, are C3 plants, things like wheat. But some important food crops, like maize and cane sugar, are C4 plants. And those two plants discriminate against carbon-13 and atmospheric CO2 to different extents. They have different atomic weights of carbon within them, different carbon isotope ratio within. We can measure those differences really well. And that means if you bought a chicken and it says it's corn-fed, carbon isotope ratio of that chicken should tell you whether it's corn-fed. Should. You can do the similar kind of thing with nitrogen isotopes, because if you've got conventional farming and organic farming, the source of the nitrogen that goes into the plant has a different nitrogen isotope composition, because one comes from the air, essentially, and the other one comes from animal manure, and through food chains, nitrogen is enriched in 15N, so there's more of it in animals, more of it the higher up food chains you go, because animals preferentially excrete lighter isotopes of nitrogen, 14N. So these different sources of nitrogen would feed through to the plants that you might see grown in different farming regimes. I showed you that atomic weight of oxygen, isotope ratio of oxygen across river water. Same thing's true with rainwater. Same thing's true with hydrogen isotopes in that rainwater. So you could look at fruit and fruit juice and say, well, actually, if I've got pure fruit juice that's shipped around the world, water in that juice should reflect water where the plants grew. If I've taken it and I've dehydrated it and shipped it and then rehydrated it somewhere else, well, likely the hydrogen oxygen isotope ratios of that extra water that's been put back in is different, and should see a difference. So again, if it's juice from concentrate or not juice from concentrate, maybe we can use isotopes to help see the difference. This is a kind of field where people have measured isotope ratios, or specifically, they measure differences in isotope ratios, particularly this relative difference in ratios. And they have done, as I said, since the mid to late 1940s. And in that time, certain conventions have arisen in how we express these things, but it's not all plain sailing. So this delta is a relative difference between a sample and a reference generally expressed in per mil. Some people, when they're expressing it in parts per 10,000, because it makes, again, their numbers into things the human brain can comprehend, use a different symbol, but it's the same quantity. And others use mu when it's in parts per million, because therefore the variations they're expressing are much smaller. The other thing to think about is this ratio, isotope ratio. It could be an amount ratio of isotopes in mole per mole. So your delta is really mole per mole per mole per mole. Or it could be a number ratio where you're counting the numbers of atoms that are particular isotopes, in which case it's 1 per 1 per 1 per 1. But they both reduce down to 1. And at some point, some people like being able to distinguish ratios that come from amounts and ratios that come from numbers. And some people use capital R for one and subscript R, lowercase r rather, for the other. But some people use that distinction of upper and lowercase r in terms of ratio to do with a measured ratio from an instrument versus a true ratio or a calibrated ratio. And it all just adds to the confusion when people come try and learn this from school. The other thing we find is that over time, lots of different people use lots of different things to mean almost largely the same thing. So if we think about an isotope amount fraction, so the amount of carbon-13 relative to the total amount, you can express that as a percentage. But yeah, it's an isotope amount fraction. But the amounts of carbon-13 related to the number of atoms of the carbon could get the same number, the same uncertainty, numbers, amounts. And some people use slightly contrived terms to describe these things, like atom percent, either with the symbol for percent or just written out, or AP for short. People use atom fraction, mole fraction, isotopic abundance, isotope abundance. Actually the same number and same reduced. And this is great if you're English, have English as a first language, because you can write a paragraph about isotopes and never repeat yourself, or a whole book, right? But if you're coming to this as English is your second language, your third language, you're coming to isotopes somewhere else in chemistry, somewhere else in science. This is an absolute nightmare to try and explain to somebody that, yeah, those two things, they're actually the same. And linking to the sort of counting, being specific about counting, delta, relative difference in isotope ratio between sample and reference, is very specific to that reference. You change the reference, you're changing delta value you get for a particular ratio in a particular. And that also means that your per mil that you're expressing it in, the different size. And so if we don't know enough about the measurements that have given us these delta values in per mil, like what is the reference, how is it being defined, how have you calibrated? It's really hard to know if things can be compared one to another. And it gets even more complicated that we're measuring relative to references that have evolved over time. For carbon, the original reference that was adopted internationally is something called PD belemnite. It's a fossilized Cretaceous thing from a rock formation in South Carolina. But of course, that was only a limited amount, and everything's done on CO2. So this carbonate is converted to CO2 and you've run out, or it's found that it's not homogeneous. Then what do? Well, then they defined new reference, Vienna PD belemnite, in terms of another reference material, bending this thing. And then you've got a point where you're saying this is 0. Then you can define a scale because you've got complete absence of carbon-13 right at the other end. But then, pretty practical thing, you can't get hold of pure carbon. So people have then adopted extra points on the scale, or an extra point to give you a span. So scale contraction or expansion effects. You can get rid of those things when you're comparing between the blocks. That sounds great, but that 2-point scale is the same as the theoretical 1 scale with a. You end up with 2 scales. That gets even more complicated when you're trying to compare delta values, particularly over time. And this kind of thing's been going on for a while in terms of trying to make things better. And the first attempt started just at the 2001. It's quite a long time ago. And it started as a project trying to improve or trying to make mass spectrometric measurements of isotope ratio better. But if you read the notes on the IUPAC project page, the updates, the early ones, are all about we couldn't achieve consensus because of whatever reasons, different user groups and so on. And then it was very quickly decided, well, we're not going to give guidance on how to do the measurements. It's going to be guidance on reporting the results of your measurements instead. So glossary of terminology used in expression of relative isotope ratios, that means the delta values, gas ratios. But actually, when the project came to an end, it didn't come to an end with IUPAC technical report, IUPAC recommendations. It came to an end with a publication in Rapid Communications and Mass Spectrometry. And it is a really nice paper from Ty Copeland. It's not just Ty's own work. It's based on the publications from the Commission, in applied chemistry at the time, input from other experts and so on. And even in the acknowledgements of that paper, this kind of lack ability, impossible to achieve full consensus. There we go. It highlights that this is a tricky area, and that's because it's got a long history and people have been entrenched in what things that the way that they like to express. That's not to say that this paper hasn't actually been useful. You don't have Web of Science access or anything like that, but if you look at Google Scholar, it's been cited 1,800 times, which for a publication isotope ratio area is ginormous. And I think as far as rapid communications and mass spectrometry goes, it's one of the most highly cited papers they've ever published. So it's clearly important, people clearly use it, but it's had some limitations. I think, obviously it's not an IUPAC document, so a lot of the terms and things in here are still absent from the coloured books and green book and the gold. And the other thing is, that was published in 2011. It's over a decade old, and there are some applications of isotope analysis that weren't in existence then that are now, where there's then issues with terminology. But 2 of the examples down here, I'm not explaining what they are, but both of them use a capital delta, but in very different contexts. And then, again, another problem where we have the same symbol used in different ways, and we have to be clear about what we mean. Some of the entries in this paper go against, I think, the current SI brochure. For example, they recommend mole fraction as something on the name of the unit into the name. But the other thing that's happened relatively recently, so certainly within the last couple of years, is that we have consensus for some things that it hadn't been achieved for in the. This is particularly around how we might define what an isotope delta scale is, not the quantity, but a scale that we can make measurements. And what changes to that definition might result in a new rather than a continuation of the old. So maybe it's time to revisit this and have another go. Another installment is a project led by Jan on terminology and definition of quantities related to elements with more than 2 stable isotopes. This is again something that was largely missing from his paper. Long time going on, but there are recent progress, and hopefully there will be something coming out soon. So, but it takes time to discuss it. In terms of this project in particular, it suffers from this capital delta thing. So I'm going to refer to one of Jan's papers from Rapid Communications from 2008, where this paragraph will do about definition of oxygen and sulfur isotope anomalies, 17 capital delta. And it's been defined in 4 ways, and they're kind of similar if you squint, but they're all also not the same. And how to unify that, and how to make something coherent that people can use and that's clear, I don't envy you, Jan. But maybe there's something to be said for, like, do as you wish, but be clear about what you've done. And that's, I think, probably where that's going to. But now there's a third project, which is the one I've led, and this came out of involvement with the CCQM isotope ratio working group. It's quite a new working group, and within the IPM, we had this issue where we need to use common terminology to mean this. And so within that working group, we wrote a document to try and unify our terminology. But now this is an opportunity to try and do the same thing more widely. It's been going for about a year. We're building on existing resources, and our idea is to write a technical report, first instance, which gives us all the context, and then recommendations to follow, which will probably be quite shorter, because it can only be for the things that we can really make recommendations on. We've been asked to look at Goldbook entries. I've listed a few here. And that's kind of made us think about, it's not just quantities, units, and symbols, it's the other terminology. And those Goldbook entries and other things have highlighted some recurring issues. One, some of the terms in the Goldbook at the moment are unfamiliar to us as a task group. Isotopically deficient, I've never seen it anywhere, but maybe it's used in the field of isotopic analyses that I'm not familiar with, like radioisotope. We have definitions that aren't necessarily consistent amongst themselves in what terms they use within themselves. There's macroscopic composition. Is that difference important? It is important. Well, maybe we should be explaining why it's important. Sometimes we need maybe an umbrella term. Isotopic fractionation might imply a change in the isotopic composition, but we can have isotopic depletion, isotopic enrichment. We have to specify what is being depleted, what is being enriched. Otherwise, we can be talking cross purposes. If I enrich something in carbon-13, all other things being the same, I have to have depleted it in carbon-12 as well. And that's why this missing contextual information is really important. If we're going to use something like describing something as isotopically deficient, I have to say the isotope is deficient, or isotopes. And actually, if it's deficient, it's relative to something. What's it relative to? Is it the natural abundance, or is it something else? And natural, that comes back to this, well, how does that relate to the normal material for a standard atomic weight? Are they the same thing? Or is there something different about natural and normal? And it's sort of an implication sometimes, at least from my reading of terms in the Goldbook, that there's a single natural isotopic composition for elements. And well, that's not the case. We've already seen with oxygen, isotopic weight changes where oxygen comes from. Sometimes terms are just not clear. There's isotopically substituted, which has got this phrase, essentially all the molecules, which is lovely, but what does it mean? Is there a cutoff? Is it 99%, 99.99%, more than 50, measurably different to natural? Who knows? So a bit more clarity in these things would be really useful. In terms of progress in the last year or so, we are getting there. We're writing this technical report. There's a lot of words in it. We have 50 quantities, but if you whittle down the synonym to just the ones that are actually different, you end up with about 20. And there's 60 other descriptive terms, fractionation, depletion. Reasonably recently, we decided we're probably going to include terminology related to isotope dilution mass spectrometry, because we're talking about isotope traces used in environmental studies, an isotopic spike used in IDMS, same kind of thing. So covering that kind of useful. And then mass fractionation correction models actually measure by a specific instrument. So they're useful. So in summary, isotopes and measurements of isotopic composition of elements are important. For me anyway, maybe not to you. The field is full of confusing terms, unclear symbols, lack of clarity. People love shoehorning everything into their quantities. There's not just delta with what the reference is, it's about the isotope. If you've got more than two stable isotopes, maybe you need both isotopes in the ratio you're specifying. You have to say the material it's in, the matrix. Yeah, and people just put it all on the. And that just ends up being really confusing, and it's not very helpful if you're trying to make this machine readable. IUPAC projects have attempted to deal with this, make it better, and we're getting there slowly. And the key thing here is that when we're combining isotope ratio measurements from different sources, or some AI thing is scraping data from across the internet, quite nice to know that the delta values it's pulling together can actually be compared. If we measure delta 18O versus VSMO or versus VBDB, these are two different references. They are give you very different numbers, the same material. So that we are clear and transparent. Thank you.
Quick question or comment. You said there are many different confusing terms. And in my opinion, I'm not sure if this is everyone's opinion, I think it is very important to have all these confusing terms in the Gold Book, if only for the reason to deprecate them. I think it's much better to have a confusing term in the Gold Book and say, yeah, some people use it, but please don't use it, than not having it there, and then people don't know what to do with the term.
I agree. That's why this technical report that covers everything, rather than just we think you should do this, is really important. It gives that context. It gives people like an encyclopedia of like, oh, someone's mentioned that term, and that's what it means, and it's equivalent to this thing. That's really useful. So I completely agree.
Yeah, it's not a question. I think it's a really good, obviously, project because I'm involved with that as well. And hopefully we are going to get this other project finished. I think it's not all gloom because I don't think it's worse than it was in solubility. And obviously, Wolf has got a publication out on Henry constants. So I think the question more is, are we going to get the buy-in from the community and adopting whatever recommendation we come up with? And that's just a plea to look in the core book at the end and the recommendations.
Absolutely no point in recommendations that nobody. What would be the point? But also comes a, if you write it like this, if you do use this term, it's better because that term is not clear. Because that kind of educational aspect maybe encourages rather than so.
Back to us.
Hey, thank you very much. Yeah, so as I said to a few people, the great irony here is my day job, as it were, chemistry-wise, is inorganic synthesis to make small molecule activators. But actually, what I'm here to talk about is obviously something units related. Jeremy just sort of said talk about Unicode, so that's what I'm going to do. So I'm going to point out that as well as being lecturer at the University of East Anglia, I'm also a member of the LaTeX project team. And that's really what, in many ways, what brings me into this, although I bring obviously the chemistry knowledge as well. So I'm going to focus in on why we'd want to use Unicode. And I'm going to talk about one symbol in particular that's been a bugbear of mine for, I don't know, as long as I've been using LaTeX probably. And the one that I've battled and got into Unicode and sort of used that as a framework to talk about why we want to do that and why it's important for data reuse. Okay, so start off with a quote from someone who, if you're into your computer science, you'd have heard of, Don Knuth. So obviously, copies of the Unicode standard have been the most crucial and most heavily used references in his personal library for many years. So Unicode is nowadays pretty familiar to most people. It's the way that we encode characters in computer programs. But when it was introduced, it's a very revolutionary idea compared to the previous approach with 7 and 8-bit data, where you use what are called code pages. In other words, you pick 127 or 256 slots, and they're the slots you've got. And if you want to change what you're doing, you have to change what the slots mean. So I'm going to take this as my example. So delta H for a reaction in the standard state, and it's got a very nice looking standard state symbol that you will find is in the Green Book. And if you do anything with the OUP, you will find you can find a symbol that you can use to do that in word processors and things. We'll come back to where that comes from. But try typing that in anywhere else. You will find this is quite challenging. Why is that? Well, because there isn't, or there wasn't, or there isn't yet a Unicode slot. There isn't an agreed position how a computer is going to represent it. So I'm a LaTeX developer and user, so I am going to put this in using LaTeX, and this is what it comes out like in my presentation done here in Beamer with the font I've got set up. Except that it turns out is not quite the same as the symbol you had on the previous page. You might notice the circle's a bit ugly and things, but we'll think a little bit about that. But how have I done that? So my LaTeX input looks like that, where I've got this command. Well, I've shortened it. It's normally not that short, but I wanted it to fit on my slide. That's how that looks, and that's fine in LaTeX. But if I wanted to copy it into a word processor or whatever, or into a web browser, could I do that? Well, what's the definition of that? It's this. Lots of stuff is going on. What I'm doing there is I'm lining up two things. I'm lining up an N dash, or actually it's math mode, so it's a minus sign, and a circle. So problem is that doesn't, because from as the computer's concerned, that's two things, and they've got nothing to do with a standard state symbol. So if I try to copy paste that, it won't work. If you try to interpret it, it won't work. So my problem with that was, well, really you want to be able to have a defined position. Also, because I'm sticking two things together, that the look, as I say, is slightly wrong. So yeah, the problem is that's how I do it, because I've worked hard at getting it right and trying to produce something that has been used in chemistry publications in a sort of pre-digital age routinely. So that's that one. But other people, well, if you look in the Green Book, it says if you can't use a proper Plimsoll sign, use a circle, which is fine, except it's not the same, and then that might be confusing in other places where the circle might mean something else. And then people just do all kinds of rubbish, like just use a 0 because that's what they can find on their keyboard. I mean, we all know that people use a 0 for degree C as well because they can't be bothered with superscripts. But the point is, here they actually can't find the right symbol easily, and certainly if I say once you go outside LaTeX, very difficult to do that unless you happen to have the right setup from someone who's done the work. The other way is to use a predefined font, and that's actually where the symbol I've got in my reference version comes from. So you can use a specially designed font, and hopefully it's been designed by some font designer who's asked what it's supposed to look like. If they've done a good job, it'll match everything else you've got. So this one does look a bit nicer. It'll be consistent between documents, because of course if you use the same font, it will come out the same, but it doesn't have a semantic meaning. So there are two ways that can be done. So either it's a classical 8-bit font, which actually this one is, and so that symbol is in the position for whatever. I don't actually know because I've just copy pasted it. Or if it's a Unicode font, Unicode has lots of space, and there's what's called the private use area, which is like the Wild West. It means we have no idea what this symbol means. It's just there. It's completely arbitrary. Do what you like. So looks better, and you say this one you can use in a word processor, and then I know that because I've been helping someone I've been proofreading some chapters for the new inorganic chemistry textbook from the OUP, and they have that available, but done in a way that, again, that text can't be copy pasted anywhere. It doesn't mean anything to the computer. So we want a better solution, and this is where Unicode comes in. So Unicode is an idea that comes from the, late 80s originally, but sort of codified in the early 90s. And the idea is using some clever tricks, we can have a space for, millions of characters, but I'm going to say thousands of symbols. We can have more space than we could ever possibly need for all the flipping emojis there are in the world, apparently. A long-standing bugbear of people in this area is that emojis get in very easily, but let's leave that aside for the moment. Lots of space. The point is, it gives us the possibility of defining all the symbols we could realistically need for lots of different kinds of human interactions, not only in science, different languages. There are many languages which haven't been used in the digital world or been used only in special areas, and so there's lots of possibilities. And additions are made in each release. I was saying to people earlier, there's a release, the Unicode consortium nowadays have a release once a year where characters, or some other code points are added. So this is all relatively straightforward in a sense, but you need to have a strong case. Now, what do I mean by need to have a strong case? So the Unicode approach is that if something looks the same as something else, you should use the same look. And some years ago, they thought they'd added standard state symbol, which is this. So this is a medium circle with bar, I think it's called. And there are lots of other circles with a bar at different angles and different variants. And the math is done by computer engineer people. And they say, oh, it's covered. And there's a note in the current Unicode specs that say this is used in chemistry for standard state. But when you put it in as designed in a superscript position, it's just wrong. It's the wrong symbol. So I had great fun arguing about exactly this. This is just the wrong symbol. It's not what's required. So you need a strong case. You have to show that symbol is used. It's got meaning. It's not just you, going off all on your own, unless you're doing emojis, per se. It's not a fast process. It takes some time. There's a whole formal process. I've got the thing here. You have to write a formal case. There's a required format. They go through review. If you get through, it takes ages. But we did get somewhere. So I was involved here. So I actually got involved mainly. There was also some people interested in adding some other chemistry-related symbols, and these were all arrows. But I piggybacked on the back of there because I'd been after the standard state symbol for more than 15 years. And you'll see provisionally assigned to throwing 10 code points, and we have 2B96. Medium, small white circle with horizontal bar. They wouldn't have plimsoll mark. They wouldn't have standard state. That's the description I was allowed to come up with. So yeah, really catchy name. Medium small, yes, because the other one's called medium, or so I forget exactly why, yes. And then you see we've got arrows. I've abbreviated the list, but long right with arrow, blah, 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 blah. You'll see that's a reversible arrow, long right was wrong, left was is reversible. So again, you weren't allowed to call them because they can't have meaning. They have to have a description of what they're supposed to look like, etc. So it's present now. That one's now present in characters approved for publication in version 17, which should be out, I think, in the autumn. So there will be an official position for that character, that code point. That's taken about 2.5 years to get that sorted. That doesn't mean that it'll show up in anything. It means that I've got something into the official spec. Once the slot is stable, you can get people to design glyphs and add to fonts. But in specialist areas, when you're looking at specialist glyph, people often just take whatever you provide as a reference and just basically copy it. You will see this with a lot of mathematical stuff that like there's script style stuff for maths, and basically they all the other fonts use the Computer Modern one that was done by Don Knuth in the early 80s, and basically they're all the same because people don't really want to redesign things. And honestly, a circle with a bar in it looks like a circle with a bar in it. It doesn't really have to match anything else. So it's just a question of convincing people to do it. It's not, but that isn't fast or predictable. It depends on people designing fonts and getting people to take action. It takes me to meaning. Symbols can have multiple meanings. We've heard that. The other aspect here is getting what's called intent. So once we've got things in, once they've got a defined character, can we give them intent? If you're converting from once you've got Unicode character points, you can start to think about converting to MathML, which is very important in the accessibility area, which is what the LaTeX team are interested in at the moment, because there's a real pressure for lots of reasons to be able to describe content in that way. And intent is something that is now available. It's not been officially ratified. I was talking to one of my colleagues on the team about this, but it is now available in screen readers, so it's sort of de facto available, even if it's not actually in the standards. And so that's really what I thought I would say about Unicode. What I'm trying to say here really is that if we want to be able to represent concepts that aren't currently covered in the Unicode standard. We need to be getting a case together to get them in. We need clear reasons. We need to be clear what we want. And then somebody has to do the grind work of writing very boring reports, showing that the character is needed, showing why it's not different from everything else, and dealing with these very picky things like what you're going to call it, getting someone to do a reference design, etc., to get those into Unicode, because once it's into Unicode, at least in principle, it can be used in a web browser, in a screen reader, in a word processor, on your phone, wherever. And that's, if you want to be talking about data reusing information, that's really important. It's not a quick process. So as a group, I think we should be working out what things are missing and not trying to pick them off one at a time. Get a block and go to Unicode, the Unicode consortium, with a coherent proposal. With that, I'll just thank the people who've helped me out here. David Carlisle, who is a co-member of the LaTeX team, works for the numerical analysis group and is my sort of key go-to person on MathML in particular. Neil Soffler, Murray Sargent, who wrote the Murray Sargent used to work for Microsoft and wrote the equation editor in Word, and Asmus Freitag were involved in me. Well, they led the efforts on those symbols, getting them into Unicode. And Barbara Beaton, who used to work for the American Math Society, now retired, who is my go-to person on Unicode. She was very heavily involved in things like the Stix fonts development, and so knows a lot about this area as well. And thanks everyone and for your attention. Yeah.
The plimsoll symbol has been used for decades, so yes. Typesetters must have had a way around it, or they must have had a solution.
So, well, obviously, you look back. So, digital typography goes back to the late 70s, early 60s, 70s, when you got the switch shift from things like linotype machines. On linotype machines, whatever, yes, if you'd have the right presses and punches, and you'd be able to typeset it. It's when you move away from that, it got difficult. As I say, OUP clearly have something because they've got this font that's got a symbol in. Other publishers, I don't know. I mean, the RSC, I think, have something as well, but there's very limited support. As I say, I think a lot of it in LaTeX is done by overprinting different symbols, which you can, ultimately, you can always, if you have some symbols and you can overprint them, or you can get a graph, someone draws it and you've got a graphic, you can include a graphic, and when you print it, or you put it in a PDF that a human's going to read, it doesn't matter that it's not part of the font. So it only matters when you're trying to reuse that, or if you're trying to get multiple people to do it who aren't experts.
Oh, well done for getting it in there.
Yeah.
Okay, fantastic. So you have a treat, an unscheduled presentation. So I will call up to the stage very shortly Virginia Murray, who is a member of the CoData Executive Committee. In her day job, she's head of global disaster risk reduction at the UKHSA. So a very important person, and indeed you are, Virginia, and involved in lots of activities globally, particularly with the UN system, but elsewhere. I mentioned she's a member of the CoData Executive Committee. With ISC and UNDRR, she's chairing an activity to develop, which has developed and is now developing a second version of the hazard information profiles. And I think that's what she'll mostly talk about. Virginia is extremely good at drawing people into this activity. So Richard has been leading the activity on chemical hazards. And so watch out, Virginia will recruit you. She's also one of the co-chairs of an activity that CoData has with UNESCO to prepare a set of policy documents, guidance, and a checklist for data policy in times of crisis and how we share data more effectively, promptly when an emergency happens. The hazard information profiles define, Virginia will explain this, but I'm going to try and link to the topic of the day. They define a set of hazards, things that can go wrong, bad things that can happen, And that's the official list against which countries are obliged to report their Sendai losses. So in a sense, we can think of the hazard information profiles as defining the thing that has to be measured. And what goes into the Sendai reporting are those measurements, mostly in countable things of the loss. Sometimes that's in currency, sometimes that's in people, sometimes it's in livestock. I don't know whether they do it in terms of proportion, percentages of arable land lost or flooded, etc. But and Virginia's looking at that. But I'm trying to there establish the link between the topic. Virginia, you have 10 to 15 minutes, and then we'll wrap up for the day. Thank you.
Thank you, Simon. Jeremy, I feel very cheeky. But this is really an opportunity to say huge thanks to IUPAC and the RSC, because I've actually published chapters in your various books over the years, but also to CoData, because this is a global effort. Let me take you to earlier this week. Did you hear about 2 ships in the Channel having a little bump? Anybody heard about it? No, you didn't. Probably one of the biggest fires that we've had recently at sea. Really a massive maritime event off Hull with huge fires and real concerns. Fortunately, not as terrifying as we thought initially. But these events are happening everywhere around the world all the time. And we need good data. And to get good data, you need good standards. And if you need good standards, we need good chemists. So let me just take you through this, if I may. 2015 was a great year. There was a global vision by the world's UN member states who adopted a Paris Agreement on climate, which you might have remembered that there's been another hiccup that one country is dropping out again. I couldn't tell you which country. But we've also got the Sustainable Development Goals. I'm sure you all know it, don't you? Really important. But to me, the magic was the Sendai Framework for Disaster Risk Reduction. And I had the great privilege of being the Vice Chair of the Science and Technical Advisory Group to help to support that work. You'll have noticed there were previous agreements like the Yokohama and the Hyogo Agreement, but we went back to Japan because on the 11th of March, 2011, some of you will remember that only 2 days ago, it's now 14 years since the event, there was an earthquake, a tsunami, and the Fukushima event. Oh, there was a few volcanoes and chemical fires and all sorts of other things that happened in Japan, and approximately something like 18,000 are thought to have lost their lives. The recovery from it is still ongoing. But Sendai was the place we went to get this agreement. It's a simple document, 50 formal paragraphs with lots of subsets. It talks about reducing mortality, affected people, economic loss, and the damage to critical infrastructure and disruption of basic services, health and education being core. But also increasing each country's knowledge of what their hazards are, how important international cooperation is, and the availability and access to early warning for all. Such important words that we need to think about at a time when the world is pretty difficult. It links to the Sustainable Development Goals, and they cross-cut so they can talk to each other, so they can communicate. But the only way to do this is to improve how we report disasters. So the Sendai Framework Monitor was set up, and when we went to the first meeting of its reporting in 2018, we discovered that countries found it very difficult to report on an all hazards approach. And all hazards sits inside the same Sendai Framework, where it talks about science, to strengthen technical and scientific capacity to assess disaster risks, vulnerabilities, exposures to all hazards. Really vital that we try and understand those hazards. So I was given the great privilege to be the chair of the group in 2019 when we set it up. And thank you, Simon, for all the support that I've had from CoData and many partners in the International Science Council to develop a hazard definition and classification review, looking at the global lists of hazards everywhere. I can't tell you how busy that was, but then to build the hazard information profiles published in October 2021, still at the time of COVID. To do this, we had an incredible network. You will see CoData is there, but actually all the international science partners of the International Science Council are key, which is why it was with great fun and privilege I turned to Richard for his support from IUPAC. We work with the UN, approximately 40 different UN agencies and organizations, of which the World Meteorological Organization you'd expect, the World Health Organization, the Food and Agricultural Organization, and many, many others. They are all committed to having a common system for identifying hazards. But we couldn't do it without linking to our insurance development partners, the Insurance Development Forum, to make sure we got some of the business type aspects. And I can't do it unless we have communities. Communities are key. But when we had our first meeting, we had many volunteers and we reached out to many. It has been a real global effort, and you can't read this, but we had a very clear inclusion criteria of what the hazards are, and we will be sharing these slides with you later if helpful. So after huge debate and much discussion, we ended up with 302 hazards. I have no idea quite why, but that's what we ended up with. We obviously had the classic hydrometeorological hazards, the extraterrestrial ones. Yes, we do get meteorites and UV, ultraviolet. And of course, the geological hazards, which other people are very much aware of. The environmental ones, which included desertification. We had the chemical ones. Now, for the chemical ones, this is where I put my hand up for all that I'm a medical toxicologist and have worked in poison centers and have worked right at the front line with many of these things. I turned to my friends in the World Health Organization, but then Richard came to rescue me. He brought in the future, and I'll explain a little bit of that later. But we were allowed to bring in the biological hazards. Do you know, the partners that we were working with said, HIV/AIDS, is that a global disaster? You can see that the advocacy that was needed was pretty massive, and we haven't necessarily got it right, and I apologize for that. But we included the technological hazards, such as building collapse, dam bursts, power outages, supply chain failures, cybersecurity, waste. Oh, think about the healthcare waste with COVID. Oh, what a mess. But all transportation accidents, of course, and maritime accidents, such as the one we've just had in the Channel. But for completeness, we were allowed to include societal conflict, explosive remnants of war, financial shock. So what do they look like? They're really boring. I'm so sorry. We've tried to get the best definitions at the highest level of the United Nations. So the particular body that was involved, we've gone to them. So flash flood, World Meteorological Organization. UV radiation, WHO, although WMO are complaining that we haven't used quite the right terms, but it's the people who are having to use it. Earthquakes, huge amount on that. Household air pollution, such an incredible impact upon the world's health, this time WHO. Lead, it survived, hasn't it, Richard? It made the cut after we went to GHS, the globally harmonized system for chemicals. You turned what we were doing in chemicals into something sane. You have future-proofed what we've done. Thank you, Richard, and the whole team in IUPAC who've been helping us. It's been an incredible achievement, and we will make it much stronger. I'm not going to steal the thunder when you come to explain it, but thank you. We couldn't have done it without you. Snake envenomation, that got through. That was, I think, incredibly important. Think of the number of snakes and the problems that we have with it. Oh, what do you think about cyberbullying? That made it. I think it's really important that we got that in. And I'm very relieved we got violence in. And violence will survive for next time too. So what we knew was that it had to be used actively by policymakers and scientists, and we've done user surveys and all sorts of things, but we were told to address cascading and complex hazards and risks. And we know, much to our surprise, that what we've achieved with these hazard information profiles support Sendai, the Sustainable Development Agreements, the Paris Agreements, because they provide a common set of hazard definitions. Thinking of how difficult it was to get Unicode to work, and Philip, to get your measurements to work on oxygen, I was a bit shocked as a toxicologist, thinking, oops, I didn't know that. So our job is always to listen. And in every one of these huge UN meetings that you have and the UN agreements, you have a midterm review. You might like this. We were absolutely thrilled when we were described as groundbreaking. They're all online. Please have a look. They're not perfect. By gosh, we know they're not perfect. We haven't the skills and expertise that you have in building standards in the same way. We would love your help. Oh, sorry, Simon. Yes. We would love your help and comments. But we know that the future is really important. We know that we need to get people to report effectively on loss and damage. We need to implement a comprehensive and inclusive approach to the development of disaster risk reduction strategies, and that we have to have this multi-hazard early warning system and understanding what we're going to do. So I was again asked to chair the steering group. Why me, Simon? Anyway, why does it matter? Because on the 23rd of March 2022, Antonio Guterres, as the UN Secretary General, called for a 5-year programme for early warning for all. We can probably do it for the hydrometeorological events, but we are really struggling for many others. Richard and I have been talking about the explosive hazards, the explosive agents, and I'm really glad to say that all of you who've travelled have been part of early warning. You went through airport screening. Did you know that airport screening is a way of us doing early warning for explosive hazards? Well, that's one way of doing it. But we've also know that disaster losses and damage tracking is absolutely key. There's a huge programme of work with the World Meteorological Organization, with the United Nations Office for Disaster Risk Reduction, and for the UN Development Programme, that this is coming in towards the end of this month. We haven't got the second round of HIPs ready, Richard. Oops. There's a huge amount of hazard parameters, effect and impact, and statistics and context, and trying to make these definitions as clear and as sharp as we can. And right at the heart of all that damage and loss work are our hazards, and the work we've been doing with WHO, and the guidance from disaster-related statistics. This is a UN Office of Disaster Risk Reduction slide. Richard, we are thought to be useful. Terrifying. But let me turn to the other thing that was mentioned by Simon. Thank you, Simon, so much again. Huge thanks to Francis and many others, and to Richard. We've been working on data policy for times of crisis facilitated by open science, something that I also thought I would share as I knew Simon was here. And this has been an effort that we've been doing, and we've just had a recent webinar. But what are we doing with it? You asked what's next. All of us are looking at what's next. So we will, on the 25th of March, do the soft launch of the checklist, of the guidance and the fact sheet, and a hard launch in June, when we will also launch the hazard information profiles at the Global Platform on Disaster Risk Reduction in Geneva. Your help is part of the whole work that we've been doing to try and take this forward. Please know that your effort to even find an underground symbol, is that the right way to describe it, sitting on top? I rather liked to see the underground, London Underground, making it. Just think of what we're trying to do for something that is even more terrifying. But finally, I just thought you might like to see, we publish a Global Hazard Weekly Bulletin, which you might want to see under the UK Alliance of Disaster Research, just to know what the horror stories of the week are. And by gosh, there are plenty. Thank you.
Hi there. Question. So the hazard profiles that you're creating, who do you see as your audiences for those?
Hello? Yes. The audience is you, me, policymakers, scientists, somebody's doing their PhD. It's people who work in the National Disaster Risk Management Agency. What are the hazards you need to look for? There's no point if you're in the middle of a land-bound country looking at coastal erosion or sea level rise. But if you're in the midst of Indonesia, where you have over 7,000 islands, it's a huge problem. You have to fit the hazards to your needs, but also it's listening to them. And in our user survey, we had a wonderful statement from one of our islands in the middle of the Pacific saying this is a really useful way of deciding what they need to be prepared for. It was incredible how enthusiastic the replies were. But it is for you and for me.
May I add to that? I mean, my understanding as well that some of the motivation behind this was that there was already a list of possible hazards against which the countries had to report in the Sendai process. So a primary user are governments or statistical agencies who are responsible for doing that reporting. But what Virginia, I think through force of will and the support of ISC and UNDRR did, was to try and align these with scientific knowledge. So the hazard information profiles as they now exist are a summum of the state of scientific understanding of these hazards, combined with and endorsed by the UN agencies. So there was a process of bringing together scientific expertise, and it's not that the UN agencies didn't have scientific expertise, of course they did, but in helping them engage more with the scientific community, and that was the link that the International Science Council and to some degree CODATA provided.
Amazing. This is just fascinating, this work. So I was just thinking, I come from Greece. So one of the most, I don't know if you've heard about Santorini now, and with the island, two islands closed down for quite some time. And I was wondering, do you also produce recommendations on how countries should tackle hazards? Because there was a lot of debate in Greece that the schools were closed, the people weren't allowed to go to Santorini for quite some time. They were expecting a big earthquake to happen, but it didn't happen. And so now everyone was a bit skeptical. Should we open up again? Should we not? Do you produce general guidelines about stuff like that?
I think that's a challenge, and I'm very glad I'm not a member of the Greek government. I think they've been having a busy time lately anyway. What we do include are messages about risk management. And I try to bring an idea of those of you who've traveled that you've all been through airport screening processes for explosive devices. And so we're finally going to include that into a risk management part of our new hazard information profile. We can provide general guidance. We can't do it specifically because, of course, we've been very worried about what's been happening in Turkey with the terrible earthquake on February the 6th, 2023, where they had two massive earthquakes on the same day that were just awful. And it's really hard to make these decisions. And if you evacuate people, how do you make it possible for them to return? I'm sorry, in chemical incidents in the past that I've been involved with, we've struggled with that too. It's never easy. It's so important that you think of the exit route as you begin the entry route.
Thank you. Well, good morning, everyone. So really, Jeremy just wanted me just to sort of come and say and put a few words about sort of the role that the RSC plays within IUPAC, and particularly the RSC-IUPAC committee. So throughout sort of the morning and potentially this afternoon, you might see a few more faces joining us. So Firstly, who I am. I've obviously been sitting here and moving around sort of throughout the day yesterday. So my name is Andrew Shaw, and I'm the International Engagement Manager here at the Royal Society of Chemistry. And so that means I have the honour of working with lots of our international partners and very much around the world. And very much responsible for the liaison between the RSC and our various membership, the federations that we're a member of. So the RSC is a member of UChems. We're also a member of Commonwealth Chemistry, and of course for this audience, very much a member of IUPAC. So the RSC is the national adhering organisation for IUPAC on behalf of the UK. And one of the responsibilities is to work with all of these sort of people who are on the various divisions, committees, and various roles and projects that IUPAC does, where the RSC and the UK are very much involved. And so one of my roles is to sort of convene the committee, and the remit of this committee is pretty broad, and it's been in existence for many years. I've only been in the role 3 years. I know it's been around for a lot longer than that. But this is primarily as an opportunity for the people working on our divisions and our committees to get together about twice a year to meet each other, say hello, and just sort of find out what each other is doing. And so that's the primary purpose, connecting people working within IUPAC with each other across the UK. And equally important, as I said, the RSC is very proud of its role with IUPAC as the NAO. And we feel because of that, therefore it's important that we have the representation on the various bodies within IUPAC. And so we make sure that every 1 to 2 years, we make sure we have the relevant people, try and bring new people into the IUPAC sort of family where we can as well, and to sort of future-proof that as well. And there's also an element of, I think, promoting within the wider UK community what IUPAC is doing as well. Of course, IUPAC, as we know, has a vast involvement in a number of different sort of proposals, services, policies, and so if there is anything that IUPAC is doing that might affect the UK community, then that's really important for us to sort of be aware of that. If equally important is how the RSC and IUPAC can work together, and I think in a number of ways over the years we have done that in ways of mutual benefit. This year is exciting in that we have the IUPAC World Chemistry Congress, but also the General Assembly, which happens every 2 years. And as part of that, as the NAO, the UK will be putting together a delegation of people to vote at the council meeting, which of course is the ultimate decision-making body of IUPAC. And importantly, as I said about sort of future-proofing and looking to the future, I think for a number of years, probably I think since it started, the RSC has got involved with the IUPAC Young Observers Programme, which is about sort of bringing early career chemists, whatever that is for them, or whatever that sort of means for them, to observe the various divisions they might be interested in, and also to understand more about what IUPAC does and the impact that IUPAC has, and its role as well within our global community. So there are a number of people in this room who are also on the committee. I have a wonderful picture of our chair, Jeremy, up there. I thought sort of as our convener of this meeting, but also his dual role with chairing that committee for 2 or 3 years, I think, Jeremy, I think, isn't it? You've chaired it, I think. Is this? Okay. And we also have, and some of them, I don't think I'm going to forget anyone, so we've got Phil, I think is at the back. Have I seen Phil? He's on our committee. And we've got Ian, there's Ian Williams, Ian Bruno, sorry, 2 Ian, sorry. And then Derek is at the front, so I'm checking I've not missed one off. So they're the people who are here for this meeting. I said there will be other people joining us this morning, and we're going to be upstairs for our committee meeting while you're having your various discussions on about the various groups, and then we'll very much invite everyone down to join us all for lunch, and hopefully some of them might be able to stick around for the afternoon too. That was what I was going to say. If anyone wants to ask me any questions, of course I'm happy to. Otherwise, come and grab me during the break. But otherwise, thank you very much for your attention. Thank you.
Thank you all for being here. Sorry that I wasn't with the dinner last night. I went to join my father for a different celebration. I think that lots of useful discussions took place yesterday, a lot of different insight, slightly different talks today, and more opportunity for discussion. One of the key people who I think became even clearer from the various discussions yesterday, a key person who isn't here is Stuart Chalk. I have asked whether, because he did offer to be available to do things, for him to be online. I've asked whether around 11 o'clock or at 2 o'clock, when part of our discussion sessions, whether he will be available to show two particular things that I think are important. One of which is the digital green book in the Jupyter book, and the other is the work that he's done on collecting together the unit systems and the spreadsheet stuff. So we may modify slightly how we do it depending on when he's available, but given there were the 4 tables yesterday, and I think the various useful discussions came out of that, but one of the things that I realized from that is that I think the next set of discussions we could usefully do today would be for the PSDI group to talk to the drum group about these units and how we can start building together, and PSDI might be able to allocate some resources to working on that, which will be great. And the other is around some of the workflow issues and dealing with terms and interactions between the gold and the green book. And I think that would be useful for those two groups to talk together. I'm hoping that we can do that after Stuart, who normally does get up quite early in the day, and therefore you may well be able to present at around 11, as it's only 4 hours time difference to the East Coast at the moment. But we're just waiting for a reply from him. So a bit of flexibility around that. Those discussions, there'll be a smaller group of you there whilst the RSC committee meeting takes place. Then we'll all come back for some more discussions. In the afternoon, Simon Hodson has volunteered to say a little bit about CDIF, which is this framework for bringing together some metadata. I know in PSDI, Aline has been very interested in looking at that. It's really quite comprehensive, but very flexible. So we'll do something around that, and I think that will highlight some really interesting things that will be useful across the board. There a discussion between Drum and Goldbook around how we might access terms. So as Juan said yesterday, the search system within the PSDI front end, how could that interact most readily with terms that are already available in the Goldbook? That doesn't need us to resolve the DOIs because we know there are identifiers underneath, and as we're all part of the internal family, we can get at anything we need to get at. The question is what would be most useful to do and how to do it. And again, Stuart will probably be a key person there. So the more that various projects can help Stuart do some work, so to actually provide some more people power there, that's going to be a really important thing to do. The other thing that's just occurred to me is that, so Andrew mentioned about how IUPAC is formally linked, sorry, how the RSC is the adhering organization to IUPAC. We won't talk about where the money actually comes from because it's a bit more complicated even than that. IUPAC is a member organization of CoData and has a representative there. That's sometimes me, and sometimes, depending on geographically where it is, it's been Richard to attend meetings. Sometimes we're both there because Richard is also the New Zealand representative. There is a UK representative of the UK on CoData, who you heard from yesterday, Doria, but I'm not sure the RSC is actually a member of CoData. It's a pity that I don't think Richard could be here today. We could have raised that with him, particularly because on that data side, I don't know what the cost would be, but maybe as our international representative, that you and Simon could have a chat, because it does seem to me that that could be rather important. We reach out and have the connections in CoData to all the international unions, but the individual societies we haven't particularly connected to. And I think the RSC's open data policies and so on, and open is very well aligned with CoData. That may not be so true of some of the other organizations that are perhaps not either more focused on their national work just because of their scale, or focused on some more commercial operations. But I think the RSC is in a very good position, and if it didn't cost us too much, I would like to push for that. That wouldn't quite come under our committee, but it would come under your work with the Commonwealth. I mean, we work with the Commonwealth Chemistry, the Pan-African Congress, lots of interesting things that I think RSC could bring to CoData where there's an overlap there. So I think that's something that we could maybe make a recommendation, but the two of you could have a chat. In the light of some with CDIF, are there any topics that, having heard these talks yesterday that range from specific to general things, that people feel that it would be great if they could discuss with another group, and therefore we can put those on the agenda for this afternoon in the discussions and maybe configure the discussions. Any other topics that people would like to hear about how another group is doing something, or have they got the same challenges, or topics that we just haven't touched upon that are critical to the mission of Drum, PSDI, Green or Gold books? Anybody else would like to put forward something? If you can think of something now, shout. Otherwise, maybe actually, because I'll be involved in this committee meeting in a bit, maybe Richard, if people could just tell you if there are any topics, then over lunch. This was our usual system when running some of our other networks. We ask all these questions and then get some input in, and then over a tea break or a lunch break, we try and reconfigure sessions to do that. So if anybody's got topics that they think would be really good to discuss, it doesn't have to involve everybody, just what groups would be needed. If we could just tell Richard sometime this morning, and then we'll try and sort something out this afternoon. Speakers from yesterday and today, it will be great if we can put your talks up in some form or other, PDF or whatever, to be publicly available. Appreciate that may not always be possible for everything, so you might want to redact things or whatever, but I think we've got copies of all of them. But Colin and Agnes definitely need copies to be able to make up the report on the meeting. In the report on the meeting, they will not, we can link to any slides that are available, but for those of you who might be concerned about what you can say, making it available to Colin and Agnes is not the same as making it available publicly. But if you can let us put them up publicly, that'd be great. If you have concerns, let's discuss that. And I think that's everything that I needed to say about today. Just waiting and say for Stuart to reply to when he can use the presentation on these two areas.
Okay, thank you. So yeah, you mentioned the title. That's what Jeremy gave me. So I think my role here is basically a warm-up act. Right? I've been asked to say a little bit about what crystallographers have done over the years. Certainly standards for terminology. There's a sort of perception out there that crystallographers have been doing this for years. They've got it nailed. I just tell you what. Translated and you'll all be fine. So I'll tell you a bit about that, and I'll tell you a bit about some of the challenges we're also facing now. So I do bits and pieces for IUPAC, but I have to say, and I hope you don't string me up for this, my allegiance probably lies really with IUCR, which is the National Crystallography. It's kind of a sister organisation, if you like. So much of what I'm going to say here comes from the perspective of the international union, and I want to talk. I come at this mainly from being a data-centric kind of guy. So I head up with Juan, who's over there, the PSDI, who are sponsoring this event, and that's all about gathering and generating collections of data. And my passion for doing that has come from being a crystallographer. And essentially from this guy, my hero, J.D. Bernal, over 75 years ago, kind of started saying, well, we should just pool all our data because we'll be able to exploit it. It's a really sensible thing to do. And yeah, he was right there. This guy was a polymath, as I say, is a complete hero of mine. This was him with his group in 1948, I think, on a group trip to Stonehenge. And this lady here was at that group meeting was Olga Kennard, and 15 odd years later, she founded the Cambridge Structural Database, and that's where much of what we do as crystallographers has flowed from, basically. So. In crystallography now we have a bunch of different databases. These are the sort of primary ones, if you like. So there's the CSD, which is now accumulated somewhere in the region of 1.35 million data sets, structures. And as I said, that was born in 1965. Then in 1971, the macromolecular lot came on, cottoned on to the idea of that being very sensible. There are now well over 200,000 structures in the protein data bank. and also covering the area of inorganic crystal structure, solid state chemistry, and physics. There's around about 300 structures in the ICSD, which started life in about 1978. So there's a myriad of data resources that cover crystallography. This is now quite a famous graphic. It basically shows the exponential rise of the data holdings in the CSD. Right. So this is how the Cambridge Structural Database has grown year on year, and I thought it was kind of interesting to kind of indicate at what points in time technology helped us kind of begin to ramp up the rate at which we were beginning to collect data. Okay, so around about 1980 was when people stopped going to computing centers with punch cards, that kind of thing, and had a great big device in the corner of the lab, which enabled them to do local computing. That was kind of a gear change, and that was the first time when computing really began to make a bit of a significant difference. As we got towards the 90s, all instrumentation was driven by computers, so the automation of instrumentation enabled another step change in the rate in which we could generate data. And then as we got into this century, things like the internet and everyone thinking and working digitally begin to kind of really compound that sort of exponential nature of the growth of data. And that's had an effect on what we can actually do with this data collection. So around about the mid-1980s, we collected this many crystal structures, and that enabled us to say, oh, this is the archetypal bond. So there were people painstakingly went through all crystal structures, essentially investigating them for every particular type of bond length and coming up with standards, if you like, for bond length. So that happened relatively early on, when there was only about 100,000 structures in the database. What's happened as the database has grown is that we've been able to understand a lot more about the actual chemistry, how molecules interact with each other, the preference for interactions. And now we're at the stage really where you can use the data set is big enough that we can begin to use it to predict the way molecules are going to behave in the solid state. These things don't come for free, right? Especially if there's a massive amount of effort that goes into collating and curating and making available these collections. And so I often bring up this slide, which illustrates the different ways in which these databases generally kind of operate and are funded. So Cambridge Structural Database is funded by kind of individual or national scale subscriptions. There's quite a lot of industry use, which has driven the way some of the software on top of the database has been developed. And the big subscribers, and actually the amount that industry contributes to the financial underpinning of that database means it's a lot more readily accessible to the rest of us. And for quite some time, the CSD has not been about the data alone. It's about the tools on top, and it's not just search and discovery. There's a whole load of processing tools to enable us to do structural science on top of the database, and effectively we're paying for that as well when you buy a license. The inorganic crystal structure based database, the ICSD, is more of a business. Again, it's a subscription based thing, but you're paying more for access, for search and discovery kind of access. What kind of do you have structures that look like this? Can I have this structure? That kind of thing. The protein data bank again is a different model. It's more of a foundation, and it's government agency funded, so it's free at the point of access for most users, and generally underpinned by governments, sort of in the three regions of the world, largely speaking: Europe, Japan and the US. And the PDB has become, because of that open access, it's become the core for bioinformatics and a whole range of different digital and data-based science. So it was very clear early on that as we were beginning to generate more and more of this data, that we needed to do this in a structured and standardized way. There were hordes of people in Cambridge who used to take crystal structures in all sorts of different shapes and sizes and amalgamate them into a collection in a standardized way. So the obvious thing to do is to kind of take that out into the community and make it a way in which everyone lives and breathes, if you like. And so the CIF was born, and it started life as the crystallographic information file around about 1990. It was published in 91, and the authors here, with the following kind of reasons behind doing it. It was a standard for interchange between different resources, so an information interchange and an archive. And it was initially presented certainly to the community as a format, if you like, so it's a restricted syntax and a defined format. But the real power of CIF, which has been enduring, is the fact that it's a dictionary. Basically, it's an agreed set of dictionary terms. And that's what drives it and what has made it what it is today. And it was all essentially under the auspices of an IUCR committee. So governance of this standard, the maintenance of it, was built in right from the very beginning. So that's this body called ComCIFs. So CIF was kind of dreamt up in 1989, 1990 or so. It was published in 91, and the ComCIFs committee that governs it and had the oversight of it came into being in 1992. And they look after the various different dictionaries. So it's a bit too small for you to see. These are a bunch of different dictionaries. So there's a core dictionary which applies to everything crystallographic, and then these sort of plug-in extras that allow you to describe very specific parts of crystallography, like powder diffraction or electron density or the likes. So there are subcommittees associated with each of these dictionaries, and they all come under the auspices of ComCIFs, and ComCIFs is the body through which you've got to pass proposals for new dictionaries, for dictionaries to be changed and edited, etc., and for how the dictionaries are actually then implemented. There's another body, so ComCIFs is completely to do with the CIF format. There's like a sister committee chaired by yours truly, which kind of covers everything else to do with data in the crystallographic community, and particularly under the vein of this talk that I'm giving, thinking about FAIR, but it's charged with understanding data in publishing, understanding the role and the maintenance of databases, looking at particularly raw data, which is now becoming more and more significant. Cambridge Structural Database, the ICSD, the PDB, they just have results data in them. Right. So understanding what we do and the link to raw data is important. It has our representative code data, so every good organization should be part of that. Sorry, Jeremy told me to say that. So code data covers a whole range of things. Data matters. It's a misconception now that CIF is a file format. Not. It's a whole information framework driven by the dictionaries that we dreamt up 30 odd years ago. So it's shifted in its first 10 years of its life. It was effectively a format, and I have to say it was pretty much unilaterally adopted as the lingua franca in crystallography within a year or two of the standard being published, everyone jumped on board very quickly. A lot of that was driven by implementation in software that was commonly used. But from 2000 onwards, it's become more of a currency across everything that we do, rather than just saying, oh, here's a result, it's in a CIF format. It underpins the entire process of generating those results, and then what one does with them afterwards. So it's become a form of communication and a framework within which we work, and it fits across everything that we do. So CIF was originally designed, as I say, as an archival format, and it was produced at result stage. Not even showing that. What has happened in the intervening 30 years since it was invented, if you like, is now spread out to cover everything that we do, right from the sample, the physical sample, then through the experiment, does to get a result, then here how one analyzes the result and can derive from those results, publishing format, getting it into a collection, and then results of pooling all of this data together. So CIF really does cover the whole information life cycle in crystallography. So, as I said, embedding it in software was key, and that now actually making sure that that software sustains is also key. So about 25 years ago, there was a recognised need to support the software, which everyone, which is the foundation why everyone uses, certainly in the chemical crystallography subdiscipline where I work. So we have, when I started in the late 80s, early 90s, there were quite a few different breeds of software out there. They've all sort of coalesced into one and been sort of subsumed, if you like, which effectively is an open platform that anyone can use. And there's at least 100,000 people out there using this on a more or less daily basis. CIF has allowed us to build tools on top to ensure quality and understand quality. So validation is a huge element of the success of CIF and really drives the growth of these databases. It's not just the validation of the format that is my CIF file syntactically correct, etc. But it validates the data within and gives you quality responses. And that's because we have a full dictionary that we understand the terms, so we can interpret the actual data and give alerts where there might be errors or areas where the quality is a bit lacking. And getting things into databases has changed in my lifetime. My first paper, I submitted the data in paper format, and I remember photocopying it all out and putting it in the post. It was a package about this sort of size, and some poor soul in Cambridge had to type all of that up. Because we now live, breathe, eat CIF, we are actually able to generate the results in a form that can be easily digested by the CSD. So there's a relatively automated pipeline. I can do within 2 or 3 minutes. I can deposit a crystal structure ready for assimilation into the Cambridge structural database myself, and it's properly embedded into the publishing process. So this idea of connecting to the paper that's associated with the data, and also quite critically, it empowers the reviewing process. So prior to structures ending up in the CSD, as a reviewer, you can pop along and pick up a CIF and assess it alongside the paper that you've been asked to review. So you can actually ensure that firstly the data underpinning the paper is is valid, is correct, and also matches appropriately to what's being claimed in the paper. And you can do all of that as part of the reviewing process. And now there's a really solid link between the data, the results data that's in papers, and the database article. And that's taken a while to get there, but in many disciplines, it sounds simple, but in many disciplines, this doesn't actually exist. This doesn't happen across all of publishing, but certainly within the crystallography sphere, you can write a paper in CIF. So any one of you who use LaTeX and play with Overleaf, where you can basically type LaTeX in one side and the human decipherable, human readable form magically appears on the other half of the screen. We have a sort of analogous thing. So you can basically write your paper or word processor side of it. And in crystallography, we do this all the time. So again, that reduces the error and keeps everything bound within this CIF information framework, which does mean we can readily build a lot of tools. So these are a bunch of CSD tools, as I said, back in the mid-80s, painstakingly measured one lengths and angles to come up with definitive standards, if you like. Now we're using the database to fully analyze our structures. Sort of standards that one sees within the database, through to prediction. You basically plug a molecule in there, an imaginary molecule, and look at what the propensity that would have to form interactions and grow crystals and that. So what we've ended up with is a quality framework, which is based on 100 odd years, but 125 years of doing experiments and developing instrumentation that all works in a harmonious way across the world. 50 odd years of building databases, 40 odd years of using the same software to generate the results. Over 30 years of operating with agreed standards, and 20 odd years of validation tools. It means we have this quality framework that everyone understands and can play by. However, new science is beginning to stretch this framework. So within what we're doing, we're getting more challenging samples, more challenging types of experiments. So everything I've described works very well for a conventional crystallography experiment. But when you start zapping your crystals with lasers or squeezing them in diamonds, the experiments become more challenging to describe. The results become more challenging to describe. And we have a whole range of different ways of doing crystallography now. Just firing X-rays, we can get crystal structures through a number of different methods, and they come up with slightly different levels of quality, but also different factors that one has to consider when describing the result, and the same with different methods of generating the result. Sort of the combination with quantum chemistry, for example. So we now need to begin to think of the reasons why the crystal structure was done in the first place, and what people will use those results for. And those two things don't necessarily match up, especially when you're generating a lot of results in a very high throughput way. So many people's drivers for getting the crystal structure analysis in the first place quite different from the consumers of that data when it comes into collection. Often people just be characterizing their chemical compound. What have I got? What have I made? Why doesn't this fit my And then there are a few things around derive. These ones down my list are focused and involved. But that's quite different, as I say, from how people will consume these results when they're in a collection. And very simply, I might ask, you know, have you seen something like this before, a database? But increasingly, we're looking to get very accurate structural features, and if you've got data that's of varying qualities, the conclusions that you draw when doing these databasing studies can be skewed somewhat. And of course, we use a lot of this now for in tandem with follow-on calculations and quantum chemistry. So again, making sure you're starting from the right point is really important. So it begs the question of quality across the database, and what is fit for purpose kind of depends on the purpose you had in mind. So about 15 odd years ago, 20 years ago maybe, we started thinking about making more of the data available. So this is a repository that we played around with in Southampton, that we're making all of the data available. So the top file up there is the CIF file, but all the other files are files that are generated along the way and give you a lot more information about the experiment and essentially how that result was generated. And the idea behind that is that you can drill down and understand. You don't just get the top level result. You can drill down and understand how that result was derived and everything that's affected it. And this is where we're at today, actually. I'm beginning to really think about the raw data. So everything I talked about, so the raw data tends to be images a little bit like this. They're in binary format. We extract the intensities of these reflections. We go to a position where we think one should be, and then we extract the intensity of it and write it down in a file with an error, and you get about 30,000 of those, and that's what you generate your, that's what you begin to generate your result. So quite quickly, your results divorced from the raw data you generated it from, and as I see here, this is not very clean. Right, there are things going on. So the operator, or the person who's doing the experiment, have a very particular reading. So they selectively pick the data that they're looking for, if you like. And so essentially, there's a lot more in the raw data often that tells you about the properties of the material as a whole, rather than its structure. But a lot of that is lost. And we see quite a lot of this in some of the more advanced experiments we do. We're doing dynamic crystallography, for example. So we're sort of a turning point. It's not normal for us to make the raw data available, but we begin to think about that in the community. So it's a piece of work that we did through ComDat in surveying the community as to whether we should, or why we should, or when we should make raw data available. And it broadly fell into three sort of categories that people were thinking about. You should make raw data available so that you can back up the assertion, the quality of your results, so that you could provide deeper understanding into those results, and that you could use that raw data to develop methods in the future. And so this is an example from my own work where we absolutely felt that we needed to make the raw data available. One day about 15 years ago, we stumbled across the world-beating structure in many ways. It's his phenomenal, remarkable structure. So much so that we had to provide the raw data to the reviewers for them to believe that it was true. And so that's what we've done for the readers. Right? So this is a very grand claim, and therefore it requires the raw data to back it up. Simply just providing the results doesn't doesn't give you enough rigorous sort of underpinning to back up that claim. And then another area that we're working in Southampton is electron diffraction. Right? So for a century or so, we've been using X-rays and looking at relatively large crystals, of sort of microns in size. Now you can basically put your crystals, much smaller crystals, nano-sized crystals, into an electron microscope and get a crystal structure out. This is great. The thing is, a whole load of experimental parameters, which means these results don't fit anywhere inside our quality framework. They're kind of outside of it. The answers are correct, but they're just not at the same the level that we've become acclimatized to over a whole century. So as this technique is getting underway, we have to provide the raw data so that anyone coming across these results can drill down and understand how we derive them. But also, we're developing the methodology. And I know in 5 years' time, we're going to be able to get much better results out of the data we collected. So we need to come back to all of this stuff and regenerate the results. Okay, so it's really, really important to make the raw data available, to link it to the, so this is a electron diffraction. Place where we put the raw data in a public repository, and that means we can kind of come back to it when we know we can do better. And a lot of this is boiled down to us thinking, well, actually, we need to do this in a community level in a more formalized way. So we made a journal to be able to do that. So this is raw data letters, which is essentially enables you to make a raw data set available and add a commentary in publication style on top of that data. We're in the process of building a whole bunch of tools to basically do that check sift type validation, but on the raw data. It covers all areas of crystallography, which is quite expansive. So I'm getting towards the end now. I think the point is we've established a system over a long period of time, which everyone has grown to love and trust and use. And now we're beginning to stretch it, but things are moving in a different way as well. So we kind of set up PSDI with the idea that you'd be able to grow collections of data in a sort of similar way that the crystallographers have done, but more kind of grassroots, if you like. So we can have collections of data in all areas across the physical sciences, and that would enable us to aggregate them and do stuff. And what is now becoming very, very apparent very quickly is that we'll be able to exploit this data a lot better with AI type tools. We'll even be able to do not just about prediction. So there's things that have come out. You might well have seen Nature papers from Google and Microsoft about materials, prediction of materials, structures, and that kind of thing. The algorithms out there can do the job very, very well. Unfortunately, the data that they're working on is rubbish. They're clawing it from here, there, and everywhere. And so there's grand claims being made, but they're built on very poor foundations. And so the results are not terribly credible, but the technology is there and it will work. And the point is we need very trustworthy, reliable, well-curated data, and then these AI algorithms will work. And it will enable all sorts of things. So in principle, you know, we spend lots of money designing experimental setups where you can measure several things simultaneously. If you have different data sets, you can probably just do all of this with AI. So there's a huge power with AI and a lot of promise, but the problem is we haven't got the right foundations to build it on. And what we need to do is think a bit more like the crystallographers have done over the last few decades. And I'd say this is just a summing up slide in terms of thinking about what we do as crystallographers, but also, you know, how it might be thought about chemistry, wider chemistry community perspective. Crystallographers are quite a coherent community. They generally get on with each other, and if someone comes up with a good idea and say, hey folks, let's do this, 99% people will follow. So that has helped, getting everybody on board in the same way. It's also very tractable because the data comes from instrumentation, and so it can be programmed, if you like. It does mean you've got to come to an agreement as to how one takes up data and describes it, but that is doable, or a lot more tractable when it comes to instrumentation. The data standards thing speaks for itself. Automated validation has meant we can develop these collections at a much faster rate. But the role of the IUCR in having these governing bodies that manage the data dictionaries cannot be neglected at all. And so that's where I want to leave it, actually. I think the idea of governance, developing more trustworthy, curated data collections that are governed is the way forward. And we could probably learn a lot from the way crystallographers have done things. And I think that's me. Okay.
So time for a few questions on the UK.
Oh, Joseph.
And almost all of those are not going to be of interest to people beyond our area, collecting that structure. How do we decide what raw data to make? Because obviously there is a cost to data storage, and so you can't say you should make everything available.
Yeah, I didn't have time to go into the details. There's a whole lecture on the findings of how when we surveyed the community. So the protein crystallography community is sort of going down the line of archive everything. It'll be really important someday, and we'll definitely need to come back to it, and we can afford to do it. Chemical crystallography community are definitely not going down that line, and it's a matter of archive and make the data available as and when it's necessary. That's fine, but as you alluded to, defining what is necessary is the problem. So that's partly was the driver behind setting up this journal, and doing so enables us to develop all the tools. So that we're going to have these image validation tools that basically say, have you extracted everything from your raw data? The answer equals no, then you should probably deposit it because someone else will find things of interest in it. So there are tools to come. Thank you to the EU for giving us money to make.
Thank you. What is your understanding of quantum crystallography?
Quantum crystallography is an interesting one. But there are two ways in which it can be used. So we have quantum crystallographic methods where you can essentially augment the refinement of crystal structure. So we compute a wave function and feed it back into the cycle. So you basically, rather than refining balls and sticks, molecules are electron density, right? So you can actually refine the electron density. Advantage of doing that are that you get much better fit of your model. Your model is a much better fit of the actual distribution. So you get much better quality models, but then you've got a quantum mechanical description of the electron density. So you of properties. So quantum crystallography is doing better refinements, generating better results, and that we can do right now. That in the OLEX2 software, for example, click of a button, relatively small system can be done on that laptop in front of you. Bigger ones you might need. That's one part of it. The other part is then what one can exploit through having a description of the electron density from that. So all sorts of different properties
Thank you.
So hi everyone. All your presentations so far have been very serious, so apologies in advance. I don't really do serious presentations. I have some serious messages, but buckle up for some cartoons, pretty pictures and ridiculousness. But then at least if you don't like what I'm saying, you can enjoy the cartoons, pretty pictures and ridiculousness. So I'm going to talk to you about a pragmatic view of the semantic web for the physical sciences. My slides will share. Okay, so starting off with ridiculousness already, but a bit of an outline. So I'm going to tell you a bit about me. I'm going to potentially introduce the semantic web to a level depending on how much you guys know about the semantic web. I want to talk a bit about terminology and units with the semantic web, because that is one of the big points of this meeting. Talk about some of the barriers and challenges that I think are issues both in general with representing terminology and units, but also the wider barriers and challenges of using the semantic web. And I also don't want this to come across, this may come across like I don't actually like the technology. I do actually really like it. I've literally been interested in it for over 10 years. I find it very exciting. I looked at semantic web stuff for my dissertation, my master's, my PhD. I still look at it for PSDI. So I'm not actually negative about the technology, but I do think that sometimes technology can be overused, misused, or not used in the right way to get the best out of it. And that's really where I'm trying to come at it from my pragmatic view. And then I want to talk a bit about where I think some of these technologies can be used really well in the future and where I see certain opening up areas of potential, and then just a few sort of concluding thoughts. So a bit about me. So I'm not a chemist. I forgot to do that in our sort of confessional introductions yesterday, but I'm not a chemist, even though I masquerade around the chemistry department and actually got to wear a lab coat this week because I was in the labs at the University of Nottingham, only to watch people actually do experiments, not to actually do anything funky myself. But I did a web science PhD, which I think is really cool because web science is basically a blend of sociology and computer science, and it really looks at the human element of technology and thinks about things like the web as socio-technical phenomena where the human input and the human way of driving the technology is just as, if not more important than the technical element. And I think that's actually very important when it comes to the semantic web, to AI, to implementing fair data. All of these things are human-based endeavors. And we, you know, Jeremy's brought together all these really clever people together in this room for a reason. We all need to work together if we're going to get it right. And that's kind of where some of my interests have come in. And so I think actually I introduced myself to all of you yesterday, and the only person who wasn't here was Simon, and he does actually work with me. So he knows what I do. So I don't really need to go into that too much. So why am I here? Who recognizes this picture? So I think this is the other Samantha. I guess the Samantha that came first. But quite apart from just liking witches and wishing I was one, there is a sort of point to this picture, is that I think a lot of people sometimes have these misconceptions that we can get magic out of some of these technologies without doing it properly, that these technologies will either belie magic or that they'll happen by magic. And this isn't the case. And it's not just semantic web, it's AI and everything else as well. These technologies don't bring magic. You don't happen by magic. You need to actually put the work in and the effort in the infrastructures, and we need to actually structure our data and our plans and our projects carefully and properly to get things to work. And so that is kind of one of the key messages I'm trying to get across with this presentation. And I think I do love the semantic web, but I've definitely seen it overused or used in areas that I think I'm not really sure this is the right technology for it. And much like the, you know, people get into obsessions with technology. We're going to make everything an ontology. I don't know, everything's going to be AI. That is currently one of our big things. But does it always need to be? Maybe we'll have some thoughts at the end of my presentation. So who actually knows about the semantic web? Before I have some slides to introduce the technological concepts, but also I don't like to assume knowledge, but I also don't want to bore you guys if you're all like semantic web experts. So hands up, who feels confident they know everything about the semantic web and I can't teach you anything? Eileen, I expect you to put your hand up, but apart from that. Okay. So the semantic web, for those of you who don't know, was conceptualized by Sir Tim Berners-Lee from Southampton, by the way. And the whole point of it really was to bring context and meaning to data. As we kind of, you know, as Blair was talking about, in his presentation yesterday, you know, we are quite good at making snap contextual understandings. We often just get things when we look at it that computers don't. So, you were talking about signs and things like that and understanding what to do. If we think about words and meaning, we have a lot of words in our language that for some reason are spelt the same way and mean completely different things, like reading and reading, tears and tears. And we just pick that up when we read through things. We just know what that is. But a computer doesn't. And that's hard. That's really hard. So you need to understand the context that goes with it. And I do think the semantic web gets a bit of a bad rap because I think it was quite misunderstood. And if you go back and read some of the seminal papers, I both understand it, but do think people maybe took it the wrong way. I think people thought of the semantic web as some sort of magical AI system, because Berners-Lee put out these kind of grand ideas that agents were going to roam the web and pull all this information out, magically understand it, and I don't know, book you really fancy holidays, I think one of the examples. But really, it's not a magical AI system. It's standards for representing your data and standards for putting your data, giving it that context, giving it that meaning so that machines can understand it, but also to create things that humans can also understand in our terms of having taxonomies and hierarchies and actually agreeing on that shared vocabulary. And we can use it to create knowledge graphs, we can use it to create semantic metadata. There's lots of things we can do with it. So we obviously have triple. So the key, the sort of original key linked data format is resource description framework, and we have subject, linked by predicate, object, and you can use specific URI to explicitly refer to the same. Now, there was no actual real reason this needed to be triples. I think they just kind of arbitrarily decided on it. It could have been something else, but it's triples, so that's where we are. And that is the kind of way you can link things and you can chain lots and lots of things together. So objects can become subjects of new graphs, and you can pull all of this together to make a knowledge graph. I just kind of wanted to give a note that there's a lot of different serialization formats. So, people see the triple, and then actually there's a lot of different ways and languages, much like we have loads of programming languages. There's lots of formats and ways to represent semantic data. So we have RDF, XML, which most people hate. So a lot of people don't like XML, which is fair enough, although I've met the odd person that really likes it. We have sort of the more machine readable things like Turtle. I think quite a lot of people like to work in Turtle. So if you see .ttl files, then that is semantic. But also probably one of the much more popular ones that people will have heard of or potentially would have used is JSON-LD. And even though you're kind of annotating your JSON with all of these things ultimately can just go straight back into triples because they are serialization formats. So this is one of the points I just wanted to get across, that there's lots of different ways of representing the data, but fundamentally the underpinning is still that triple state, that linked data. And then we have ontologies. So I've got to be honest, I like to just tell you that ontologies are fancy taxonomies with a bit of logic whapped on the top. So ontologies can be really simple. People can literally use them to define. So they're basically used to define knowledge in a domain. So you set out your relationships, your hierarchies, your concepts, and how they relate to other concepts. These can be really, really simple. I mean, you could basically start with a taxonomy, put it into OWL. That could count as an ontology. Things can also get a lot more complicated. You can add in lots of rules. You can add in, constraints on the relationships, and that's where you can then start to get things like inferencing, reasoning coming out. Sometimes things need to be that complicated. I would say a lot of times they don't. It really depends, again, what you're trying to do with the data. And then when we take that linked data model and when we take ontologies, we put them together, we basically make knowledge graphs. So these are just these graph network structures to describe your real world entities. And again, you can use them to infer new knowledge if you have actually encoded the amount of information in there to actually enable you to do that. Again, I like knowledge graphs. I think they're very cool. I think sometimes they're overused. And one of the things I do kind of want to get across in this presentation is they're great, but not everything needs to turn into a knowledge graph. I think there was definitely a stream of trying to turn absolutely everything into knowledge graphs, and I'm not always sure that's the most useful thing either. We have Sparkle, which is just a super cool name, but it's the query language, and it essentially allows you to search on concepts rather than text, which is great because then you actually know what you're searching for, which is fantastic. And then we have Shackle, which is the shapes and constraints language. I kind of wanted to mention this because I do mention it in my future thing as well, but also because I thought this was going to be really complicated because it sounded mathsy. And whilst my maths was good enough to get onto a computer science degree, it's certainly not the level of my hardcore machine learning colleagues' level of maths. And because they were talking about shapes and things, I thought this was going to be really difficult. Actually, it's not. It's basically validating your graph against a set of conditions, and the reason that and it's the condition that essentially forms the shape on the graph. So it's actually really simple. So I did just want to get that across because I definitely thought it was going to be way more complicated than it was going to be. So, bit of a whirlwind tour, but I'm aware I only have 35 minutes and I do like to talk. So there are, I say these are quite, well understood use cases of the semantic web. So you can use it to define these common shared vocabularies because, as we kind of discussed, some of the things yesterday, it's important that we all understand that we're talking about the same thing. But also, if we're not, that's also important too. And a lot of people use the same words to mean different things. I mean, even within PSD ourselves, Eileen, Cerys, myself, the team, we have spent such a long time hashing out, what is a service? What is a resource? Well, I think it's this, Anna. Well, I think it's this. And I think this is what it means. It's important that you actually agree on those terms. So that's a really good use case of that. Also making machine readable data. If you feed any of your algorithms random garbage, they're not going to understand it. So, if you want your algorithms to understand your data, it needs to be machine readable. I think there's a lot of interoperable metadata. Again, I think semantic metadata, I will talk about this later, is very, very, very key, very important. We absolutely should be doing it. Linking together data sets. Again, once you have that capacity to mark things up using a vocabulary where you all know what you're talking about, you could actually bring in multiple data sets and then look at them together. And of course, then you can do inferencing and semantic search if you kind of added those extra layers of intelligence. And as Simon kind of alluded to at the end of his talk, if we're making our data fair, if we're making our data better, we're potentially making it AI ready, if it should be used in AI. But let's have a bit of a more focus in on terminology and units. So yeah, one of our first big use cases is defining common and shared vocabularies. So fantastic, we can use this technology to define common terms to describe things consistently, and then we can mark up our data sets to talk about the same thing. That's great, right? Sounds simple, sounds easy. So one of the questions I get asked quite a lot, which is not helpful because I'm not actually a scientist, but I think a lot of the team also get asked this, is what is the physical sciences? So my computer is rapidly falling off this thing. Yeah, so what is the physical sciences? I get asked that quite a lot, and I'm like, well, I think it's chemistry and it's materials and it's some of these other spheres. But I mean, we will give slightly different answers. It's actually been quite a hard question for us to answer. So we thought, hang on a minute, there must be some classifications out there. There must be some things that tell us what the physical sciences is. It's a big area that's funded. Lots of people work in it. We go to meetings that have it in the title. Surely someone's thought about this. Someone's made a plan. It's all going to be fine. So there's actually quite a lot of classifications used to describe the physical sciences. These were just some of the ones that we found, which again kind of just starts to belie some of those problems. That actually is all very well and good saying we're going to classify things and we're going to come up with universal ways of talking about things, but then everyone goes and does it. And then it's really hard to know which one you should use. So these are just some of the classifications and ways you could break down and explain, these are the things that count as physical sciences. There's also loads and loads of ontologies. Now, these aren't even just a list of ontologies. These are a list of the ontology lookup services where you can look up ontologies that pertain to the physical sciences. So again, this just kind of, I'm just trying to give you an idea of the broad space in which we're working in. It's great that we have all of these, or is it, depending, but there's a lot of things out there, and just because you're using one term from one place doesn't mean that everyone else is actually going to be resonating with or using it, and actually understanding what things we should use is really hard. So yes, why am I telling you this? Terminology is not straightforward. It's tough, and it's great to have ontologies, but you do actually need to sit down and agree on what you're representing. And kind of the last point I think is really important, and something I always come back to, whether it's AI, whether it's fair data, whatever. If we can't define things as human beings, then how can we expect machines to understand them? And how can we start coming up with technology and standards around them if we don't actually know what we're talking about ourselves? And I think sometimes we skip that step. So terminology seems hard. Let's talk about units. And obviously, as evidenced by quite a lot of the discussions yesterday, sorry, I love the meerkat, I love Boromir, this had to come in here. But units is also really hard to describe, really complicated. Now, this isn't an exhaustive list, but this is just some of the unit ontologies that I have come across again. Now, some of the reason these exist in different places is because they run over certain different domains. But again, we don't have one standard for representing units. And then if we think about, okay, so, you know, we heard a lot yesterday about all the different things you might need to consider. I think someone did mention QUDT, which is the one at the top, but yeah, we heard a lot about what should we be considering with units. So it's not just about what the unit is, you know, what are we measuring, what are the contexts, what's that information? Again, how do we capture that? So just as a little example, you know, 10 degrees centigrade, this is some JSON LD that marks this up as a temperature measurement. You know, so there's actually quite a lot of code for, you know, 2 numbers, a symbol, and a letter. Again, I am going to share these slides, but I'm aware I kind of have to whip through them. But then if we look at the diagram of like bringing it out, again, this is quite complicated for what we're actually trying to represent, which doesn't mean it's wrong. But I guess what I just kind of want to get across is this is quite a bit for one small measurement and one small unit. But also, does this even actually capture everything that we want? You know, does this belie a lot of the additional provenance information or the extra context? You know, I'm thinking about this as kind of, you know, maybe a scientific measurement of something, but you know, Blair, you talked about kind of a whole set of extra dimensions, accuracy, all these things. So it just feels like we're making it quite difficult, and it is difficult, but almost I'm still not sure we've actually then captured the breadth of what we need, which doesn't mean we shouldn't use these schemas, but I do think we need to consider what are we actually getting back from this? Like, is there a use case? Are there proper use cases here for these things to be machine readable? And is this the best way of doing it? Now, I'm not saying I have all the answers. I'm asking the questions. So I wanted to sort of, I could say so many things about the semantic web and I could talk for hours, which I won't, don't worry. But I kind of wanted to focus in on terminology and units as that these were some of the points of the meeting. But I think these do highlight some of the big issues and concerns around these technologies. So there's lots of ontologies competing in the same space, and yet we absolutely don't have enough ontologies either, which is why people keep making new ones and they keep going, well, there isn't something out there that already represents what I want. So I guess I'm going to make new things. And when things might sound like they're easy to quantify, but actually when you dig into them and you think about all of the additional bits of context you need to capture, they're complicated. And creating linked data to represent these things is time consuming and challenging. Again, that doesn't mean we shouldn't do it, but I do think we need to think about the overall points of our project, what we're trying to achieve, what we actually want to do with our data, and be pragmatic about it. And not all data will lend itself to semantic representation. So obviously I focused in on terminology and units, but I've seen projects where people have tried to represent, for example, complex numerical schemes semantically. And that just doesn't work very well. And again, one of the things I kind of wanted to also make a point with, which was I showed you the JSON LD, I showed you those triples for something really small. Scalability is still quite an issue because actually these things have the capacity to get very, very big if you're trying to turn big data sets into knowledge graphs, which again, doesn't mean we shouldn't do them, but we do need to be aware of the consequences. So, time to get pragmatic. And I think if we're going to undertake using these technologies, we need to ask the right questions. So I've had people come to me and say, I want to make my data semantic. Well, that's nice. Okay, but why are you doing it? What are you trying to achieve? Oh, I just thought something better would come out of it. Okay, but why? What do you want to get out of it? Again, I think there's sometimes the assumption that just by using a particular technology or doing something in a certain way, that something magical will happen. And that's not the case. I mean, it may be that actually the due diligence to go ahead and work out how to mark up your data and work out how to put it into this format helps you understand it better and you create better data. And fantastic, then that in itself is a use case. But imagining you're going to get random fancy inferences out of something that you haven't even thought about how that's going to happen, that feels less likely. And again, do you need an ontology? Are there correct ontologies to represent what you want? Are there taxonomies that represent what you want? Do you need to make a whole knowledge graph? Or would it be enough to say have a semantic metadata layer? Like, do you just want to describe your data, or do you need to actually make the whole data itself semantic? So what data would actually benefit from going into a semantic format? And what do you want your data to look like, and how are you going to use it? And what domain knowledge do you need? Because again, that's also really, really tricky when it comes to using ontologies. I was part of a hackathon at the Machine Actionable Interoperability in Chemistry conference last year, and we were actually looking at how to semantically annotate and mark up data sets. And I sat with the person who wrote the data set, and we still spent ages debating the ontology terms, and she'd made the data set because it is hard. And you have a lot of things, and a lot of ontologies, scientific ones, cross over different domains, and they sound like they're giving you the terms you want, and you go back up the hierarchy, and it turns out that's not it at all. And I guess there's also, are there any obvious quick wins? So this was a discussion a few of us ended up having last night over dinner. For example, with the green, with the Green Book and the Gold Book, should you be linking those to ontologies? Should you actually be ontologizing them yourselves as the authority and then letting other people use them and then map them to ontologies? Again, I'm not on those teams. I don't have the answers, but I think those are questions that are worth asking. So I think it's really important that we consider our data in advance. So it's not trivial to make knowledge graphs, and it's certainly not trivial to create, to convert existing data into linked data. So again, I think you need to think, do you actually need this whole thing to be a knowledge graph, or could you have a semantic metadata layer? And how rich do your descriptions need to be? Is it just enough to say, this is the term I'm talking about, or do you actually need to go into more detail? And I guess also when you're making an ontology, conceptualizing it and using it in a data set are two different things. I've seen a lot of papers where people have kind of competency questions and hypothetical use cases of ontologies, but when you actually come to trying to use them in a data set to actually mark up your data, often you can find that they don't work the way you think they do. And you need to think about your entire life cycle of the project. I always think thinking about the why and the what. So why are you actually making ontologies and what are they for? And playing to the technology's strengths. So, some ontologies can be made in RDF schema because they're really simple. Some need OWL because they're more complex. Do you need full scale triples? Is JSON LD better for what you're doing because you're integrating with web applications? Again, just being pragmatic about actually how you use the technology. And reusing and extending where possible. There are lots of ontologies and vocabularies out there. So, you should look for what exists before you make a new one. And also, some of the, I guess, well-used ontologies are ones that have come from, that kind of authority, that top-level knowledge, taxonomies already exist. Are there schemas that could be turned into ontologies if you needed them to be, rather than having to make up your own? And again, you can also reuse design patterns. So don't know how many people have heard of the Obo Foundry, but they have a lot of design patterns and rules around how you make ontologies, and they made them, a lot of them, compatible with each other. Because again, that's also really important. As soon as you start using multiple ontologies together, that can cause a different type of issue. And again, if you see something that you think, well, this ontology is great, but it'd be great if it just also represented this bit, well, make an extension, or at least explore the option of extension, rather than just saying you're going to make a brand new thing. Modularizing ontologies is also really important. You can get giant whacking ontologies, and pulling them into your system just kind of breaks everything, and you just can't see the wood from the trees because you've got too many things to consider. So I think that's just quite an important point. And I always think, don't forget your standards. So even standards should have standards. It's one of my favorite things to say. So just because you're making something that's semantic doesn't mean you're making it well. Just because you're purporting to make fair data doesn't mean you're making it well. Or just because you're digitizing something rather than having it on paper doesn't mean you're doing it any better. You've just put it in a different medium. And again, there's no point you creating, I don't know, lovely ontologies in your research papers if no one can find them because you haven't put them anywhere. Or if you created great semantic data sets and nobody can find them, or nobody can use them, or nobody understands what you've done. So just because it's semantic doesn't mean it's useful. It can be very useful, but you still have to think about all these other things. And so I just want to talk a bit about some of the areas I've seen come up in a lot of the conferences I've attended, and the sort of things I think we should be thinking about in the future, and some of the potential I see in these technologies. So the first one is obviously extensions to existing ontologies, because as much as I said, we should look at extending onto others, there are still gaps. So for example, something that's come up in our community a lot is that the reaction ontologies that exist are not sufficiently deep to cover what scientists actually want to represent reaction-wise. Although this has also then led to discussions and debates about what should actually be represented ontologically and what shouldn't. But again, it's worth thinking about what these gaps are. When these actually come up at events, then we should be looking at them as a community and going, okay, this is clearly a gap. This is clearly something that people need. How can we make it happen? And, PSDI are working with the NFDI to set up a on-site meeting later this year so that we can actually discuss both what additional ontologies might need to be made for the community, but how existing ontologies could be expanded and used more usefully. And again, I think semantic metadata is really, really important, because we should have machine readable metadata. And, you know, that is kind of basically the entry point to all of our data sets. You know, so whether that's just using JSON-LD or whether that's using RO crate, so the research objects crate with JSON-LD, I think we should be describing our data sets like that. Although there are some serious challenges with that because it's not necessarily integrated through to repositories. There's quite a lot of barriers to entry with knowledge. So again, assigning generic metadata can be relatively straightforward. Assigning domain-based metadata can be a lot trickier. And again, we kind of then block into this ontology problem. But I do think that we should be moving more towards machine readable descriptions of our data so that people can actually find it. And then again, automated metadata extraction is an area that really, really interests me. Again, it is hard. It's really hard, but that doesn't mean we shouldn't be looking into how to do it. And I think in terms of, you know, creating our metadata in general, a lot of people don't do it, which is why a lot of people can't find people's data. And creating semantic metadata is obviously a new level on top of that. So if we can start looking at how we could automate some of these processes, if we made it easy for researchers, they might actually start to do it. No promises, but they might actually start to do it. And again, it's super hard because people just use random things like chemical 1. Well, I have no idea what that is, and nor does a machine because you haven't put the context in. But I still think it's worth considering. Semantic ELNs, obviously, this is like two of my passions literally merged together. So of course I was going to bring this up. There's work on the ELN file format, so by the ELN consortium, which actually looks at using RO crate and looks at packaging data in a machine readable way so it can be transferred between different electron lab notebooks, which is really cool. And there's also, if no one's looked at the Herbie electron lab notebook, it's awesome because it uses Shackle to validate forms, and it actually has underpinning semantic web technologies, and it's really neat, and I really liked it, and it made me very happy. So I think you should all have a look at that. It looked very awesome. And then also using Shackle for validation. So again, this is then actually kind of putting a set of rules in place. I've seen some quite cool things about assessing the fairness of software using RDF and Shackle. So there are some cool tools out there. Again, doesn't mean they're always going to work, they're always going to be the best thing, but I did think that was just quite a neat idea. As also, you know, a lot of people talk about fair data, but not that many people talk about fair software. So I think any efforts in that area is also really important. And of course, the big LLMs. So this always amuses me. This is a big hot topic at one of the conferences I went to recently. I find it funny because I feel like we go through cycles where people go, we need structured data. Oh, no, we don't. Here's our new ML technology that means we don't. But what if we put structured data into that? Oh, but now we no longer need it. And we pretty much keep going around that circle. But I think the key point is we're always going to need structured data. That is always going to be important. And I feel like we're always going to improve things with structured data. So thoughts for the future. This is a group effort. We can't do it by ourselves, and it's just not going to work. So we all actually need to work together, and a little semantics can go a long way. Sometimes you could get a lot more out of just having a semantic metadata record or linking to a few ontologies than spending years developing a knowledge graph that no one's actually going to use. And this is as much a human endeavor as a technical one. So this is something that we need to work on. And thank you. Somehow finished on time, which was unexpected.
Somebody asked a bunch of questions, but maybe the smarts about those questions. Yeah.
No answers from me, Sammy, but that was a wonderful talk. Thank you. I've just got questions in my head that I'd kind of like to share with you. So when Simon was speaking before you, he explained how they were able to make such progress in the crystallographic community because there was a good understanding between the members of that community, and when one person had a good idea, there was a very good chance that other people would follow. And yet you've pointed out there are many ontologies for units, which is just such a fundamental thing when you're starting to talk about data. And in fact, I mean, there's a paper, somebody did a search of all the open source software support for units, and there are hundreds of them. If you go beyond ontologies, it just doesn't stop. So we're definitely not a homogeneous community. And And the metrology people, my community, and Richard Brown was here yesterday, he's a prominent figure in that, we can't even really agree, right? So we wonder what a quantity is. So I'm not sure how we can make progress. We don't seem to be able to agree on the terminology. And so someone like me comes along and thinks all of the unit systems are no good. Here's the M layer on top of everything else. But I don't know how we can get ourselves out of this mess.
I mean, I think we need to, I mean, definitely don't have the answer. I think we do need to bring together the informed groups like in meetings like today to have these discussions, because we're not going to come to an answer on our own. And I think it's still better that you kind of come together, see each other's points of view and see, A, if there is a way for a resolution, but also if there's terminology. I think someone did the presentation yesterday where there was all the different ways of referring to things and saying, well, we need to know that those ways of referring to things exist, because otherwise, at least you know that, either you shouldn't be using this, but it is a thing and it does still mean this, rather than just, oh, no one else actually understands what it means. I can't remember, I think it was isotopes or something around that, but like, yeah, there we go. So, and I think that was a really, really good point. So I think almost, even if we can't agree on the terminology, if we can say, well, these are all the things that people think this means, then we could at least filter in that we do know that people are talking about the same thing. But I agree, it is really hard. But I do really think it's a human problem. Like, we need to bring the people together and agree. And I guess we need groups like, CoData, PSDI, the Gold Books, the Green Books, the people working on these things that, have been, I guess, funded and put together for a reason based on their experience and their knowledge. So we need to try and use these groups to kind of come to some authority in some of the chats we had last night, to drive that down. But I agree, it is really hard. And clearly we are away from solving it.
Maybe just ask the question I was going to ask. You're going to wave a magic wand or post. What would be the thing you would do first?
Oh gosh, so many things. I would definitely misuse my magic powers for evil. But that aside, that's a very good question. Oh, sorry. Well, yeah. Actually, yeah. I would find a way to bring the important people into the room, and I would stop time so that we actually all had the proper time and headspace to hash it out for a week-long conference where we weren't being distracted by the 50 million other things we were meant to be doing, and emails and people and life and things. And we would act, because I think these meetings are really useful, but also everyone is very busy. So actually getting people into one room is really hard, and getting people into one room where they're focused on one topic and they're not thinking about everything else is even harder. So yeah.
Yeah, it's hard. I mean, I've got a thought that I'll share with everyone. I don't know how good this is, but with the metrology community, for example, you become a metrologist in a particular field, and you become very, very specialized, and you only work within a very small group of peers. And I think this is a good example of something that's called a community of practice, where knowledge is held by a group of people who work together and who have a special way of communicating. In my talk yesterday, I talked about how we learn about units early on, and then we adapt them to suit our particular needs. So we're all good at using units in our own field. And I think that the problem we have in this metrology community, and I suspect this exists elsewhere, is that these communities are to some extent isolated from each other. And so if you're used to talking about using a particular unit in this field, and crystallography, clearly you've got it all together, they're one big community of practice. But if there are these other communities, we haven't found a way of bridging those gaps. And the dynamic inside that community is the more experienced people are bringing through the less experienced. So it's a very human social activity. And so to change things, you can't just knock on the door and say, excuse me, we've got a definition now for all these things. You somehow have to get it to be socialized, to be shared within those groups. That to me is, I'm finding this quite an interesting idea to try out at the moment, but don't see an easy, quick solution to it.
I mean, it is really hard. And I think the problem is it also just takes a lot of time. Like, I mean, it makes me feel old to say this, but having obviously been looking at things like semantics, but also things like ELNs and digitization for over a decade now, we are making progress. It is just slow. Like, for example, for ELNs, we've gone from no one in academia wanting to use them to some people wanting to use them, but it being really difficult. But we've progressed from no one to someone, and we've progressed from it's really hard and it feels impossible to it's really hard, but we are kind of doing it. But it's taken 10 years. So I think some of it's obviously being patient, which is obviously not great. And obviously things move on in time, and I'm hoping we can accelerate them. But some of it in terms of socializing and understanding, but also I think we also almost, things come out, we react to them, and then it takes time to realize that they haven't worked as, for example, FAIR. Like, I often think about how we could, making things fairer, because of FAIR data came out in 2016. And I think it kind of took everyone by storm. It's been super cited. Everyone talks about FAIR data now. Wherever I go, conference-wise, it comes up. But we've gone from FAIR is fantastic, so we're going to do it and we're going to implement it, and that's going to be great, and that's going to fix all our problems, to, oh, actually, it's really hard and we can't do it and we're not sure what we're doing. How should we address this? Which is then where we've kind of moved to, and so we need people, we need to bring in these, and this is how we need to do it. So I feel like almost things come out, we respond to them, and then we have to start the cycle again.
Just a sort of passing thought about that. Something we need to do better is success stories.
Yes.
We need to tell other domains, disciplines, areas that we've done these things in this area and it's really successful and it's enabled us to do these different things, just as a part of the story.
Oh, absolutely.
Thank you very much. I would just like to come back to there and then have a question for you. I think there is space for units or sets of units that are used by all specialized groups, right? As long as all these units have a clear definition and action and scaling conversion factor to the SI, for instance. Samantha, you mentioned that semantics is very important, but in your presentation, I noted a couple of acronyms that I didn't understand.
Okay, of course.
If you could be so kind, because you can have access to your presentation, and add at the end a definition of the acronyms.
Of course, sorry.
Great. Thank you very much.
Okay. So I gather that there were very good discussions. We seem to have lost a few people. And as ever, if you're not in the room, you get given things to do, I understand. So we'll find out. I think the person who's got the convey the message, Eileen, has gone away. So I will find out what I'm supposed to do. Welcome to Stuart. And it's good to see you up there.
Afternoon, Jeremy.
Great. So Stuart's name has come up many times in the meeting, and so fortunately he can join us remotely, and I've asked him to do two things, one of which is to show some of the work on the digital Green Book version, of which has in his mind gone through a few developments, and he's going to show us something, and the other is the work of part of the drum group on Stuart's collecting up of all of the various different ways of representing units and systems for that he has found. So I don't think I've seen any more. Your name has come up many times, Stuart, so we know that you're a key partner here. And I'm hoping that one of the things will come out of this work, this workshop, is that we'll find more volunteers to help out, so that we'll get more, help you get more things done. So Stuart, over to you.
Thank you, Jeremy. Let me share my screen here. Okay, you should be seeing, yes, I think I can see it on the video. So thanks, Jeremy. My name has apparently come up in vain in multiple places, I guess, and that's probably because I seem to get my hands in things that are very interesting to work on, especially in IUPAC. So as Jeremy said, the Digital Green Book 5th edition has been an IUPAC project for a number of years now, and I was lucky enough to be sort of recruited into the group through Commission I.1 to think about what this might end up looking like. And as Jeremy suggested, we've iterated on this a little bit over the last couple, 3 years. And the first sort of main idea that I came up with was to implement a digital version of the Green Book using the MediaWiki software, which is freely available. It's what Wikipedia is based off of. And at previous meetings, I've shown some example pages of that kind of interface. And one of the reasons why I've sort of rethought that is because the project should be one distributed, and by that I mean members of the IUPAC project and potentially also members of Commission I.1 in a sense should be able to be involved in this if they are interested and have time to do so. And so it was kind of important to find a mechanism that would allow many people to contribute to this, because one, it's obviously a very important resource, but two, having a lot of people involved obviously takes the burden off of one person. So so at this moment, what you're seeing is a prototype, sort of just a sort of a show and tell version of a few pages indicating functionality in a website that is on GitHub, and I can put that URL into the chat here. And the way in which this has been developed is using a Python package called Jupyter Book. And if anybody in the audience is familiar with Jupyter Notebooks, Jupyter Book is a different piece of software than Jupyter Notebooks. So be careful not to get them confused. And the nice idea about, or a nice way in which Jupyter Book works is that it's basically a package that allows you to structure any kind of online book using a set of pages that are built using the Markdown language. And there are different flavors of the Markdown language, but this particular flavor is based off of another core package that Jupyter Book is based off of, which is called Sphinx. And so the nominal pages that you see here are really just text files in the end. And what I'm going to do is I'm going to show you just a few of these pages just to highlight a few features that are available within the software. And then also I'm going to show you sort of the back end of this, which is how this will be something that many people can participate in if they're interested in doing so. So the basic front page is sort of by default, it has an index on the left-hand side. It has main content in the center. And although there's a lot of white space on both sides here, there's also opportunity to take advantage of the space on the right-hand side in terms of navigating through a particular page. So if I go through and kind of highlight or pick out a couple of pages here. So here's an example page where there's a decent amount of content on here. Most of it's text, but for instance, there are equations. And so Jupyter Book supports LaTeX inherently. So you can write quantity symbols, unit symbols, and equations and that kind of stuff in LaTeX. One thing that I would need to enhance this with, if this were what we would use, is to implement some of the other LaTeX packages that are more chemistry specific. But obviously that's a thing for the future. It supports also creating tables. You can, of course, import or display images. And you can also link to other sections. So here's a link that goes to section 7.1. And also you can indicate, it might be difficult to see it here, but there are some citations here in the page, and those link directly to the bibliography, which is in this case on this page. And this is all done by defining the bibliographic references in what's called a .bib file within the context of the overall project files, and then in text of the pages that are used to create these pages, the citation is added, and you can add as many as you wish. And of course, then it basically will sort of automatically, as long as you populate the bibliography file, it will automatically populate the references page as you add new citations in the pages for the site. You can also have these little sort of text boxes to pull out things as well, which end up making a relatively nice interface in terms of, highlighting some things within a page. There are also footnotes that can be added. So that feature, again, is just something that you can, using a certain set format in the documentation for JupyterBook, you can define that entry for a footnote, and it will show at the bottom of the current page. I'm going to go down and go to... So this one is an example of a page that has not just the main title, but it also has subsections in it. And so what ends up happening is when you have subsections in a page, you also get this, as I mentioned, this contents and on the right-hand side, and these are clickable links, so it will go down to certain sub-portions of the page to be able to visualize them. And then maybe the final feature I'll show on here is the index. I've got a few things here that have been added to the index. And again, these are actually, you define what file is going to contain the index. And then on whichever page you need to, you can then add a link to a particular entry that will then show up on the index page. So again, in the page that is used, the markdown page that is used to generate this page, there is an index entry for number of entities and an index entry for amount of substance as well. So, so there's a lot of functionality that's automatically built in to JupyterBook, and allows you to create a very nice, relatively easily navigable website with the kinds of functionalities or the features that are already in the 3rd edition of the Green Book and in the 4th edition as well. The way in which people can contribute to this is through the GitHub repository. That is where this is derived from. And so let me change pages here. So on GitHub, the content that you just saw is present as a repository. In this case, at this moment, it's private. It could be made public, but it in fact doesn't obviously need to be made public because the content is already live on the page that you just saw. And if you're familiar with GitHub, you'll know what this is all about. But if you're not so familiar with GitHub, GitHub is just basically a place where you can typically store a set of files. These are typically scripting files, but they don't have to be. They can be text files. And the nice thing about this particular setup is anybody who would want to participate in contributing to this as a project can be added as a collaborator on here. And then the way in which they would actually be able to contribute is by taking what's called a fork of this repository, which means they basically they have their own account on GitHub, they take a copy of this repository, and when they take a copy of the repository, then they get all the files that are in the repository, but then locally on their computer, they can go ahead and make edits to pages. And once they're satisfied with those changes that they've made, then they can submit what's called a pull request, which is just a fancy way of saying, hey, I've got some changes that I think are appropriate that need to be added to the main content. And those are submitted through GitHub. The main admin on this project would then review those content updates, and obviously assuming they're appropriate, we could then approve them, and then that information gets merged into the content on this repository. And because of the way this content has been configured, that actually any change in content triggers what's called a GitHub action. And GitHub actions can do a number of different things, but in this context, the action is to build the book that you just saw automatically when new content is submitted to the repository. So basically, once a contribution comes in from a collaborator and gets approved through the pull request process, then when the admin accepts that into the main repository, then that process automatically triggers the action to fire, which would then update the content of the book. And so this is a really nice way to share the load, have multiple people contributing. But one of the key things about this particular book is that in addition to the text content, obviously, one of the things that's very important are the quantity symbols and the unit symbols. And as a consequence of that, this project would need to be not only an IUPAC project, but it would also need to kind of integrate with a way in which to put together metadata around quantity symbols, unit symbols, so that consistency, not only across this particular output, but potentially other outputs where the same content might be used could be standardized. And so this project it's about creating a digital copy of the book, but it's also about making sure we have appropriate digital representation of units and quantities that are important, obviously relative to chemistry. Before I move off this topic, let me briefly bring in, just so you can also see, this is a window to the actual content that is used to create this site. As I said, the actual book itself is created off of a set of what are called markdown files, and the markdown files are just text files and have specific formatting for things like headers and lists and tables and that kind of stuff. And so, this is a nice way to be able to sort of author pages and then be able to submit, obviously, content, as I said. So that's the first topic that Jeremy asked me to talk about. And the second topic is something near and dear to my heart, which is something that's been generated through the drum groups.
Stuart, can I stop for a moment? Shall we just look, see if there are any questions on this part?
Sure.
This is really good, what you've done. So just getting the microphones here. Whilst we start that, so I have a couple of questions for you, Stuart. Given that the Jupyter book and the Markdown, can it also interact with a computational backend? As in, if you put a table in, can you generate the graph, for example, and put in a figure, like if it were in RStudio or in a Jupyter notebook itself? Is that something?
You can do that, yes.
So again, it might mean that we don't actually have to put a separate graph in, we can generate stuff. Roberta.
Stuart, hello.
Hey,
thank you very much for this very nice progress presentation that you showed us here now. And one of the tables that you showed Yeah, for instance, that one. I notice, well, here the symbols are pretty much familiar to me, also from what I know of from the current printed version of the Green Book. But you had another table where symbols, particularly for units, seem to be different. Perhaps you can show
this one, or
no, this is no, you had another, yeah, this one here.
Okay.
Here we have, for instance, the Pico, so what is PMA? What is this meaning?
That's I think that's probably a typo on my part.
Yeah. It should be
Yeah.
MPA.
It should be MPA.
Pascal, yeah.
Yes.
And
Yeah.
here the fonts that you're using in the table differ probably from the fonts that you use in the text.
That's correct. I think that's the default way that Jupyter Book is set up, but I'm pretty confident that can be made consistent across the both the regular text and the table text.
Okay. Thank you very much. My second question would be, take this page here now. Could you just show to us, if this is not too time consuming, how you proceeded on this GitHub source file, on the markdown file, how to edit, for instance, this table?
Yep, I can bring that up right now. Here we go. Let me see if I can make this a little bigger. Well, maybe that would take a little bit too much time. So hopefully you can see this. This is the is the table itself.
Yeah.
Literally, the way this is set up is
I see.
Each row has the pipe character to separate columns. This is sort of like the header definition row and has some formatting to it. So, for instance, the colon at the left-hand side, the colon at the right-hand side, basically says the formatting of the column should be centered. If it's the colon is only on the left-hand side, it should be to the left aligned. If it's only on the right-hand side, it's right aligned. So you can change that per individual column.
Yeah, thank you. That's fine. I think that's
yeah.
fine.
I mean, it just shows it's straightforward editing. I think one of the things that we talked about, which is parallel to this, is, for example, we already have in work that Stuart's already done and Roberta's done, macros in LaTeX in some cases, HTML strings. In some cases in the units, we even have it in QUDT. And actually imagining that we will have a place where you could go and copy and paste those things to save them being retyped in here. This is entirely, as I say, consistent with this approach here.
But I should also add here regarding Joseph's input, right? Stuart, we should have here now we should replace all the entries there for units. So the Pascal, for instance, we should replace it by a Unicode corresponding macro.
In the right place for the right. I mean, there are some things. There are good ways of doing different things, and I mean, I think one of the, unfortunately, I wasn't here. Sorry, Joseph, wasn't here. But I think everybody realized there's a lot of scope for some of the things that took this long piece of LaTeX 20 years ago. That's gone. But equally, we're just having places where we can refer by names, macro, whatever, to things which will make it even easier for people to edit these pages. I think that's something. It's a parallel part of this. But
if this is still allowed, one last example, Stuart, if you could show to us one typical Green Book table with definitions and ISI units and things like that.
Did you do one of those?
If you already did one.
Yes, it's.
I'll be a lot, right, Stuart.
Yeah, that's all right. Let me go back to here.
Yes.
So here, here's an example, and this shows you the index command, which is this string is then added to the index on that index page that I showed. You can also this is a title for the table, and then these are the individual percentage widths of each column to be defined, and a default left alignment.
Thank you very much.
So this is
You're welcome.
Really great. And I mean, just, my vision that with things like this, being able to insert a column, which you can either show or not show or print or not show, that would link to the Gold Book entry if there is a commentary. The Gold Book, the Green Book has the symbols, the units, and some advice on it. If you want a textual definition, that's somewhere else, and you can bring them together or not. That's the sort of thing that we will be able to do here. Any other questions?
One thing I could show really quickly here too is, I don't know if people saw it as I was talking to Roberto, but I made an edit to fix that issue of the unit that he saw. And so now what has happened is this typo fix commit that I made automatically triggered a rebuild of the pages. So at least theoretically, if I now refresh this,
well,
I've even still got it the wrong way around, but you get the point.
Yeah.
That you can relatively easily make a change here. So
fantastic. Okay, if there are no other questions on this bit, Stuart, back over to you for the unit stuff. Fantastic, thank you.
Yes. So as part of the work of the CODATA task group on the digital representation of units of measurement, we've worked on, primarily myself, but others have contributed. We've worked on what was an Excel spreadsheet originally, and is now this page on the CODATA website. Let me make this a bit bigger so you can see it. So what this page does is it goes through. Again, I'll put this in the chat. This page goes through different digital representations of units, and these are from many different areas. So for instance, as Joseph showed yesterday, obviously LaTeX, there's a lot that can be done, obviously representing units of measurement using LaTeX. Not only sticks, SI unit X, but also other options. But it's not just about formatting. There are ontologies in here. One of them, most important one maybe, is QUDT, quantities, units, dimensions, and data types. But there are also different software packages for scripting languages. Pint does units for Python. There are a number of different other packages for Java and JavaScript and so on and so on. In addition to that, there are encoding standards like the Unified Code for Units of Measurement, which is now heavily used within the medical community and is part of the FHIR, FHIR specification. So there are a number of different digital ways in which units of measurement can be represented, and in a sense, it really kind of boils down to, well, what is your application? What are you working on? What's the right way to represent units in the context of how you are dealing with data in a digital sense? And one of the things that this has also led to is the idea that we need to have some way to do unit interoperability. And another project I've worked on is through NIST, through Bob Hanish, who's on the call, the Units of Measurement Interoperability Service, which is literally a mechanism to pull together representations of units from different systems that are maybe not necessarily the most important, but maybe the most used systems of the ones that are on this page, and provide a website where people can translate across unit representations if they need to do that. I don't know that it necessarily happens at this moment, but I think it's quite possible in the future that either general or domain repositories will maybe in some fashion start standardizing on unit representation. And so you can imagine if somebody in a particular community represents their units a certain way, but then if they need to contribute that data to a domain or a general repository, and there are requirements about how the units are represented, then you could certainly imagine the need for being able to translate the units from however, in a domain sense, they're represented to what the repository would require. And so that work is ongoing. I'm not going to show it here, but that's going to come out over the summer of this summer, sort of in alignment with the formal version 1 of the BIPM's SI reference point, which is the upcoming, already available in beta version, but upcoming digital way to represent the SI. Anybody has any questions on this, I'm happy to answer on this work.
Thank you, Stuart. I think what's really interesting about what you're suggesting there is in line with what Blair was suggesting yesterday, that you present your data with your units and then give the ability to the recipient to translate them. Well, that's one unit system to another, but one unit representation system to another can also happen here. As long as people put complete information, put the necessary information in, or as we maybe was referred to in the discussions, in the data conversion service we provide with PSDI, we highlight if the conversions are lossy or lossless or whatever, or that there wasn't enough information in the first place. That's fine, this is what happens, but this all works to be the balance between the producer and the consumer, and I think this is a very interesting way to go. Any questions about this thing that Stuart knows a lot more about it than he's hiding underneath. He's looked at all of these, so if you want to ask about any of them. Interestingly, I think again the point about what is sensible to do, to pick up Sammy's point about you can provide your pages of semantics and it can be useful, but is it what is necessary? And to put so we had a discussion on a drum call a few months ago from some people who are associated with making space measurements and whatever, who are actually linked to NASA. But they said QUDT is far too heavyweight for any one. There isn't space in the place in the file. That's just a start, and nobody's going to put it in there. What they need is something that people can easily use. That, of course, they understood. These people understood perfectly QUDT, as in if there's something that you can get somebody to sensibly put in that could then be converted into QUDT if it was useful and necessary to do so by somebody else, that would be your best bet, because you've got to understand who's going to do what. And that's been one of the driving forces of Trump. How do we get people to easily do enough that you've got the information in there? But questions? I think there'll be a lot of follow-up stuff from PSDI people in due course.
Jeremy, I was going to say one final thought, and is if there's no other comments in the room there, maybe 3 years ago, as I had a slide in one of my ACS presentations where I suggested that because there are these different ways to represent units, that we may have to think about how do we, or what guidance should we give the chemistry community specifically about if you have your data in Excel, how should you appropriately, or maybe what's the recommended way, or some guidance on noting the unit relative to data in an Excel spreadsheet. But then if that data gets translated into other formats, maybe there's a need to have guidance about, well, if you're moving it to this kind of format, you might want to translate the units into this unit representation, for instance. But again, that's trying to kind of keep the knowledge about the unit sort of accurately as we translate data across different formats. And we're not anywhere close to that yet, obviously, because we're still trying to get ourselves into a fair data kind of scenario. So
I think that I would only add to that, what we're talking about from yesterday is, yes, we do it the units, but we also, there's the quantity and units are tied together here, because the unit doesn't give you all the information you actually need about the quantity. And that's the part where the M layer comes in and so on. So it's treating the exchange of the piece of information that that data range is behind. And case studies across different domains, that's going to be really important to put in as this grows. Following the whole metadata idea here, I've asked Simon to, he volunteered, to produce a few slides essentially on one of the major pieces of work that CoData has been doing, CDIF, which I vaguely knew about. Eileen picked up and said, and volunteered to read the 100 pages. But in those 100 pages are really interesting things about, if you know, the sort of basic files. One of the lessons we learned a few years ago, like 15, 20, we did some work with a student, and he actually recorded, this was a second harmonic generation liquid surface experiment. It was organized, it ran organized from a computer, it knew what it was doing, it recorded the data really nicely. We recorded it into a database, and there was a web front end that means that people could see the final results and track all the way back to the individual data points. And we're trying to get this back up again recently, only to discover that the website had disappeared. Only then to discover the database dump was incomplete and anyway out of date, and actually rebuilt the system from the CSV files plus the blog entries of doing it. Of course, after a while, I had this great idea, and I sent a note to our computing services to say, you know, basically, I knew that we'd archived this properly somewhere on one of their stacks. So I said, could you look up the last place that this DNS entry, this web address, pointed at? And they could, and they gave it. And then we were able to find out where that was archived, and we actually recovered the whole website and the whole caboodle. And the interesting thing was how much of the information to link everything that was coded into the website that was not obvious from some of the other things was because we had this very good record. Stephen had done a fantastic job. But it just shows how difficult it is to archive something. In the end, the only thing that didn't come up working was the Google Charts API that has all gone and disappeared, which can be replaced. But one of the things that it showed me is that CSV files are really very powerful things if you've got columns. And what I understand is that reaching into things like CSV files, actually CDIF may provide methods of doing that. So I'm really interested to hear more about what's going on. Simon, if you'd like to give.
Thanks for the opportunity to speak. Jeremy, just before we got started this morning, said, what do you want out of this meeting? So this is what I want out of this meeting. Next steps for Drum. Further contributions from Drum and this community to what we call the universals profile for CDIF, and I'll explain what that is, and identify further areas of collaboration around CDIF. Now, obviously, CoData cares about CDIF, the cross-domain interoperability framework. We even now have a logo, and we're trying to encourage other people to care about it as well. Now, there are some people in this room that have seen many of these slides before, some people who've seen some of them before, some people who've seen none of them. So I apologize accordingly. I'll try and rattle through so as not to take too much time so we have some discussion. But, you know, hope the slides will be shared afterwards. Very quickly, CoData. With the Committee on Data of the International Science Council, and obviously, therefore, we're not a committee, we're an organization in our own right. Okay, so I was explaining that CoData is called a committee, but it's not a committee. It has committees. We have an executive committee, a data policy committee, but we're not a committee. That was just the nomenclature which was used in the 1960s and 70s when the International Science Council or predecessors set up other organizations. They were called committees or scientific committees. We're an organization on our own right, and one way of explaining what we are and what we do is that on the one hand, we're a membership organization that leverages a network of experts globally in the way that many similar organizations do through task groups or working groups and a certain amount of voluntary effort. And on the other hand, we've made great efforts in recent years to expand our secretariat through project funding. And so we now have a significantly larger secretariat than we used to, which is directly involved in a number of projects. And I think just in the 21st century, that's a necessary part of our activity because we have to show that we address our mission more rapidly and through more activity than is possible for us just by voluntary effort. So, and I think that duality is quite important and potentially quite interesting. At least I find it so. And in terms of drum and further work on units and further work in relation to CDIF, something quite important is that we're calling for nominations to our executive committee and task group proposals. A call will be released before the 17th of April. The deadline for proposals, for nominations for members of the executive committee or for proposals for the task groups is the 17th of June. And that will all be decided upon in our General Assembly on the 17th and 18th of October, just after International Data Week in Brisbane, Australia. Okay. Right, now onto the content. This is the abbreviated version of where CDIF came from. We were asked in 2018 by the International Science Council to look at implementation of FAIR and above all interoperability for interdisciplinary research projects. And so we call that activity Making Data Work for Global Grand Challenges. The reason for that was the International Science Council sponsors a set of global programs, advises on global programs to address significant issues. Climate change adaptation, disaster risk reduction, we heard from Virginia yesterday. These sort of research areas are fundamental to planetary and human future. They're fundamentally interdisciplinary and they require data from many different sources. And for many research questions, the integration and combination of those data. So how do we do that? How do we make those data fair so that they're interoperable and reusable? So we explored this through a number of activities and pilot projects. Sami mentioned earlier how great it would be to go away for a week and not have email and just work. We've been doing that for the last few years at the Dagstuhl Center, the Schloss Dagstuhl. It's a Leibniz Foundation center in the middle of nowhere in the Saarland in Germany. And we have used that opportunity a great deal to advance our work. It's been a huge privilege and it's been very effective. Ways of doing that through other means, I would recommend to this community, to any collaboration, because it's where some real work gets done. We were then fortunate enough to have the WorldFAIR project, which was EC funded, but we were allowed to have partners from all around the world, except for China, North Korea, South Sudan, and the United Kingdom because of Brexit. But apart from that, it was a global project. But we did have UK partners, it's just they weren't paid. Or weren't paid by the EC, they were paid by UKRI. I'll talk about the deliverables from WorldFAIR, and that's now WorldFAIR Plus, and I'll explain what that is. But one of the key outputs was CDIF, the cross-domain interoperability framework. Here's the outputs, summary of what we achieved in a blog post, a link to outputs from the various case studies, 11 case studies from various disciplines, including one from IUPAC, who were a funded partner on the project. Some fantastic outputs there. Please have a look at that case study outputs. And Leah was the lead of that work, and I'm sure we'll explain that to you. We did a lot of work with FAIR implementation profiles. I won't go into that, but I think that's interesting stuff as well. We made a set of policy recommendations in that leaflet and CDIF. So on to CDIF. What is CDIF? It identifies a set of functional requirements for interoperability, particularly for use cases where you want to combine or integrate data. So we thought about what are the functional requirements for this. And although we were inspired by the FAIR principles, we didn't follow those slavishly. And then we made a set of recommendations for good practice and produced a set of implementation guidelines. And I think that's quite important as well. So I love this XKCD cartoon. Many of you will have seen that many times before. I really don't think we've fallen into that particular heffalump trap. CDIF is not a new standard. What it is a framework of standards. That's why it's called a framework. And it's a set of recommendations of existing standards to use to address certain functional requirements. So the originality of CDIF is that it's not original. We haven't invented anything. We've made a set of recommendations and guidelines to do things that need to be done by pointing to existing standards and providing guidance on how to do those things. And although that might now not sound world-changing, I think it's extremely useful. Yeah, and I think that's what needs to be said there. So what is it? This is the first version of CDIF that was released in May last year. So it's a set of practical principles and guidelines to improve data management and to enable integration in cross-domain or interdisciplinary research areas and for reuse in that context. And it recommends a set of existing standards and provides guidelines on how to use them. We released an original report, which was about 150 pages long, and then that's been turned into a GitHub-powered book, which is available there. The initial profiles. Discovery, because you need to find the data. Access, because the repository needs to have a way of controlling access. Controlled vocabularies. How do we encode them in an effective web-friendly way? Data description, and this is the key step for integration plus universals, and that's possibly the area which is most relevant here. That includes time, space, units of measurement, and some other things that are important for integrating data, for connectors between data sets. So that was the first. Oh, and I should have said, in each of those things, you can see on this diagram some recommendations, some simple recommendations around existing domain neutral standards which can be used for these functional requirements. So for discovery, schema.org or DCAT expresses JSON LD. ODRL, the Open Digital Rights Language, for an expression of rights to use particular data. SCOS for description of vocabularies. We haven't yet got into discussing and describing how to use OWL, because at this stage we just wanted to deal with flat terminologies. Data description. Here's the more interesting, or perhaps the area of CDIF where we're pushing things a bit further. How to use DDI, CDI, cross-domain integration, for data integration, to decompose and to recompose data sets. And then the universals, those connectors between data sets, which are often needed for data integration or data combination. So that's where we got to. And where we're going next is further work on access and access controls, further work on integration and providing a set of use cases and examples of how to do that. Mappings, semantic mappings, and recommending the use of ESM for that, and looking at current work in current European projects and in the RDA group on mappings and using some of that outcomes. And then some of the things that we've discussed here already this morning. Context, how to and provenance and process. Context is our term for the context in which the data were made, and in particular, how we describe the object of interest if we're using observations and measurements terminology, the variable if we're using social science terminology, and the units involved. That sort of cluster, how to model that cluster of things that you need to understand and reuse the data. Now, Jeremy, I don't know how long you want me to go on and how long I should explain some of the details of this. So I can go on to a little bit more of detail. This is what's significant about the discovery profile. And we've had some very good feedback on this. This essentially incorporates some good practice that we got from the case studies in WorldFAIR, and looking further afield, looking at people who are developing science on schema.org for the earth sciences, and the use and the recommendations in ODIS, which is the Ocean Data Information System. And that was actually represented on the project in our oceanography case study. So the discovery profile, in simple terms, contains a content model, what you should include in the fields, recommendations on that, examples of JSON-LD serialization, and a DCAT example as well, and example workflows. And the content model will be familiar to many people, but has one I consider extremely important additional content. Surface the variable description in the discovery metadata. And in the PSDI workshop last week, I said this is one baby step, or one small step that we can do to improve discovery. Discovery metadata is often managerial. It often has the priorities of funders or other people at the fore, rather than the priorities of researchers who might want to use it. What are researchers concerned about in a data set? What did you measure? What variables are in it? Let's move our practice forward a little bit by surfacing the variable description and definition in the discovery metadata. So variable measured is a field in schema.org that can do that, and there is a field now as a result of discussion in DCAT, as I understand it, which will do the same thing. Then for data integration. So the use cases that we're concerned with are, yes, how do you combine data sets when you're involved in an interdisciplinary research project and you're dealing with these different data sets? But it could equally well be a use case where you're combining a lot of data in the same research area. One way or another, you need to integrate data, which might come in different formats, in different structures. And there might be analogous but similar definitions of key variables or other concepts associated with the data. So we need to think about the semantics, how they're encoded and how they can be mapped. We also need to think about the data structure. And this is what CDI, which has recently been released. It's been around in a sort of an effective beta version for a few years. The official release was last month. Now, what CDI does is provide three particularly very useful functions. A description of the structure of the data. So that allows you to develop functions to transform the data to decompose and recompose, and to know to log what you've done. The data description and the variable cascade, which links the concept with how it's described generically and how it's described in an individual data set. And then there's this middle one, the represented variable, which is a sort of a middle road to enable data integration and to round off the fuzzy edges between how it might be implemented in this data set and how it might be implemented in this data set. We can go into the details of that, and Steve can provide an example if you like. But that's the sort of the layperson's description. This is how it's implemented in a given database. This is the definition. This is how it's described more generically, and that's the concept to which it's referring to. Now, that variable cascade is used in a number of disciplines as a way of managing the relationship between concepts and their implementation, and helping manage the integration of data. And it's a very powerful idea. And it's something that I think is potentially really useful in a number of different domains. And that's something that we're keen to explore as well. CDI also has a module for provenance and processing of these transformations. So 3 functions to better enable decomposition and recomposition of data. And very useful for that. Now, why? Why are we interested in this? I think it's always really important to pull back to concrete examples of why this is useful for research. So these are 2 projects that we've been involved in one way or another, where this sort of data integration happens. One is a series of projects in health research and population level health research in East Africa, where they've combined statistical data, population level health data, clinical outcome data, and now various additional environmental factors, taking an exposome approach to public health. And so there's a number of different data types that need to be combined into a model. And there's a number of terminologies which need to be aligned. So classic data integration. But DDI-CDI performs an important role in the midst of all that semantic mapping for the combination of the data. Similarly, we're involved in a pilot project, or CoData wasn't directly, but people that we work with were. It was called Climate Neutral and Smart Cities, but essentially what it did was combine the European Social Survey with climate data, both temperature data and pollution data. Really important research question. What are social attitudes to climate change, and how do they correspond or not to the real experience of pollution? And how do you create these combined data sets? Now, this is something that people do all the time, but they do in a very manual, laborious, data munging, data wrangling way. What we did in this project was demonstrate how you can essentially create a provenance chain for how those data are combined, how that can be created using a standard, and therefore repeated automatically year on year on year in time series. So relatively simple thing, in a sense. It's not that easy in terms of the data wrangling, but once it's described using a standard and using the DDI-CDI standard, then you've got the provenance, you know how the data have been combined, and you can repeat it, you can repeat it, you can repeat it. And that's got to be a time saver, it's got to be incredibly useful, and it's helpful for reproducibility as well. So hopefully those 2 case studies have given you an indication of why this is useful. And I hope that in PSDI, we can reflect what are the case studies, what are the use cases that we might have in the physical sciences that could be of interest. 2 slides on WorldFAIR Plus. So WorldFAIR Plus is not a single project, as WorldFAIR was. It's a federation of projects to continue that work. And so CoData is acting as the glue between a set of projects, most of which are about either about a case study approach, looking at FIPS, looking at how you implement FAIR and trying to understand the requirements in a given research project and what that can tell us. And then in particular to implement CDIF, to implement, test, refine and extend the CDIF recommendations, and to address other areas that I spoke about. There's a lot of text on this slide, but this is just to convince you that WorldFAIR Plus isn't just a pipe dream, it's reality. We now have 8 projects. I had good news earlier today that a further project has been funded. There's a range of research areas here: population health, disaster risk reduction. CDIF for XAS involves some people that are involved in PSDI. Leandro Liborio and Abraham are involved with that. That's putting a CDIF layer on top of XAS data to encourage or to enable further use of that XAS data in other domains. A set relating to climate adaptation and one relating to geology as well. So if I've not used too much time, I can say a bit about CDIF for XAS as well. So CDIF for XAS was one of the cascading grants from the Oscars project. So it's not enormous, but it's not insignificant as well. I mean, it's 250,000 euros. The partners are Codata, STFC, Cardiff for the catalysis lab, and two groups in Germany who are unfunded partners, but contributing a great deal to that HZB and the Helmholtz metadata consortium as well. The objective to enable, well, I won't read that out, it's on the slide, but essentially what we're trying to do is to demonstrate that by adding a layer of CDIF metadata, we can make that XAS data more interoperable, more reusable, and more reusable outside its original domain or outside the original course for its creation. Drivers for that is use of XAS data in various disciplines, listed there, and larger experiments, larger data volumes, need for data integration, need for reuse of data across facilities, need for aggregation, and as soon as we say machine processing, we also start to think about AI readiness. The outputs that there will be from that project are listed there on the slide, and the first one is already available. That's really a landscape survey of facilities and the various standards used in X-ray absorption spectroscopy, with a conclusion that we would focus for the next step on, I never know how to say this, on XDI data, because that's easy, and NXS? How do I say the NXXAS? You like that, yeah. So we identified anyway, after the landscape survey, you know, what pops out is that actually we'll focus on those two standards and see how far we can get with putting a CDIF layer on top of them. So that was our key finding. I think it's a useful survey. It was certainly an eye-opener. It was certainly an eye-opener of how many standards there are in X-ray absorption spectroscopy and how many of those standards have been put in place essentially by the particular facility. I mean, I think that's the message that came out of it. Lots of facilities doing that work, and they've each developed their own standard or variation of standards. Now, they're not entirely uninteroperable, but you need to do some work to move data around between facilities. And so our contention is that maybe with that CDIF description, we can help make that task of moving data that was perhaps created in one facility needs to be, and with a XAS profile and combining with data from another facility, we can make that process easier. Or at least we can identify some recommendations to make that process easier. And I think that would be a good output. So the next step and the next deliverable due end of July. So through that landscape survey, we identified those two standards that we'll focus on, NXS and XDI. Apply the CDIF discovery profile, which I've discussed. Explore how we can use that variable cascade and the other components of DDI CDI to describe the XAS data to help us combine it. And in particular, that will involve a characterization of the HDF5 data structure using DDI CDI. And that's something we've wanted to do for a while. That's not included in the current descriptions of data structure, and that will be incredibly interesting. I don't think, if I understand it, it will be too difficult because it's like a sort of a component of different tables, but we'll see. And then obviously mappings of different concepts. So that's where we are with CDIF for XAS. We're very keen to discuss that further, and in particular, the outcomes of the next stage that we hope will be useful. Any feedback on the, we've already had some extensive feedback, as you might not be surprised, from some members of IUCR on the survey. I think they were positive about the survey, but there was just lots of stuff that they've written that we hadn't cited. So we'll try and shoehorn that in. But I think, I hope that project will be of interest to PSDI, and we're keen to keep communication open around that. So where next? We're always interested in case studies that we can, where we can collaborate with the FAIR implementation profiles approach. With PSDI, would it be possible to do something building on CDIF for XAS? Another area of research that's important to PSDI? Are there interdisciplinary case studies which are significant for the mission of PSDI, where there is physical sciences data which has a high reuse potential in another domain or in something that counts as interdisciplinary? And then the next 3 bullets are really what came out of the discussion earlier. Modeling of this generic understanding of the core information that you need to understand data. How do you define the property or the variable? How do you define the units or the scale? What information do you need about that to understand data beyond the domain? As you've already seen from the CDIF diagram, we're very keen to look at provenance and process, and that's on, there's active work on that already. And quality, process, and certainty. How do we relay that information to potential users within a given discipline or outside that discipline? We have got a draft engagement document that we're discussing with various potential partners, and we'd be happy to have a similar discussion with PSDI or any other stakeholder. And I think that's, I'm contractually obliged to plug International Data Week on the call for sessions for SciDataCon, which is part of that. If you're quick with your telephones, you can get the link there.
We do now is if everybody goes and grabs a cup of tea, coffee, round a bit, and then come back here for a final sort of roundup. We can ask any questions on CDIF. I've got a few other points to make, and we'll particularly hear if there are any people who got specific things that we suggest we should do that have not been mentioned so far. So tea and coffee, I think, is there. I think it's there, and getting cold. So go and grab your tea, coffee, biscuits, bring them back here. And in 10 minutes time, we'll have a roundup session, and we'll aim to finish probably about past or something. Okay. Okay, what I'd like to do is to call you all, come back for a few minutes just to have a bit of discussion. So I thought I'd just start out this session with a little bit of amusement. A few years ago, Stuart had a session at ACS meeting around units and semantics and so on. And I was reporting a little bit on Drum to that, and reporting on some of the problems. Actually, I had recently before that had a discussion with Ian Mills about ratio units and some papers that he'd published that people were criticizing so on. So I did a little bit about that, and we've heard some of the issues with ratio units, and it also extends to angles and so on. But there's also one of the thing that struck me. Ian was complaining about the removal of cycles per second from the SI. He said, what's wrong with cycles? So we have, Hertz is effectively cycles per second. So Hertz is used. They're highlighted. This was a special case that tells you it's a frequency, and I had actually forgotten that Becquerel is events per second, but we're still missing things. So I thought for a bit of amusement, because effectively it was kind of a run up to Christmas, and I always meant to write this up for the Christmas edition of CI, so maybe I will. So first of all, let me point out that people redefine things in their own way to make things as simple as possible. So the famous atomic units, given AU, which is otherwise known as arbitrary unit, because it's just as bad as the physicists writing ESU or EMU. Those are not units. They are a system of units. And the CGS units extended for ESU and EMU were perfectly good ones, entertaining for any of the students who didn't know that hidden in there was centimeters to the half and things like that, because there is no dimension of charge in that system. All fine otherwise. Actually, sometimes very convenient size quantities. But when I started doing non-linear spectroscopy and you wanted Chi2, the second order non-linearity, and you get a number ESU, you know, nobody knew what to do with that at all. It took a long time to find conversion units to SI for that one. So anyway, but in atomic units, to make life in calculations in quantum chemistry easier, we do have a length which comes in the Bohr. Energy is the Hartree, charge is just the electronic charge. And lots of these nice numbers are defined to give you values of 1. So, well, okay, very well. I still think they should have capital letters for some of these things. But it's a set of very convenient set of values. And that's what we have to remind ourselves what people do, is that they will use sets of units. You had the example came up before of you know, we might be a nanomole of humanity, something like that around. But the idea that you have an Earth. Now, interestingly, for example, I had a very excited mathematics colleague who came to me and said, it's extraordinary, isn't it, that the circumference of the Earth is almost exactly 40,000 kilometers. No, it's not extraordinary at all. It's all down to Napoleon. That's exactly where the meter came from. But you know, the idea of one astronomical unit, which is the average distance of the Earth to the Sun. It's not a circle. It's a, but the idea that we need, if everybody was to consume as much as North Americans, then we would need several Earths worth of production of food. Yeah, an Earth and we always do. Black holes are millions of sun masses. You know, so this is very important. So this is a particularly useful one. If you do nuclear quantum chromochemistry, chromodynamics, then you need different things here. I still don't understand about why the Higgs field is not the ether, and that we're really, you know. But then I listened to a program last night that explained to me that I was wrong to think that photons don't know time. Photons travel at the speed of light, right? So speed of light means that in the speed of light, time dilation is infinite. So photons, the time for a photon is concerned between emission and absorption is 0. Well, it turns out no, because there's no reference frame for a photon. You can't catch up with a photon to ask what the reference frame is. So it turns out you just can't ask that question. So listen to one of the podcasts from around that, but I'm thinking about that one. So it turns out it still comes from, it doesn't matter how fast the potato is going, it won't turn into a black hole, right? Because you know, the protons going around the Large Hadron Collider get heavier and heavier as they get faster and faster. So if you move a potato very fast, it would turn into a black hole. But no, because potato is already moving that fast with respect to the protons that are moving around. So it's the inertial mass and the energy dependent mass. It gets harder and harder to push the proton, but that doesn't mean it's got heavier in the same sense. And it's no harder to push it sideways. Interestingly, it's still got the same mass. Anyway, digress there. So I came up with, I was thinking about the fact that on the atomic scale, you have the Boltzmann constant, right? Boltzmann constant, nice. But conveniently, chemists don't like working with Boltzmann constant most of the time. They like working with the mole of things. Well, the amount of substance equivalent to 1 mole of things. I have to get the amount of substance thing right here. So the gas constant, which perhaps we could have called the Boyle constant, because he was one of the, it could be called the Charles constant as well, I guess. There are several big people involved in defining the properties of the ideal gas. But that gives us the gas constant. So that's the equivalent of on a molar scale. Now, in certain equations that turn up in transition state theory, you get kT over h on the front, and then an exponential of delta H over RT. And I'm surprised that the students don't rebel at this, of having an equation with both K in it and R. It does seem to be a bit crazy. So it seemed to be clear that we should invent the quantity of a mole of Planck constant. But then it depends what you're actually trying to do. If it's in the classic virtual quantum chemistry, and Planck's constant is to do with uncertainty, which, you know, that's one of the places it comes from. A mole of uncertainty, I thought, should be called a Heisenberg. Right? Would seem to be the most useful thing there. On the other hand, if it's a mole of photons, I think it should be an Einstein. It turns out the Einstein is a unit biologists have used, but typically they actually put a frequency in there. Sometimes it's a mole, it's the energy of a mole of photons around visible light. It's not well used, and it's probably not to be recommended, but, you know, we could have an Einstein of photons. Now, we have the charge already, that's the electron charge, and we measure this in coulombs, but maybe we should have had a single charge, maybe called a Millikan or a Thomson, after the discoverer or the measurer of the charge. But we do have a mole of electronic charge. It's the Faraday, very important, especially in this building. And it's a certain number of coulombs, but Faraday is a very convenient number of electrons, especially if you're doing electrochemistry. So then it occurred to me we should really have the chemical amp, which is a Faraday per second, because that's the amount of charge we're moving per second. It's clearly a current, and I thought the best thing for that might be a Nernst, because the Faraday constant in this concept frequently turns up in the Nernst equation. So, you know, it's possible to invent really useful things. And as far as I know, these characters I'm putting here, well, Heisenberg have some issues interesting about that. But most of these people haven't had too much negative documentary against them. But if we then look back at this issue, so we have events per second is the Becquerel, typically applied to reactivity, but I guess it could be any other events per second. Cycles per second is the Hertz. We don't have a unit name for radians per second, the angular frequency, which pops up. And that seems to me that could be a Hertzberg, because he was a very big spectroscopist. And then there was, I think it's called the Ktal, was proposed for the turnover numbers for enzymes and things like that. So it seems to me that with Michaelis and Menton, we should really call that the Menton. And that would be the first order rate. So, you know, we can be imaginative here. And I think the principle here is that, as Blair highlighted, if you read back Guggenheim's work and some others about dimensional analysis, you already mentioned that length and height and depth are independent in many cases. And you can usefully do dimensional analysis by extending and considering those orthogonal measurements as separate dimensions. Sometimes it's useful, sometimes it's not. Sometimes it's useful to explain that some of these special units do have a significance and give them a name. And sometimes it's not useful to do that. After all, we talk about energy in all sorts of different ways. But, you know, just like our astronomical colleagues, they have hydrogen, helium. They occasionally talk about lithium, and the rest are metals. Right? For their purposes, the periodic table are metals. Under the sort of conditions that you get in astronomy, maybe that's true, but, you know, suit for purpose. But it's the overall message is, how do we convey information about stuff that we generate in such a way that other people can use it appropriately for their use? And that's the difficult problem to do. Anyway, I just thought for amusement, and if anybody's got any other suggestions of names for suitable units that we could bring in to our community, I'll collect them up and maybe we'll put that up for Chemical CI for the Christmas edition. So with that, I really want to throw this open to you guys. We've had quite a lot of discussion, some have been here, some not. I know that there's been some plans to take things forward. We can hinge quite a lot on work that has been done and problems that have been surfaced, but are there any things that people would like to highlight of areas that we should be trying to aim to cover? Anything that people have realized that there is a problem they didn't know was a problem, or a solution out there that they might be able to pinch and use that perhaps hasn't come up in the discussion? So make a note of it.
But it's always annoying that all chemists use mole per liter, and this is not directly SI. It's a factor of 1,000 away from it. But if we call it Bunsen, then we would say, okay, our millibunsen is what we usually use, milli or kilo. Well, anyway, so yeah, that's on my wish list. Something for mole per cubic meter.
Well, and actually this is called molar among many chemists, which we should not use at all.
Yeah, with the whole, well, amount of substances, you always pointed out, you and Martin point out that the German for it, which is amount stuff, I think is the translation. It works very well in German. Just doesn't work quite. Actually, the more often you say amount of substance in English, it starts to work a bit better. But I do think it would actually help when we're teaching to be really clear about that, because it does cause confusion, especially when you then get a mole fraction and we don't, and there's this problem of the fraction is a fraction. Interesting, if we follow up one of Stuart's slides there, where he puts up all the different, lots of these different unit software and the software that goes with them. The Pint brings into Python some unit handling, but I think the only programming language that I know that built in units quite early on into its system is F#. So it was probably in response to the Mars orbiter problem. I don't know how many of you know this famous case that the Mars orbiter, well, it probably went off into space rather than crashing. And it turns out that they should have realized something was wrong, because every time they did a mid-course correction, something went a little wrong. The problem was it was well on line, so it really didn't show up too much. And the problem turned out to be that the drive unit, the rocket, was built in America, and the control software comes from France. So the control software worked in newtons, and the rocket worked in American, so of course it worked in British thermal units, which most of you have no idea what a British thermal unit is. It may appear on your gas bill, that's about the only thing. Now, that's the statement, right? So there was a miscommunication between the control software and the rocket software. Yeah, but engineers are not stupid. They knew this perfectly well. The problem is both sides built the conversion in, and that was the difficulty. Right? Now, that's a much more subtle problem. So what you realize is the problem of type checking, which between the call of the subroutine and the, the Constance bridge, that was an offset problem in the bit. But the problem is you call a subroutine and it may type check what's going on, but it didn't necessarily quantity check. And that's, now it turned out that quite surprisingly, my understanding is, it's slightly anecdotal, that some of the biggest users of F# are the accountancy and insurance companies. And one of their cases is the problem of a percentage versus a percentage increase. And this causes a nightmare for them, like it does for most people trying to work out what their mortgage is. But they're a percentage, and the percentage is anyway a fraction. And so there's a factor of 100 that you don't know for certain, because number, and a percentage increase, it's on what, I guess that's on the interval. Well, it's a ratio scale of a ratio. So it's really very hard. And if they apply a percentage increase as a percentage, it goes wrong. So that could be encoded apparently in F#. And this is why some of the big insurance companies recoded a lot of their software in that, so that when something was passed a percentage, it says, no, I'm expecting a percentage increase, something like that. So I think there's a lot we can learn from the wider community, as we learned from Gyorgy about counting things. And counting things are very important. He didn't address the CO2, kilograms of CO2 equivalent, which I would have liked him to, and that's a project left for us to deal with on drum. Any other thoughts, either funny units or actually even more serious things that we should consider? Even these units have a point, why it's done. Actually, then the meters cubed is not so big a difference from the liter that it would cause inconvenient quantities. Phil.
Thank you. Some years ago, some people had read the Green Book and said, oh, well, Vermil is something we shouldn't use for doing isotope delta. So we better invent something that we can use. They decided on the URI, which would be a delta value of -1 would be -1000 per mil. So delta value of 1 euro, which is 1000 milliuri. And it would all kind of work out, wouldn't it? That same issue that you have with per mil is that once you change the reference, your per mil is a different size, and you've ended up creating a name of a unit that is different size depending on measuring it. It doesn't change. And it's not really been adopted. There's, I think, 2 laboratories in the world who insist on writing milli on everything they do. And nobody else does. Everyone else goes, well, we've been doing per mil since the 90s. Why are we changing? That's one thing.
If it comes, I mean, one of the things that Phil and I discussed is that there was a very good reason why you referenced things to standards. For standard, the NMR machines were the same, because you weren't absolutely sure of the magnetic fields and so on. You put a standard in. A lot of these things change as technology moves on, and you don't necessarily need that standard anymore. We can do things on a more absolute scale, and yet we don't change because, you know, this is tradition. At some point it cracks and you do change. But then it's important that all the previous stuff, I mean, as an undergraduate, I was still in a time when you had to remember that some of the previous molecular weights were defined for hydrogen is 1 rather than carbon-12 is 12. Now, to an undergraduate, it was an academic difference, but to somebody who was actually measuring these things, and we did measure the carbon-12, carbon-13, that was one of the experiments we did, from natural gas I mean, it was the time also people were switching from town gas to natural gas. And actually there's a significant difference between the two in the aspect ratio. So we were aware of the reality of the difference, but but the standards do make a difference here. But as you switch them, so again, that needed to be in there. And a lot of it was just assumed, well, you have to look at the date of the publication to notice whether they're now sufficiently old that people really don't look there. But those reference points are then very, very important. And that, of course, it's changed again now. And now there's an uncertainty on these masses that there wasn't there before, which I'm pretty sure, for example, most of the school teachers have not realized the definition of the mole has changed. I'm waiting for my son to come home and tell me his definition of the mole, and I will argue with it. But since Simon and I taught his chemistry, his headmaster, we hope he will get it right. Any other thoughts? The end of the day, it's the end of the week. Okay, I think then draw things to a conclusion here. I found it a very exciting day to be able to sort of reposition from the beginning the whole what's the environment that we're in. And thank you very much, Vanessa, for doing that and encouraging us to think out of the box about what we're trying to do. But also there is a community of philosophers of chemistry, and I think we need to engage with them and learn from them. I'm hoping that they might, we just discussed, maybe they could be the bridge between the analytical side, the measurement science side, and those who are actually trying to sit there and do some chemistry with it. And we know that there are significant issues there in talking, and we do need to talk more. Maybe we can join that up. Through to technology moves on and technology gets simpler. And I think Joseph pointing out with the Unicode, things have become simpler to represent things properly. But maybe sometimes we need to make more fuss in the right place to get the symbols that we want there. And we can still have a plimsoll line. We don't have to put a 0 in there that could be that doesn't mean quite the same thing, at least to me, in the standard state. Saw with Stuart producing the Green Book there within a framework that is now a conventional framework that's available, widely supported, showing that we can get down this digital route. Haven't quite sorted out how you might be able to use those files to produce other things, but producing a PDF is certainly possible. Producing HTML is there. Whether we can feed those into the accessibility engines that then give you allow you to get to speech to text type, text to speech and so on, screen readers. But at least there's a chance that they will do, because and we can get, we have master copies of things, and that's where we were trying to go. They got to a point with the Green Book where we almost gave up on the digital because we could not get the traction with the publishers to do what we wanted. Well, now we can do what we need. It's fairly clear, and we just need to make it simpler and easier to do, and we will be learning how to do that. But content also moves on, as we discover, and getting agreement on content is even more difficult about things. So that is one of the challenges, but at least now we can share content more readily. But the discussions about what things mean is still just as difficult as ever, and the mechanisms for doing that. But again, listening to somebody, they were interviewing one of the current leading mathematicians, say, well, what do you want to do when you learn some more? Someone wants to learn a bit of different maths. He said, well, I sometimes look at Wikipedia and see there to get some key references. I said, you look at Wikipedia? He said, yeah, but I know enough maths to know when it's foolish, and I know enough maths and people to know when the references are good references. And then I look up, but it's a very convenient place to go and find something. And I think that's an issue. We can make documents available, but if people don't, if it's an audience that we're trying to work through that doesn't have the background, we have to be exceptionally careful about the information we put out. To a skilled background audience, that's fine. And in that sense, the computers consuming our information are very foolish, and we really have to be very clear about them. So still lots of challenges, but I hope you've had an exciting time and learned that there are potential solutions to some of your problems. Thank you for coming, maybe we'll find some funds to organize another one next year. We'll have to see, but maybe somebody else will do that. Sorry? Well, the quite one behind you. I think I'm on the same grant, so maybe, yeah. Next time we will try to be a bit more organized and try, if we do it, and a bit more in advance. The other take-home message, it's one of the reasons for organizing, it's a long delayed version of this meeting, it's a bit different to what we actually had, was a discussion, as well as the RSC-IUPAC committee meeting where we met this morning, and that is looking quite exciting. Changes are happening. We used to have a CSN, so what would nomenclature meeting, which actually had people from the standards laboratories, from the patent people, from the school teachers, from the examiners, across the board. Because the school teachers, it's now been a long time since they produced a new version of a book that actually has, it's a version, if you like, of the Green Book plus nomenclature and so on, to recommend how teachers should use. This had gone a bit into abeyance because the kind of people, we lost people and it wasn't clear there was anything more to be done. The updates to the nomenclature tended to be rather more obscure than was being taught at a lower level, and that was being taken care of. I think this meeting has evidence there is an absolute need to have that group deal with agreeing things and what should be in the digital space and what the new textbook people who produce stuff that turns up on the web, what we should do there. So we will be trying to get hold of the relevant people, replace the people who have long since retired, and get these on board. So.
Thanks, Jeremy. I mean, if we're going to talk about sort of next steps, and this comment was prompted because you said, oh, maybe we can organise something similar next year. I mean, I think this has been very useful for a general conversation and to spark some ideas. And what I'd really like to do is, okay, what are the next step? I mean, Agnes has been very kindly typing things down, and I hope hopefully we have some very specific things that we could follow up on. In the discussion we had earlier, at least, there was, okay, what sort of recommendations can we make to PSDI about units? And I know that Eileen's been working on that. What recommendations can we make, or how can we use that sort of work to contribute to the CDIF profile on universals and get some drum input to that as well? And then the discussions we had about modeling units and properties or modeling quality. If any of those ideas spark interest, what I would like to see as next step is a 3-day workshop, but with the emphasis on the work, where we're around tables and we're looking at code or text and trying to write recommendations.
Yep.
You know, to push it that step further.
Sure.
In a really practical way, that's hopefully of use to PSDI, but is also of use for the other stakeholders that are represented here.
Absolutely. So Colin and Agnes have been making notes. We have copies, I think, of everybody's talks. I will be checking how we can make those all available, but they will be used to make a set of notes, and we will draw out a set of, so especially for the conversations people have put in, I know I owe some stuff into that, but captured in the notes there, we will throw all that together. So immediately there will be reports. So there'll be an extensive report that will go out as under the PSDI, you know, a big long thing. There will be summaries of that will come out through IUPAC and CodeData and others, being made available as reports. And then, yes, if we have a set of actions that we will draw from there, I will be very keen that we sort of create that workshop space to actually do the work. We hope to be 2 days, but probably going to be 1 day at the moment, and it's coming up at the end of April under the Chemical Information and Computer Applications Group, the RSC, to actually create the more than the framework for a Python for chemists, but more for not just physical chemists, so not just examples full of numerical calculations, but the sort of draw molecules, do things with it, to engage that chemistry community. There's lots of stuff around there, but none of it's, you know, as we've been teaching it, none of it's just quite, we've learned lots of lessons as we teach it more and more. Pull that together. Now that's a very limited special thing that's fairly clearly defined, but useful for chemists. The idea that we get people together for 2 or 3 days to do that sort of work is something we think is a really good way of getting something done. So absolutely, and I think the notes are still open, will be open. So anybody who's got any other ideas, put them in, and we will get them organised, and we'll put them out as an output. As I said, people will then be able to refer to this, the Burlington House meeting, something like that. Anything else people would like to say? Okay, well, then, thanks again. I'd like to thank Andrew and Jamal for organising things and getting everything arranged, dealing with all of the arrangements inside here, all the meals and everything, liaising with all the staff here, and to Victoria, who you all probably talked to, who made all the arrangements. And well, we'll see how many of you decide to use the Z well again and bring your, as Helen says, bring your own window. And thank you all for participating. It's been great. And thanks, Stuart, if you're still online, for particularly all the wonderful work that he's been doing. Thank you.